So this is a pointer system. So this is a slide forward, slide backward. It's a little bit delayed in the working. And this is pointer, and you just, it's a virtual pointer. So you click it in, and you point, and it's a little bit delayed.
Delay as maybe if you delay, maybe people.
Delayed. It's a little bit delayed, so this is slide forward, slide backward, a little bit delayed, and this is virtual pointer. So just point to the screen, wait, and you see the red.
Oh, you pointed on the screen.
Yeah, it's virtual.
What do you mean by virtual? What does that mean?
Also, that means that knows where it is in space. So it doesn't take off your finger off.
But when I look at my slide, then I will see where the pointer is with respect to the slide.
You see your slide here.
And this will project the thing up to there.
And online.
Okay.
That means that where you're pointing this and click there,
Yeah.
that is basically your reference position.
Okay, I get it.
Okay, I'll give you 5 minutes for it.
Good morning, everyone. Welcome back for day 2. Yesterday was great. I'm sure today will be even better. So let's just dig right in. Lars is going to chair the session.
Okay, so the first speaker is Rick Devore, and he will talk about the of reconnection, Corona, and the calls for arms.
I was instructed just to use the podium microphone. Okay, good morning, everybody. Thank you to all of you who are survivors, hardy survivors of last night's banquet. It's good to see you this morning. And I'm going to be talking about arms, its genesis. My talk's going to be more of a retrospective, really, than a highly technical talk. because my plan is to emphasize the key role of Spiro's scientific ideas and his scientific leadership in the generation of arms. And so my topic is reconnection in the corona, call to arms. And for those of you who aren't aware, ARMS is the adaptively refined magnetohydrodynamics solver. And we saw several talks yesterday, and there will be a couple more today, that will feature results of simulations that were performed with ARMS. So this ARMS is not an instrument for warfare, but an instrument for science, for heliophysics science in particular, deploying time-dependent, three-dimensional, nonlinear, solution-adaptive simulations of MHD systems, such as the corona. So this is a highly oversimplified timeline of Spiro's career. I know the top line is highly compressed. He was at more places than just Stanford before '85. But I put it up here because what I'm going to be talking about are his scientific ideas and the development of arms that resulted from that during his NRL years, beginning fairly early after 1985. During that time, in addition to many other scientific ideas, concepts, models that he developed, came his embedded bipole model for jets, which we heard about some yesterday, and of course also the breakout model for coronal mass ejections, which followed just a little bit later. So let me carry on. Spiro has a procedure that he applies when he does science. I refer to it here as his recipe for success. When he tries to understand the sun or any other science object he may be studying, the first, examine and understand the observational data, use physical insight to develop a model, and then derive qualitative implications of that model for observations, and using analytical approximations and estimations where possible, derive at least some quantitative considerations. But Spiro's not content to stop there. He always wants to see the detailed implications of the model that come out of solving the nonlinear time-dependent MHD equations, and so he's always eager to see detailed numerical calculations performed and see the quantitative implications of those results for the observations, which we can then feed back into the model and the simulations to revise them as needed. During that time, Spiro was thinking a lot about magnetic topology and magnetic complexity in the solar atmosphere and the formation of current sheets, and especially the topic of this session, the onset of reconnection and the implications of that reconnection. So the sun's atmosphere is highly magnetic complex with numerous flux systems butting up against each other, and the constant churning of the atmosphere is continually adjusting the boundaries and stressing the boundaries between those systems. In particular, null points and separatrices, they become activated boundaries between neighboring flux systems due to this ongoing dynamics of the atmosphere. Current sheets form readily at those boundaries because they are magnetic discontinuities, and therefore they become susceptible to reconnection. Spiro emphasized that it was very important that that reconnection be left off for a long time so that energy could be built up under the null points within active regions before the eruption would turn off or would turn on, and that there would be a sudden turn on and then the reconnection would stay on after that process got underway. And that was important for getting explosive energy release in these events. So these are the problems that we were wanting to focus on numerically as well. So to test this hypothesis thoroughly, we need magnetohydrodynamic simulations, but there are two problems. At that time, this was in the, again, late 80s, early 1990s. The MHD simulations of that era employed globally structured numerical grids with more or less uniform resolution everywhere, whereas the important features for inhibiting and then allowing reconnection to occur in the corona are low-dimensional structures in that atmosphere, point-like null points, line-like structures or surfaces like separatrices. So in order to optimally address these problems and thoroughly test his ideas, we needed to implement adaptive mesh refinement in our codes. There was a confluence of convenience at this time in the 1990s in that at NRL there were active research programs on high-fidelity algorithms for shot capturing in computational fluid dynamics, adaptive mesh refinement, and massively parallel computing. And the advent and advances in parallel computing drove a lot of this algorithmic development so that we could really exploit that exponentially growing computer power. We had a partnership already between our Laboratory for Computational Physics and the Space Science Division, where Spiro and Judy and Jim were located. And we had a joint NASA theory program, which Spiro was leading. But that was not an appropriate forum for doing our software development project. The Department of Defense was investing heavily in high-performance computing and also had a very large software development program. And they had a call, and Spiro was inspired to combine our people and skills with personnel at the Air Force Research Lab to attack this problem. And the idea behind the proposal was to create ARMS, the Adaptively Refined MHD Solver, and also Heliospace, which is a desktop visualizer for ARMS data, and that was based on the Air Force's Geospace desktop visualizer for near-Earth space environment. So we wrote the proposal, Spiro led it, the DoD reviewers approved it, and ARMS was born. Let me say that Spiro was very enthusiastic about the prospect of having this great software tool that we envisioned at the time. I was very excited by the prospects too, but I was also very apprehensive because I knew it was going to be a ton of work, and we really couldn't be sure until we built it how well it would work. So, but Spiro was inspirational, and I liked the challenge, and so we took it on. Well, these many years later, I think it's fair to say that the project was successful. I wouldn't say it succeeded beyond our wildest dreams because we're able to dream pretty wildly, but I think for sure it exceeded our minimum expectations by far. So what I'd like to do here is just show a couple of examples from problems that illustrate the sorts of issues I was talking about. So this is a calculation that was done by graduate student Justin Edmondson at the University of Michigan, where Spiro was an adjunct professor, and Thomas Verbuchen was Justin's faculty professor. So this is a very simple embedded dipole configuration here in a nearly vertical magnetic field with a null point here, conveniently in the circle. From this null point, there's an inner spine line that goes down to the surface and an outer spine line that goes up to the top. And this very simple system is driven by applying a flow across the top boundary that convects the field there from left to right across the screen. What this does is it stresses the null point and moves the outer spine line here at the top to the right and displaces it away from the inner spine line. If you remember the little cartoon that Peter Wiper showed yesterday, Spiro had used a cartoon in a paper to show how that would lead to the formation of a current sheet and eventually would induce reconnection. And so this project was designed to test that idea and see what other implications we could derive from it. So Justin started with the grid that's shown here on the right side. Each rectangle in this image is not a grid cell. It's a block of 8 by 8 by 8 grid cells. This was actually a three-dimensional calculation as well, with symmetry out of the plane in this simple case. And he pre-structured the grid because the displacement of the outer spine to the right was going to create, we anticipated would create a current sheet off to the right of the null point in this volume. So this was a pre-structured grid that was set up at the beginning. After some time, I'm checking to see, it's probably going to be very hard for you to see the grid lines in this calculation, but 4 additional levels of grid refinement were allowed in this calculation. And in the paper and in a very finely resolved image, it can be seen here that this is a time sequence from top to bottom showing no current structure here at the beginning, of course, because the field was potential, and as the outer spine was displaced to the right, the current sheet formed and lengthened and increasingly tilted with time. We got to an aspect ratio of about 80:1 or 100:1 in this current sheet, which was facilitated by the adaptive refinement, and eventually we saw onset of plasmoid instabilities in the sheet. And this sequence of arrows, this is another time sequence on the right, and the arrow points to a plasmoid that forms in the sheet and then flows down to the end of the sheet. So this illustrates the power of ARMS and its ability to refine these time-developing structures. This particular calculation, there was no significant amount of free energy stored in the system, so the evolution was quiescent. It wasn't explosive. But let me go on to another example, which is our famous breakout coronal mass ejection image. I think Peter probably showed this yesterday. And this is an ARMS application of the problem Spiro and I with Jim had initially studied back in 1996. And I'd like to show this image, which is at a time similar to the one that's on the photograph, the beautiful color image out in the lobby, but this is zooming into the sun and showing the flare current sheet. So here we have so we have the separatrix surfaces here, the flare current sheet and flare arcade here, going up into just below the flux rope. There are also current structures here, which signify the boundary of the sheared flux region from the unsheared flux. And the key takeaway here is the fact that the regions without strong currents are coarsely resolved, and all the regions where we have strong currents are very finely resolved. So we're able to carefully track those aspects of the system, those structures in the system, and inhibit reconnection there until the physics demanded that the reconnection turn on. So the ARMS project was conceived and begun about 25 years ago. It was right 1999, as I recall, actually. And in the intervening time, Spiro and Judy and I and other collaborators, our postdoctoral associates who have become peers and colleagues, graduate students who have become peers and colleagues, have used ARMS to study a lot of problems in the corona, not only the jets and the CMEs, but also pseudo-streamer dynamics, the S-Web slow solar wind, and helicity condensation and filament channels. It's been a very productive 25 years of effort. We heard talks yesterday from Ben Lynch, from Judy Carpin, Peter Wiper, Erica Palmirio, Kalman Knishnik, and Joel Dahlin that featured ARMS simulations. And today we'll hear from Etienne, Pariat, and Sophie Masson. And I'm getting a pointer to Aleda. I guess Aleda is going to show some ARMS results too. I didn't realize that. Great, Aleda, sorry. Your abstract didn't emphasize that. So let me conclude. My talk's mostly been about the past and how ARMS came about and what we've done with it, but we're looking forward also. We had an ARMS workshop the first 3 days of this week, where we were talking about current science and technology and plans for moving forward. Nearly all of the first generation ARMS users that Spiro and I trained were present and are here today. And there are some second generation users who were trained by them, who are also participating as we get ready to move into the future. And I at least take more of a back seat to these activities. Perhaps it could be referred to as an arms takeover. But I embrace it. And what I want to emphasize here, also, this is a photo of us. We were gathered here. And you'll see that Spiro is in the middle of the photograph because he was in the center of the action a good part of the time, providing inspiration and ideas as always. So what I would like to say is thank you, Spiro, from me individually for our partnership and for all the great science that we've done together. And on behalf of all of the Arms Squad, thank you for your ideas and inspiration, and congratulations on your many achievements.
Okay, Spiro.
I'd like to make two written, designed, because I got 100% by Rick. So the output, all the output that has come, as you say, it's helped all these students. We've done so much science from it. It's all based on your work, Rick. So you've done a fantastic job on building this tool, the general purpose tool that we can use to investigate processes in the corona. The second point is that for coronal science, where you're looking at reconnection, and reconnection needs current sheets, you really do need to have the adaptive mesh refinement. Because the corona is kind of a unique system, or shall we say a specialized system, where current sheets form, shall we say a specialized system, where current sheets form, in most cases, at special locations. They don't form everywhere. If they were to form everywhere, then AMR doesn't help you much. But if you're looking at something like an embedded pipehole, where you know the current sheet is going to form at the separatrix and the null, and you need to resolve as well as possible that current sheet. Of course, you're not going to get it to the Lundquist number of the sun, but you need to resolve it as well as possible in order to see if plasmoids do form, and in order to see things how things scale with numerical resolution. Then ARMS is indispensable for doing that kind of science. So thank you, Rick.
Thank you, Spiro.
Thanks. So I want to ask about the assumption, or the point you put in there about the buildup of at the current sheet before the reconnection ensues. We know the jet model from Shibata and Yokoyama, where you have emerging flux coming into an open field, and you get a current sheet forming, and you get current building up there, and then you get a burst of reconnection that makes the jet. Mm-hmm. We've looked for jets, Ron and I, and Navdeep and others have looked for jets that work that way, and we just don't see them. We don't see, in emerging flux places where jets form that way. So it seems like actually the sun is deciding to reconnect. I mean, we know that flux is emerging into the open field, so reconnection must be occurring there, but it seems like it must be happening very rapidly, at least in those sorts of circumstances, because it seems like you don't get the buildup of the current that allows for the burst of reconnection and the jet to occur in the Shibata type of fashion.
Well, there's no question that if you have flux emergence, then you easily can get driven reconnection because you're driving flux systems together that can be anti-parallel. Are you saying then that you're not?
So the Shibata model says that you would get jets based on that. You know, the current sheet, the current builds up, and then you get sudden reconnection that lets out a lot of energy, and the jet comes out. We do not, we see, when we look at the sun, we see emergence into open field regions, but we do not see jets formed that way. The jets don't come that way. They come from, other things. Okay, and people are going to answer that, but also I want to know if we heard about Spiro's good
politics. Was the name of arms based on that because you were working at NRL?
Well, actually, I should have mentioned that. The arms name did come from Spiro, and he was inspired to create that before we submitted the software development proposal for the program. And we think the reviewers probably didn't object to that because arms sounds militaristic and aggressive, and that plus the fact that we actually said we would work with Army people may have impressed the review panel.
Yeah, so let me address the point that Alphonse made, which is an excellent point. The simulation that Rick showed by Justin, where you drove the system, so the only currents you'd get were at the separatrix. There was no eruption there. Because what happens is, as you say, the current sheet builds up very quickly and reconnects very quickly, so you never build up much free energy. So what you need is kind of a subtlety there. You have to build up volumetric currents away from the separatrix at the same time, and then rely on some kind of feedback between the reconnection and the ideal motion to give you a burst of really strong energy release, right? So you're right, just simple flux emergence is going to drive reconnection of the separatrix right away. And yes, you will get some energy release, but it won't be explosive. You need more than that. So again, this is why you need to have AMR, and you need to have a robust code to kind of distinguish these dynamics, to separate these dynamics.
Okay, thanks the speaker again. So next speaker is Hantao, when you talk about the solar reconnection, the beginning of the problem, but also the end.
Thank you for the opportunity to talk at this important meeting for Spiro. But before for one thing, that the reconnection workshop, we decided last time in Japan, in Hawaii, were not helping. It's in my email, and we worked very hard, I promise, but we couldn't make it work. Many other things I can tell you in private, but we're going to happen next year, about a year from now. Hopefully Spiro will come. Yeah, it's not too far. But the reason is that many people preferred Hawaii, and we worked really hard. But we'll find other opportunity to go there. So this is one. But then we have two review papers here. As you know, getting older, you write review papers. Two review papers here. As you know, getting older, you write review papers. That's maybe not a good sign, but it's because there's good reasons. Li Jiang, thank you for the inspiration. The first one there, which is a good opportunity for us to learn what we have learned, and then we can look into the future as well. Okay, so also, thanks a lot of people signed the white paper we have right now is under the panel, I guess, the digital survey. Hopefully promote collaborations on reconnection topic. No missions, no arms, but needed some scientific collaboration. This is our goal to move forward. Okay. So that's a very simplified version of the history of the reconnection. And it's so simple that you feel upset, putting somewhere is missing. But I think globally, maybe it's okay. Because it's really the reconnection embodied by sun throughout field observation. And the phase one here is really MHD. We heard about this already, and it's still ongoing. I put a 90 there, doesn't mean stop there. But the main activity has been MHD. The models that we know is Sweet-Parker, Pachak. The underlying thing is Sweet-Parker is pretty winning, I think, but not everyone agree still. And the focus rate, the reconnection is fast, slow, and observation-wise, I remember first time I saw the Yoko movie. It's pretty impressive. Before with the pictures and such, we have movie in X-ray. It's eye-opening, really. So it's really opened the new era of the reconnection research due to the solar observations. The experiments is really slow and catch up a little slowly. Of course, the fusion experiment happened during the 70s even, but the controlled experiment in the lab, including MX here, is happening only in the 90s. But second phase, quickly kicking in, it go beyond MHD because they couldn't find a fast solution other than Pachak. And it's obvious in the space, there's many other things going on other than MHD. So the time, the debate is, of course, still rate, but also dynamics. So how exactly electron ion behave dynamically to give the reconnection rate that you see. Of course, model-wise, there are how about whole MHD? It's very simple, but it may need a full kinetic. I think by now, with the new observation of MMS, I think full kinetic model has to be in place, not just simply whole MHD. And in situ measurement becomes dominating rather than solar. So it's still like not so new solar observation, but the kinetic reconnection has been dominated by in situ measurement by the spacecraft around the Earth in the solar wind. And cluster MMS, I will mention a little bit. The modeling, of course, keep going and also things competing. And experiment and marks, I'm going to say a little bit, that it really tackle on the kinetic aspect reconnection. Now I'll talk about phase 3 there, which is important. And it started actually a long time ago already. And not just the MHD or kinetic, you need both. Why? Well, the solar flare reconnection, it is both. Sorry, ARM, and I'm not, it's ARM getting to much more refined scale at time. But eventually, I think it'd be nice to include kinetic physics when get to there. And I can't predict, I don't know for sure, but in order to understand both MHD kinetic simultaneously in solar flare, probably you need one way or the other, that kind of model, otherwise you won't be convinced. So there's 2 ideas, plasma-based, we heard a lot of things about plasmoid model and the 3D turbulent reconnection model. And we need a macro scale observations. Good things in Europe, the plasma observatory is under study. I hope will be real mission. And we are looking for the panel for the Deco survey, see if anything come out in the next 10 years on that kind of frontier. And experiment, we have flare experiment, which is confusing you, right? Flare, too many flares. So maybe one thing pro, flares, this is solar flares. The singular flare, this is device. That's a little, not enough, I guess. But I hope you can understand. But it's a good reason for flare. It's because you really saw a macro scale reconnection problem. So there's 100 years ago, we had this, it took 100 years before getting real physics research, the phase 1. And prediction the future is hard. I want to predict when Spiro is 100 years old. We stand here and say, we saw reconnection. But solar flare. I don't want to generalize. There's many reconnection happening in the universe. Solving everything probably is impossible. But solar flare is just about right. Big enough, you have macro scale, enough challenging, but small enough, not too far. You can have lots of observation and everything. I don't know what other people think, but I think it's a very neat compromise, the best place to study. I guess this is going like here, but there's good reason for that. Okay, so the rest of that, I should go quickly what we have done, the MI part, which I know very well, and Spiro knows very well as well, because we go to reconnection workshop all the time. But I want to come quickly to the flare, what we can do to contribute in this macro-scale reconnection research. Okay, this is a device, and nothing to show, but inside, there's 2, by the way, Masaki and Russell say, congratulations to Spiro, they cannot come. Okay. Then there's 2 coils, one left and right. You can drive them under your wish have field line in between the reconnect. So this is a cartoon always we show. There's a left coil, kind of like green one, right one, yeah, same direction current. You form quotable structure, not a bipolar. Remember here, quotable structure. And if there's a null point in the middle, like Judy would say, you need a null point to start with. And then if you change the current in the group, then the right-hand side, I can try this. Very nice. So if you left, right, if the current is the same direction, then you have reconnection in between. If the current increasing, we call it push reconnection. If the current decreasing, we pull reconnection. And pull reconnection means the field line go around 2 coils, come together, pull together by pulling away to the green coil, then have to reconnect in the middle. So if we think carefully, it's about roughly it's breakout. Why? It's quotable, right? It's not the bipolar. If you look at it on the top, if you make 2 incoming inflow asymmetry, so one's over stronger than the other one, you could push out the current sheet to different gradient locations. You're going to break out. So I'll say, wow, we're doing this all the time already in the nav. Of course, it's not exact. And it's a new device in flare. We do have drive coil that and the larger radius, the small radius side. If we only turn on one, not the other, it can break out or break in. So in a sense, you really want to study the geometry of the breakout reconnection on flare, we can do it. This is after hearing yesterday's discussion. We are doing that already for the past 25 years. Anyway, so what we have done is we change the cardinality of the plasma. We make mean free path very short compared to any scale of the plasma. This time, the thickness of the current sheet. If the mean free path is short enough, everything falls into MHD. Like MHD Ohm's law works perfect. There are no missing terms. In that case, 3 Parker really works. There's no missing mystery, everything. We check it's 2-dimensional, everything. There's no mystery anymore. But if we go to the other situation, you make a mean free path long, then you need to put into additional term the Ohm's law, we call it generalized Ohm's law, not just the Spitzer relativity term, but the other term. This is the detailed kinetic physics we have to study. But that's one feature here is the so-called quadruple structure of the outplane magnetic field. And I skipped the details, but that's the signature of that term. The additional terms are important. So if we do that, we are convinced that that's really happening. And you compare to cluster, this is one running more than 10 years. And statistically, they can see the quadruple structure at the bottom by Jonathan Eastwood. You see a little bit connectively red, black, red, lining up very much like the experiment. But it's only statistical because you don't measure simultaneous in the MRX. On the right-hand side, you can see the potentials, electrostatic potentials, which you don't measure in the sun, but they measure in the magnetosphere. And half of that matches pretty well between experiment and the fluster measurement. The MS, we have also good agreement, and the left side shows normalized units of the profile of the magnetic field and the current density. It matches, okay, there's an error bar there. But roughly not bad, but actual field, there's a factor of 10 difference between two. We are still working Y. And then right-hand side shows the asymmetry connection, and left two is from experiment. Most of the right ones is from the observation. Matches pretty well. I think more or less qualitatively, we are settled with the this kinetic reconnection by comparing experiment and the space. Of course, we compare with numerical simulations. The left is the experiment, right is the 2-dimensional particle in cell simulation. And to some details, they agree very well. There's not much room you can argue is missing anymore. Okay, with this, we have two, the phase 1, we set down the coronal reconnection 3 Parker. They are good with the big plasma, but they are slow in terms of reconnection rate, in terms of prediction. But in the phase 2, we say, well, kinetic reconnection works, but they predict fast reconnection. Unfortunately, it doesn't apply for big plasma, only good for small plasma. Now we need to combine them together, so solar flare. Globally, they are MHD, like arm, we see that, right? And locally, they are kinetic. Mean free path is much longer than any size, like a kinetic size that you think about this. So you need to combine them into one self-consistent model so that it can be applicable solar flare, but still give you the answer you want to have from observation, like onset, remember the energy and how they really work in time scale, the rate and such. So this is a multiple scale challenge called phase 3. So there are two competing ideas right now, maybe there are more. One is based on plasma instability. If you stretch the 3 Parker MHD current sheet, it should be unstable. The unstable current sheet becomes the plasmoid in between. There's a new current sheet, which could be more unstable. They eventually get to kinetic scale. And by how many? Well, by Shibata Tanuma's estimate is they have like a 4, 5, 6, depends on the detail of the model. It don't take too long to get to kinetic scale by this model. But whether it's right, I don't know. But right-hand side is a well-known 3D turbulent reconnection. It may not like this, the details, but the idea is still there. And there's no reason to believe reconnection laminar in such a large scale. Just like any system, like a turbulence, fluid turbulence. So it must be some sort of turbulent. Whether turbulence is well defined or not is a question, but hopefully there's a solution there. So based on the left, the plasmoid, we construct a sort of reconnection phase diagram. Of course, it is wrong, But let's give you some ideas still. Right-hand, the horizontal axis is size of plasma. The real plasma normal is the ion kinetic scale. Vertical axis is nucleus number. And in addition to single X9 reconnection, we see, but you can have 3 more multiple scale reconnection regimes. And the middle ones, the circle, solar corona, is really the hybrid. It means globally fluid, locally kinetic. You need 2 kind of reconnection physics working simultaneously. So we propose a flare, this project, trying to cover all the 5. It's very small in this scale, but trying to reach the new regimes of reconnection, and it didn't happen in the lab yet. So that's the main version. Back in 10 years ago, Jim, I'm happy to see you in person now. We worked together, wrote a proposal, getting the NSF funding 10 years ago. And this is the cartoon on the right-hand side. And it's very much similar to the MRI, except it's very big. It's very energetic. The red coil is a drive coil. They say if you turn on the one pair, you get the break out or break in reconnection, remember? So, but the new regime coverage should be enough to cover all the 5 different regimes. And this is 5 years later, we made it happen. So we call it stage 1 energy with 0.8 megajoule. It's already very large compared to MRX. And you can increase the MRX box to stage 1 box. The closest the result is a test experiment. And that works pretty well. And after that, as mentioned, this is 2 pictures I want to show you quickly. The left is the result guide field. And you can see and hardware there, but you also see, if you are solar observer, you see the strikes of maybe symmetrics. On the right-hand side is a discharge with guide field. You can see that there's a helical field line go around, but maybe there's plasmoid out there already. But we don't have in situ measurement to tell you it is really plasmoid because this is morphology measurement. This is white light in your terminology. So now we are moving the flare into PPPL, which is plasma physics lab, and increase the energy by another factor 8. And right now it's under construction. And we call it second plasma. Thank you, yeah. And hopefully another 8 months, 10 months, we really see the second plasma. And we want to make a user facility, which means everyone with good idea, which is doable, we can do experiment together. Not just I do it, we can do as a team. Yeah, this is the idea, not just for one team, one person. No, it's a whole community. And it doesn't matter where you are. It don't have to be United States even. Okay, so this is the current status. And then what I can do experiment, the topic-wise, there's 2 medium to list. Multiple scale, you have lots of topic. Actually, some of them can be PhD thesis, each of them, right? If you do right, reconnection rate, and the partial ionization. In the chromosphere, we didn't talk too much. It's a big deal. It's very complicated out there. And you can onset, we didn't talk about either. How can you have enough room to accumulate the magnetic energy, build up, storage, and release, right? That's the idea. The 3D effect, and lots of things out there. And the particle heating acceleration. This is frontier research that many people doing that. Maybe we can do it on fair. So the red here is one thing that I'm curious. How do you scale the number of the X9, O9, whatever plasmoid? That's the key. Why? Because the scale separation between 2 extreme, you need a way to connect them. Shibata Tabunda have layers 5, 6. That's a macro scale. If it's bigger, you need more layers. If it's smaller, it's small layers. But whatever the layers, the same physics carry over. That's the beauty of the universal physics. But there's no guarantee, of course. But hard to believe, every reconnection works differently in the universe, right? It got to be some common features. And that's the one we are looking for. And if that can be done solar reconnection purpose, I will be super happy. So I'm looking for power dependent, the plasmoid. Those are pictures gathered from space and in lab, or exponential, nothing parallel. And it's disappointing, right? Then you look at the solar statistical studies. Left 2 are parallels. The PDF of the solar flare, there's a number of the energy, temperature, and such, and also particle measurement is parallel. But right-hand side, this is the one I found, published the result, shows the plasmoid is not parallel, it is exponential. So still, there's no parallel in the sense that I wanted. So what I want to do, I want to have this one. It was part of a white paper we submitted together. Many of you are signed for me. And you have exponential with small scale around kinetic scale, or exponential in system scale with exponential. In between must be a parallel connecting them. And we are looking for evidence of this. And from space and net, we are from small scale side. We want to push to large scale, see if we get a parallel. From solar on the astral, it goes the other way. My arm is one idea maybe, and you can go to small scale, see access to the parallel area. That's where we can meet together to solve the problem. That's the idea, right? So actually, it's last year, happened to be Stefan Eriksson here. Actually, that's why I came here earlier, meeting him. He did find the parallel, and in addition to the exponential distribution, as a so-called reconnection exhaust in the solar wind. And if we look at it, he connected more than 3,000 event winds that night, show parallel dependence if the system is big enough. Wow, that's a good sign to know. And we have some idea to move on 1 minute. Okay. So then Jim could tell me maybe there's something we can do, like the brightness, if the size big, small, if we do enough statics, maybe you can construct distribution functions. No. Anyway, we are trying very hard. So as a summary, is that okay? Summarize. So we said phase 3 is important to solve reconnection multiple scale problem. I didn't talk about particle acceleration, onset. They are all connected together. They are not really independent problems. And there's 3 papers there. I mean, last I want to say, we have to work together as a, I call it a 5 community here. Maybe each of them have its own method, different advantage, disadvantages. If you put them together, there's a chance maybe we can solve. If we work alone, probably it's harder. But even work together, there's no guarantee success. But I'm hopeful because Spiro will be here for another 100 years, so we will solve it. Of course, depends on the definition was successful. I didn't know solar flare how to work. I'm happy. So how about that? Thank you.
Okay, one question for the speaker.
Reynolds or Lundquist numbers do you get in the laboratory plasmas?
Oh, in the case flare, okay, it's 10 to 5. We don't want to be too high.
Okay.
We want it big as well. So the two demands sometimes not compatible. So we compromise is big enough, large numbers enough to do this all regimes.
Right.
So we are trying to as big, but not too big, that you separate, because if you're too hot, your ion gyre is getting bigger. So your normal size goes down. So there's a compromise between parameters. We tend to be cold plasma is good. Cold plasma, you can have effect on large plasma. But too cold, the nuclear plasma goes down. So you have to just compromise somewhere. Yeah.
Right. Then on the small part on the kinetic scales, when you show the exponential, it might be an exponential, but there is some evidence, which is debated, of course, that we are talking about a different hierarchy of self-organization there with steeper loss that implies a lot more frequent small-scale events over there. This might or might not be the case, but it has great implications. So if you were able to look into that region, with better statistics and better resolution, perhaps, that would be very interesting and important.
Yeah, you're right. I didn't take all the details. Oh, I think I'm in the wrong direction. Solar chromosphere, for example, they don't get access to kinetic physics. But the different neutral particle become important. This introduces another scale. That it is still largely unknown, right? Depends mean free patch between ion neutrals and neutral to ions. The another scale, where to go, is quite complicated. But if there's enough dynamic range of certain phenomena, then you can try to see if any dependent of size and Lundquist number. Sure. Sorry, maybe I didn't understand your question very completely.
Thank you, Hantao. This is really important work because we need to know not only the rate in this and that, but where the energy goes, and so forth. Let me ask you, for the meeting coming up, magnetic reconnection in 2025, will we be able to come and see flare in action?
That's the hope, because I was told 8 months or 10 months from now, which is October or December this year, so by March this year, almost exact 1 year. I'm hopeful, but I can't be 100% because I was wrong for many times now. Yeah.
It's working. I'll bring the bottle of champagne.
Wow, let's work for it. Okay, yes. Thank you.
Okay, let's thank the speaker again. The next speaker is Jim Drake. He will talk about modeling participation during.
Now, Spiro and I have not written a lot of papers together. Actually, last year was the first paper we've ever had together. But I have admired his work from afar. And I have to say that when he came up with that S-Web, it totally blew my mind. And, you know, when I saw that, I thought, this is the most innovative guy working in heliophysics that we've got. It just so impressed me. So I just want to say that at the beginning. Thanks, Spiro, for all the stuff you've done, and I've really admired it from afar. Okay, I'm going to talk about particle energization, which we probably haven't discussed too much yet. So first comment is that energy release takes place not at the X-line region where reconnection takes place. Oh, here it is. Not here, but downstream where the bent magnetic fields that are reconnecting expand outwards. That's where the energy release takes place. Okay, got it. There's a key parameter, which is the available magnetic energy per particle, and that's equal to B squared over 4 pi n upstream density, and that's equal to MCA squared. And this parameter controls whether you get modest heating or significant energization. And in particular, you get strong energization in, this thing is slow, flares, where this parameter is about 12 kilovolts. And believe it or not, the magnetotail actually can get very energetic, something of the order of 18 keV, and it's because the density gets so low, you can see down here in the tail. And then I'm going to show you some interesting results from the heliospheric current sheet close to the sun. This doesn't seem by much like very much, but on the other hand, we're seeing some very energetic protons there. Okay, so here's the classic picture of reconnection going on. And lo and behold, if you look on the right, there's this February 10th, 2017 event, which really looks very much like these classic pictures of reconnection in the corona. Okay, so let's start talking about energetic particles. So here is a classic picture of hard X-ray spectra back from July 23, way back in the early days of RESI. Here's the hot thermal stuff here, and there's the power loss spectrum from Bremsstrahlung from electrons. And here's the stuff from the lines from the energetic ions coming in. So this is a gamma ray flare. And one of the things I want to emphasize in this picture is that we know very little about the energetic ions below around an MeV. And that's going to be a crucial issue in what I'm going to talk about on the rest of the talk. On the other hand, there are solar wind measurements from impulsive flares, and in those measurements you do see nice ion spectra up to very high energy. On the other hand, they can't really get below, historically below around 100 keV, so we really don't know how far these power laws extend downwards. And not only that, you don't see any protons here. So the measurements of protons in the solar wind from impulsive flares are not nearly as good as some of these other stuff which came from ACE. So the question is this. If you start adding up the energy in these distributions, the energy tends to be dominated by what's down here in the low energy domain. So what fraction of energy release in flares actually goes to the non-thermal ions? We really don't know the answer to that question. Just an indication from the Earth's magnetotail data that you do see power law spectra of both electrons. So here's hot thermal stuff here around 8 kilovolts, and then you see a power law. And then for the ions over here, 14 keV for the hot thermal, and again a power law spectrum. And the important thing I want to emphasize here is that the ions carry more non-thermal energy than the electrons. And you've got to take these measurements seriously when you're talking about flares, because data where we can actually do the measurements, there's more energy in the energetic ions than there is in the energetic electrons. Okay, so what are the basic mechanisms for electron, actually, and ion energy gain during reconnection? And so in the guiding center limit is the easiest way to see this. If you have paraelectric fields, of course, which is a historical mechanism everybody focused on. But then we've got the curvature drift, which is the Fermi slingshot term. And the picture simply is that you've got a bent field line expanding at the Alphane speed, incoming particle moving at V0, it slings around and comes out at V0 plus twice Ca. So this is Fermi reflection. And then you got betatron. However, for betatron, the problem is when you have flare energy release, the magnetic field typically goes down. And if it goes down and mu is conserved, then V perp goes down. So this is actually a cooling mechanism. So betatron really is not an effective mechanism for particle acceleration in reconnection. Okay, and then if you look at what about the highest energy electrons, how do they gain energy? And if you look at, and the bottom line is that Fermi reflection dominates the energy gain for the highest energy particles. Here's a beautiful PIC simulation by Lee et al. In 2019. And here you see the energy gain from the Fermi reflection curvature drift term. And you notice that the betatron term is actually negative. And lo and behold, E parallel is also negative for the most energetic particles, although it's positive down here for low energy particles. So it's the curvature drift that drives the energy gain of the most energetic particles in reconnection. Okay, so there's been lots and lots of PIC simulations, but it's very difficult to get power law distributions out of PIC modeling. And so here is the best simulation done so far. This is Zhang et al. 2021. And they have power laws on the electrons and power laws in the protons. However, you can see the energy range here is only like 1 decade in energy. And the problem is that there's insufficient separation of macro and micro scales in the PIC modeling. If you look at the biggest PIC simulations and you go back to the Corona and you say, how big are they? They're 100 meters by 100 meters by 100 meters. They're just not big enough. And the problem with the PIC is that electrons and ions, as they gain energy, they become demagnetized in the turbulence that's in the simulation. And that's because the simulation is not big enough. So you can't get extended power laws out of PIC modeling. Okay, so we decided that what we need to do is come up with a totally new model. And the model is what we call K-global. It brings together MHD description and the particle description to model electron and ion acceleration in macro systems. And the bottom line is that all kinetic boundary layers are ordered out of the equations. And that's because particle energization dominantly does not come from boundary layers. It comes from the formation and merging of macro scale islands. That's how energy is gained. So you don't need kinetic boundary layers to model energization in macro systems. And so what happens is we have particle electrons and ions distributed on an MHD grid, and they're involved with the relativistic guiding center equations. And we induce reconnection with a hyperresistivity, which gives you an effective scale size for the system. So there's a bunch of papers already published historically on this, and the most recent one is going to come out now, which now includes we can do ions as well as electrons with this model. By the way, we should combine this with arms to produce K-arms, and we can do modeling of energetic particles in macrosystems with real solar geometry. Okay, so the first data that started coming out of K-Global was for electrons, and you can see now we've got energetic electron spectra going nearly 3 decades in energy. The energization comes because you get lots and lots of islands which merge together and drive particle energy gain. And the important feedback mechanism is through the fire hose marginal condition. You can see here you got the islands tend to be far at marginal fire hose. At marginal fire hose, the magnetic field has no tension anymore, and that feedback and kills reconnection. So fire hose condition is the critical issue that you need to include in modeling in order to do feedback on the MHD dynamics. And so all this stuff, all this energization you see here comes from the Fermi drive. Okay, we've now got ions in K-Global models, so we can do energization of both electrons and ions. So here's the results of a simulation with both electrons and protons. And here's the initial, so we're looking at the number density as a function of energy, and it's a log-log scale here. And so here's the initial distribution here, and at late time, here's the electrons, and here's the ions. And you can see from here that the ions have more energy than the electrons. Quite a bit more energy. And they extend to higher energies than the electrons. Okay, so what we've been trying to do now, so do you believe this? Do you believe that in reconnection, ions actually gain more energy than the electrons? So we've started benchmarking with with some of the Parker Solar Probe observations in an energetic heliospheric current sheet reconnection event. And this occurred on encounter number 14 for Parker Solar Probe. The spacecraft was sunward of the reconnection site. It was an enormous event. The exhaust lasted more than 6 solar radii in length. The exhaust encounter was nearly 4 hours. That's why we know it was such a big event. And there were some sunward streaming energetic protons up to 500 keV. And this is not a solar source. This is a source from the heliospheric current sheet reconnection event. The energetic protons are streaming towards the sun, not away from the sun. Okay, there's evidence for trapping of the energetic protons in the exhaust. There's evidence for active merging of magnetic islands and flux ropes in the exhaust. So all the pictures we've come up with on how particles gain energy are happening in this reconnection event. And then we've been doing direct simulations with K-Global using the ambient parameters from Parker Solar Probe data, and this reproduces the power law spectrum of protons up to 500 keV. So direct simulations of this event producing protons up to 500 keV. So here's the observations. Here's the magnetic field. You can see it's reversing here. This is the radiomagnetic field. This thing is nearly 4 hours in time across here. You can see that the velocity here, a reduction in the radial velocity due to the fact that we're in the reconnection exhaust, and the X line is away from the sun from the spacecraft. So we've got flow coming from larger radii back towards the sun, so that causes a reduction in the solar wind velocity as you're in this reconnection exhaust. And you look here and you can see the energetic particles here up to nearly 500 keV for the highest energy particles. And the energetic particles extend through the entire domain. If you look down here at earlier time, this is the pitch angle. And you can see that the pitch angles are centered around 90 degrees, and that means these are basically confined energetic particles within the reconnection exhaust when the spacecraft is in the center of the exhaust. And here's what the particle spectra look like. Here's the data from the observations. This is the protons. And of course, they also measure other ion species. Here's the helium-4 here. And then here's the direct simulation from K Global, the initial distribution. This simulation uses real parameters measured by Parker Solar Probe for the initial conditions. And you see the energetic particle spectrum going up here to around 500 keV. And the best fit to the data has a guide field which is between 0.2 and 0.3 of the ambient magnetic field. And the power law spectra pretty much agree in slope with what we see in the data. And so amazing new result coming out. By the way, this is going to come out, see, how do I go back? Yeah. This paper is going to come out hopefully fairly soon. Mahir Desai is playing the lead role in trying to analyze what's going on here. And then the recent observations then coming from Typhon's analysis of this reconnection event. And I'm not going to spend a lot of detail on this, but you can see this is in the reconnection exhaust, and you can see lots of structure. Look at here's a sharp change in structure of the magnetic field here, and Ty has analyzed this, and it turns out it's a reconnection event which is transverse to the current sheet, to the exhaust region here, the reconnection line here, and the exhaust is coming out here. This is a reconnection event, which is the merging of two flux ropes in this region here. And Ty has seen a whole bunch of these mergings going on, so that whole exhaust is dynamically reconnecting, and we believe that's the reason that it's producing all these energetic protons. Okay, so conclusions. Just what I said, and we need to build a K-arms so we can do global simulations with particle accelerations, with full feedback, so we can tell what's really going on in the sun. And we need new diagnostics. We need direct measurements of energetic ions down to tens of keV. Otherwise, we're not going to know where the energy is going in flares. Thank you.
Any questions, Spiro?
Yeah, very nice. Isn't that by its very itself?
No, it's the other way around.
The electrons have more energy than the protons.
No, if you looked at that slide I showed you, that's
oh, maybe I got it wrong then.
Here's the protons. Here's the electrons. The electrons are dropped down.
Oh, I see. Okay.
And also the core ions, 14.4 keV, and the core electrons are 8 keV.
I see. But I thought in some result that you had that the electrons actually had more energy than the protons. Maybe I'm mistaken. Maybe I misunderstood your argument. Because I was just going to argue that if you found that a lot of the energy goes into electrons, the ratio of energy in electrons versus
So my
protons.
point is that the ions, the simulations.
Oh, yeah.
The simulations are really showing now, direct simulations showing the ions are actually gaining more energy. And there's historical data also from the magnetotail in which where is most of the energy going? It's going into the enthalpy flux of the ions,
Okay.
and not the electrons.
I was just saying if you can distinguish between turbulent reconnection versus plasmoid reconnection by looking at that energy ratio.
Yeah.
Yeah, thanks. This is for a second about how
Wait a
you...
minute, I'm trying to find out who's speaking.
I'm back
Oh,
in the
okay.
back. Yeah.
Okay, yes.
Can you talk for a second about how you couple the PIC dynamics back into the MHD system to account for the energy loss from your fields?
Yeah, so it's dominantly through the, so we're doing guiding center equations, so we have a gyrotropic pressure tensor. And so the dynamics of the particles are V parallel and V perp. And then, so we produce a pressure tensor, which is got P parallel and P perp in it. And so that comes into the momentum equation And the momentum equation includes both the MHD fluid as well as the particle ions now that we've got ions into that system. So the feedback is through that pressure tensor. And that pressure tensor, as I showed in the islands really bump up against the marginal stability for the fire hose. And again, people are not maybe used to this, but when you hit the marginal fire hose condition, the magnetic field has no tension at all in it. So there's no tension, and that means the entire driving force for reconnection is completely gone. And so that's the feedback mechanism. And so the problem with doing test particles in MHD simulations is that feedback mechanism isn't there. And so you need that, and that's why we need to upgrade ARMS to K-ARMS so we can do global modeling.
Thanks to speaker again. So next speaker is Li Jen, and she will speak about current sheet formation by magnetic null stressing. This talk will not be recorded or streamed online. You see, it's a delay, and also when you're moving it.
Oh,
it
okay,
has
but
a
you don't need to do this.
Why am I talking to them?
We don't have Spiro.
Yeah,
Where's
we gotta have
Spiro?
What?
He's skipping it on purpose.
Oh my goodness, how terrible. Yeah. He is doing that, all right. That's an actual word. I'll tell you what it means at the end. Kind of depending upon how you react. Yeah. Paramount.
There he is. Now we can start. Okay.
Oh, that's okay. Well, oh, the podium, I see. Yeah, oh, yeah, for the mic. Yeah, that would help. Yeah, thank you.
So fancy.
Thanks. This is the IT expert. His name is Celsius or Fahrenheit? What is it? Kelvin. Kelvin is the name, yeah.
Yeah, he's never heard that one before, Jim.
Yeah, sorry.
Okay, so our beloved Jim is going to kick off the session on thermal non-equilibrium, and I'll give you a 5-minute warning.
Okay, thanks. Please ignore the misspelling here. I'd like to talk about some recent work that I did with Terry Kuchera and Manuel Luna. All right, so for many years, one of the real mysteries in coronal physics was how the heck you can get cold dense plasma up there in the hot tenuous corona. I'm thinking of things like prominences and coronal rain. And the existence of the cold plasma seemed to imply that the heating is reduced. But these things are very massive, and to get a lot of mass up there, that generally implies enhanced heating, because the condensations, the cold condensations, cannot form from the pre-existing hot coronal material. There's not enough of it, so you have to bring material up from below. We typically do that by evaporation, and we get evaporation from increased heating. So there were these two contradictory requirements: reduced heating for the cold temperatures and enhanced heating for all the mass. So what's going on? Well, it took a very smart, very creative person to figure it out. Spiro said, you know, we can have our cake and eat it too. We don't have to have the heating uniform in the coronal loop, which is what people were assuming. Let's put a lot of heating down low near the legs, near the foot points in the legs, and very little heating up at the apex at the top. So the strong heating down by the legs will drive this evaporation. So we'll get material flowing up into the loop. But of course, it doesn't stay in the lower legs. It fills the entire loop. So we build up density up at the top. Density gets larger and larger. And radiation varies as density squared. So there's a lot of strong radiation, but the heating up there is very small. So there's an excess of cooling, and we get a thermal runaway, and we form the condensation. And then this continued evaporation feeds mass into that condensation. Now, if the field line has a dip, concave upward, then that condensation can settle in the bottom of the dip and grow, and that's a prominence. If the field line is a traditional curved loop, concave downward, the condensation grows for a while, but then it slides down one of the legs, and then the process repeats. Another condensation forms in a well-known cycle. All right, so this is a process known as thermal non-equilibrium. And I'm delighted to say that I was a co-author of the very first paper that presented this result back in 1991. What is that? 33 years ago? Time flies when you're having fun, and we certainly have been having a lot of fun, haven't we? But I was going to say to you guys that I played only a very minimal role in this. I mean, the idea was all Spiro's. I simply ran the loop model to verify that it was correct. But I was discussing after the banquet yesterday with Spiro and his family, just having a chat, and we talked about Brian's drawing that he made on my board in my Stanford office. And Spiro said, hey, Jim, remember that couch you had in your office? I remember sitting on that couch talking about prominences with you, and that's when I got the idea about thermal non-equilibrium. So in fact, I did play a very major role because that couch was my personal couch that I had brought from home. So I'm going to take a lot of credit for this. All right. I quote here a second paper, Spiro and Judy. As far as I know, that's the first paper to actually use the term thermal non-equilibrium, TNE. I don't know. Let me know if you find it. But did it? Okay, maybe I missed it. Anyways, well, the first paper, it really kicked off a whole new area of research. Many people started working on this, and in fact, we've had a bit of a renaissance in recent years. Many people are working on TNE again. All right. Now, most of the TNE work up until recently has involved steady heating. You don't have any time dependence at all. You just have steady heating that's concentrated more at the lower altitudes than at the higher altitudes. And that gives you this phenomenon that I'm talking about. I should point out that it is not a thermal instability. It's a thermal non-equilibrium, which is different. There's a debate going on in the community now about, well, maybe it really is a thermal instability. I have very strong feelings about that, and we can talk about it later if you want. But it's really a thermal runaway, not a thermal instability. Okay, but that's with steady heating, but in reality, the heating is not steady. It's very impulsive. Whether it's due to reconnection or waves, the heating in the corona is impulsive. Now, if these impulses occur very rapidly, we call that high-frequency nanoflare heating. Well, it's roughly equivalent to steady heating. But if the nanoflares are separated in time at low frequency, that's quite different. So the question came up, can you get these condensations forming with impulsive heating? And a number of studies showed that indeed you can. Spiro and Judy were authors of one of them. And they showed that there is some kind of relationship between condensation formation and the frequency of the nanoflares and the height of the nanoflares. But no one had done a real systematic, comprehensive study, so that's what we decided to do. So we addressed the question, how does condensation formation depend on the frequency and the height of the nanoflares? And we considered 3 different scenarios. First, we looked at different frequencies with nanoflares occurring at a fixed height. Then we looked at nanoflares occurring at different heights, but with a fixed frequency. And then we looked at a combination of random frequency and random height. So that's what I want to talk about. Here are the details of the simulation. I'm going to skip over this. We use the Argos code to run these simulations. All right, let's first take a look at the case of nanoflares occurring at a fixed height with a regular cadence. They occur every 1,000 seconds. And we're going to have nanoflares occurring simultaneously in the two legs at the same time. So boom, boom, boom. And let's see what happens. So if you could run the movie, please. Oh, before you, well, you go ahead and run the movie. What I'm showing here, these plots, the top one is temperature as a function of position along the loop. Okay? So here's the left chromosphere, the transition region, the corona, the right transition region, and the right chromosphere. And in the middle, it's velocity, and the bottom is density. And you see the nanoflares going off. You get these temperature pulses down in the legs occurring at the same time. You form these features here, a temperature dip and a corresponding density spike. That's the condensation. Come on, form one, you buggers. You've seen them. And there, it sits there for a while. Then asymmetries, numerical asymmetries in this case, cause it to fall down one side or the other. All right, good. So we looked at many different cases with different frequencies. That last one was for a 1,000-second delay. Here we have, just concentrate please on the, there we are. The blue curve here, this is for these nanoflares occurring simultaneously in both legs, also called those symmetric. Here's the case that I showed. For delays less than 1,000 seconds, and this is a plot of the rate of condensation formation. So number of condensations per 100,000 seconds. That's basically a day. So number of condensations per day as a function of the time delay. So for 1,000 seconds and shorter, they all have about the same condensation rate. So this is pretty similar to what you get with perfectly steady heating. As the delay gets longer and longer, the rate of condensation formation decreases, and eventually you get to a point where you have no condensations at all. So somewhere between 1,500 seconds and 2,000, there's a critical delay beyond which you do not get condensations. All right, let's look at a different case here. Now we have nanoflares alternating between legs. Again, a regular cadence, but it's left, right, left, right. And this is 1,000 seconds again, all at a fixed height. So run the movie, please. Let's see if we get any nanoflares. Run it if you would, please, the movie. They're not going? You have to get the, whatever, the control bar. If you click on the plot, it should show up.
Yeah, it's not, it looks like there's.
Can you click on it to the right, maybe? I think that's what I do on my computer.
Oh, I see, yeah.
There, okay. Thanks. Here we go. You see the nanoflares occurring, alternating left and then right. But no condensations form in this case. Well, we looked at a number of other cases with different delays. This now is the black curve here. And in fact, we do find that condensations can occur. All these have condensations going on. These don't. Again, there's a critical delay. In this case, it's at a shorter delay. The critical delay is somewhere between 1,000 seconds and whatever this is, 950. This is the case we were just looking at. So similar to the symmetric, simultaneous nanoflares, except that it's more difficult to form condensations. And that's because, well, the way this whole thing works is, with steady heating, you have the evaporation happen continuously. So material is flowing up all the time in a steady fashion. You're building up density up at the top. With impulsive heating, you have a burst of evaporation, and then you have draining, and a burst of evaporation and draining. And if the nanoflares are occurring at a rapid enough frequency, with each cycle, you attain a higher density, and eventually the density that you get is so high that the cooling rate is shorter, the cooling time, rather, is shorter than the draining time, and then you get that thermal runaway and you form the condensation. Now, the buildup of density in this cyclical manner happens more efficiently if the nanoflares are occurring at both legs at the same time, because the evaporation fronts are coming up and colliding up at the top. But if you have alternating nanoflares, you send up an evaporation front on one side, it goes over the top, starts going down the other leg, and then a nanoflare occurs there, and it hits it, and then it comes up, and there's still an interaction of evaporating fronts, but it's not as efficient as when you have the nanoflares occurring at the same time in both legs. So that's why the critical delay in this alternating case is smaller than for the simultaneous case. Also, you have this very interesting thing here. At these time delays, there are no nanoflares. I mean, why would that be? Well, it's actually easy to understand. In that case, there's a very nice resonance. So a nanoflare goes off, sends the evaporation front over the loop, and just as it's getting to the other foot point, you have a nanoflare there, which sends it back. So you have this nice organized sloshing back and forth and back and forth, and you're not building up the density enough to get you the thermal runaway. All right. All right, so now let's take a look at random delays. Again, nanoflares occurring at a fixed height, and the height here is something like 7,000 kilometers above the top of the chromosphere. But the delays are random. We select our nanoflares from a power law energy distribution with a slope of minus 2.4, and there's a reason for that. There's a corresponding power law distribution in the delay. So I can, I think, just advance the movie this time and it will work. Let's see. There it goes. So here you see in the temperature profile at the top, the nanoflares going off in kind of crazy ways. And in fact, you do get condensations forming, but note their erratic behavior. Everyone. Here, look at this thing. It's going to kind of wiggle back and forth, left and right, and finally go to the edge. It turns out observations show that very same behavior with coronal rain. So what's going on here is you have the condensation form, an nanoflare goes off, it creates a pressure on that side which pushes the condensation to the other leg, but then a nanoflare goes off at that leg and pushes it back, and because these nanoflares are random in time and in energy, you get the crazy behavior. All right. Okay, so here now I've added these to my plot here. It's the green curve. Here's the case I just showed. And what you find is the rate of condensation formation is smaller with randomized nanoflares. So randomizing things, which is more realistic, reduces the efficiency of producing condensations. However, you do find that at very long delays, and these are random delays in green, so what I plot here is the average delay for the simulation. But you can get cases way out here where the average delay is beyond the critical delay given by the other cases, and still you get a condensation. Thanks, Leda. And that's because in any random sequence, you're going to have some period of time where things are going to be happening differently and more frequently. All right, so I got to push along here. As I mentioned, we also looked at different heights for a fixed nanoflare frequency, but different heights. We find once again that there is a critical value. It's a critical height beyond which you do not get nanoflares. Oops. And that's over here. And that's different for the symmetric case versus the alternating case. We also looked at random. And randomizing the heights also tends to diminish the condensation rate. But the effect is not as big as randomization in frequency. Okay, this is kind of neat. This is random delay and random height. The plot at the left, you saw yesterday someone show a plot similar to this, but it was rotated 90 degrees. On the horizontal axis is position along the loop. So yellow, and this is density. So yellow is high density, and green and blue is low density. So here's a chromosphere, and here's the corona. And the vertical axis is time. So each horizontal slice corresponds to a single time. Okay? And the crosses here, the red crosses, are where the nanoflares go off, both in space and time. And you can see they're random in both. And here you find that a condensation forms. It's the bright yellow, that's high density up in the corona, and it moves in a kind of a crazy way, like I showed before. Ignore the breaks here, they're artificial. So this is one example. On the right, I show the results for many different cases. Color is the condensation rate, condensations per day. On the horizontal axis, I have the height of the condensation, which is increasing, going from left to right. Then going from bottom to top is the delay, average delay between nanoflares. It's increasing. So the bright colors here, the red and yellow, that means a rapid formation rate. The dark colors mean condensations do not form readily. And as you'd expect, as you increase the height of the nanoflares, the rate decreases. As you increase the delay, the rate increases. But there's not a real sharp cutoff here. You might have thought there'd be some kind of a diagonal line where there'd be a sharp cutoff. There isn't. You can be way out here in this part of the plot and still get the occasional rare condensation. And that's, again, because of the randomness in the input parameters. In any random sequence, like I said, you're going to have some period of time where things behave differently. All right, so concluding then, condensations can form with nanoflare heating. We knew that before. The condensation rate decreases with longer nanoflare delay, in other words, lower frequency nanoflare heating, and with greater nanoflare height. For regular cadence and fixed height nanoflares, there exists both a critical delay and a critical height beyond which condensations do not occur. Randomness tends to diminish the condensation rate, especially randomness in time. You do get unusual trajectories, and those, as I say, have been observed. And they're a very good indication of the nanoflare heating. You can infer from the motion of these coronal rain condensations what the heating is doing. And so for more details, please see our paper that was recently accepted. So thanks very much.
Can you rule out wave heating based on the trajectories? Because I would think you would need a fair amount of momentum to cause the condensations to move up. And with wave heating, you could easily get condensations, but would it be possible to get these unusual trajectories of up and down?
It all depends on the magnitude of the heating. If you can get wave heating to produce a lot of energy release in a short period of time, therefore high pressure, you could do it. But I think wave heating models don't tend to give you that kind of behavior. And I would point out that I think there really is a consensus in the community that active regions, where we tend to see these things, are heated primarily by reconnection events. There's some wave heating. Wave heating is, of course, extremely important and dominant in open regions. In quiet sun, we don't really know which is more important, reconnection heating or wave heating. But in active regions, it's primarily reconnection heating.
Here's a question from a newborn solar physicist.
Welcome to the club.
Can nanoflares occur in the foot region of erupted flux rope? And if they can, perhaps what you were showing us would be a possibility for those cold, dense helium plus to get out.
Nanoflares certainly can occur anywhere. Would they tend to occur readily in erupting flux ropes? I'm not sure. We're working very hard on the question of onset of reconnection. When does a nanoflare go? Spiro made the point that for understanding big explosive phenomena, the reconnection has to remain dormant as stresses build and then turn on. That's also true for nanoflares. Well, I mean, not initially. If it's a flux rope, it's a big, long flux rope. But yeah, in general, I agree with Spiro. I would be less inclined to think nanoflares would be common in erupting flux ropes.
So, Jim, you showed very interesting. You showed at some point a power law of energy injection, and I was wondering whether you have done some statistics of the energy released based on this energy injection and how the statistics of the output relate to the statistics of the input. That would be interesting for a random frequency and a random height.
If I understand correctly, my answer would be we're working very hard at understanding really what is the power law distribution of energy of events. We're running what we like to call multi-strand MHD models, where we model just a portion of an active region. You know, the old Parker idea. Yeah. You have a uniform field, and we drive it with random motions, and so we have a limited number of current sheets in our domain so that we can resolve them sort of okay, and we're studying the energy release of those. And we don't yet have the results, at least not in the form I'd like to discuss. But the 2.4 came from a cellular automaton model they did with Marcelo Lopez Fuentes.
Right. Yeah, this would be very interesting because it would show the level of storage and release you managed to achieve in this situation.
Oh yeah, that's a key question, and we're working on that very, very hard.
Last question.
So in the model you've shown, the condensations are moving down field lines down into the chromosphere. On the other hand, you know, I've watched a lot of these movies of coronal rain, and I get a sense that they're falling down, but not always along field lines. So I'm wondering, isn't it possible that Raleigh-Taylor could be playing a role, and then the condensations could just fall basically directly down and not just along field lines?
I doubt it very much. Now, there are different kinds of coronal rain. There's coronal rain associated with flares, and sometimes you see prominence erupting, and some of the prominence material then falls down. The coronal rain I'm more interested in, at least at the moment, is coronal rain in non-flaring active regions. It's happening all the time. And it's always, in that case, they follow nice curved trajectories that you can be quite confident, I think, are field lines. I don't know, do you really think, I would think you wouldn't get Raleigh-Taylor instability that would give you much cross-field motion, like trotting. Yeah, but is this, well, is it really, well, in this picture, is the plasma actually slipping through the field lines, or are the field lines moving? It's slipping through the field lines. Yeah. I don't know.
Sounds like a coffee break question.
Sorry?
Sounds like a coffee break discussion.
Coffee break discussion, yeah.
Let's thank Jim.
All right, thanks.
Okay, our next speaker is Wei Lu.
I'm probably the work with Spiro, directly or indirectly. Spiro and I, we had dinner together a few times. He's a friend of my professor. We went to the same graduate school, but that was 30 years apart. Other than that, I had nothing to do with Spiro. But think about it, really? And I thought one of my first projects as a student, it turned out actually was modeling of breakouts, variants. So I was I was in the shadow of Spiro 30 years later. So another thing, I moved on to work on high energy emission from flares, working on RESI, and I thought, well, Spiro never worked on hard X-rays. Fair enough. They worked with Peter back in the 70s for all of those features we've discovered with RESI and some of those chromospheric evaporation features. It's all in Spiro's work in his thesis. Boy. And I move on to some other things in more recent decades. Also something, we went into this business by some accident. I was just intrigued by those condensation and coronal ring in very weird geometry, which I'll show some examples. I thought, okay, Spiro didn't work on this. Boy, sure enough, I was working on, because there was very interesting null point geometry. It was very fascinating. And guess what? With the help of Ebony Mason, Spiro figured it out. So I would say, well, my entire career, even though I had nothing to do with Spiro, but every step of it has I was influenced by Spiro's inspiration. So thank you, Spiro. All right, so here comes my talk. So I'm going to cover a bit on the observational side of the coronal ring and prominence, and follow up on the discussion Jim had just a moment ago. So I'll go over prominence and coronal ring, and the driver of this is but the where and when coronal ring condensation forms, and I'll show some examples, and then I'll boil down to the question why condensation will happen in those locations, namely null points or QSL preferentially. And before we get there, let me step back a little bit, look at why such things are important. And let's look at the mass budget. The Sun has a mass of 10 to the 33 gram, and the corona is about 10 to the 17. So a prominence we know is very heavy, very dense. A large-scale prominence, a single prominence in the corona can take a mass of roughly about 10% of the entire corona. So namely, about 10 prominence can take the mass of the entire corona. And then prominence is oftentimes the exhibit active drainage or mass flow. So the mass is being constantly drained, and on such typical speed of about 10 kilometers per second, a big prominence can drain the mass equivalent to the entire corona. So basically, if you look at prominence as a sink of the entire corona replenishes itself in one day. So it's important. The prominence mass is super important. And so now let's look at some of the aspects of another thing, because the mass of those cold condensed mass plays also an important role in terms of the so-called chromosphere mass cycle. Namely, as we've been intrigued by the mystery of how corona gets heat, and by the same token, we need to understand how the corona gets cold, right? Because those cold plasma sits in the corona, and there's mass going up by heating, but also comes down by cooling. And this is a typical prominence movie by Tom Berger. You see those meandering flows and active drainage of the prominence. So this is what we see from prominence. And if you look at coronal ring, this is what Jim referred to as typical coronal ring. You see they have very organized geometry. They follow on those like loops. They're definitely loops. There's a flare, but also beyond the flare time, there's active coronal ring happening in active regions. So now why there's some difference between these two phenomena, prominence versus coronal ring, in terms of their geometry, morphology, and timescales, things like that. There's one thing I'd like to just step back and look at physics. And so the corona has so-called thermal non-equilibrium or instability, whatever you call. And basically, this is a radiative loss curve of the corona as a function of temperature. So somewhere between the range, between the range of 10 to the 5, 10 to the 7 degree, the loss curve is even decreasing function of temperatures. Namely, the higher temperature you go, you actually lose more energy. So that's how it goes into a runaway situation. However, we also know the corona is very hot. At the 10 to the 6 degree, conductive heating is very efficient. Anything gets cold can be warmed up very quickly. So because assume basically it's like you put some snowflakes in the oven. Locally it's very cold, but the environment is so hot. However, the corona we know is magnetized. Magnetic field plays a crucial role because thermal conduction cannot go through across field line, but can only go along field lines. So the magnetic field basically works as a regulator to regulate thermal conduction, how thermal conduction works, or then that helps condensation to form in certain locations. So that's what I'm going to emphasize in this talk. Geometry matters. So and now, so let's move on to some questions we can, what I'm trying to convince you, or some, not really answers, but some examples. So one thing I would like to emphasize here is the singularity, namely those locations where we have weird magnetic geometry that can facilitate condensation. So, a few examples. I'll show 3 examples, one from an active region, another one from the sort of neighborhood of several active regions, another one from very high altitude. So this was a neighborhood active region where you see that in yellow is the 171 material showing the hot corona, and the red is the 304 material, very cold. So basically what happened, what you saw, the movie, I'm trying to replay the movie, could you, okay. So there's a prominence sitting there, eruption blows up everything, so the corona got left over with nothing, and then something happened. Over hours, you see some red cold material reappeared on its own, And if we take so-called cuts over this region and in 2 channels and do a J-map, what you see, this is a sequence of the movie we just saw. And what you see here is horizontal is the time, vertical is height. What you see in the lower portion is you have some material, the prominence sitting there, eruption blowed up everything for a long time, 7-some hours. There was no cold material sitting there. But eventually, some material reappeared at low temperatures. Before that, you see some signatures at the intermediate temperature, slightly warmer than the cold material, basically being progressively forming. And if you look at other channels, from AIA, from hot to cold channels, what you see here is a progressive delay from high temperature to low temperature channels, and you can map out some sort of cooling sequence and make some hypothetical calculation, say if this is radiation dominant, and you can find some sort of cooling timescales. That seems to be in line with some of those simple calculations. So that seems we're understood, but if you look closely, it's not happening in some random locations. If you look at the middle panel here, where the circle highlights is where the initial condensation happens, where you see some sort of cusp features or double Y geometry. Here's the cusp, sorry. Sorry about that. So that's indication where that's potentially a null point location where some, and also recollection could be happening because we see some signatures. So therefore, we moved on to look at some of the geometry. Sorry about this. And so we tried to do extrapolation to figure out the field line geometry in that neighborhood, and we found some potentially null point. This is a 3D rendering of that region where somewhere in this neighborhood where the cusp located is where the initial condensation happens. There's potentially a null point. So now we'll move on to another example. This is region sitting a bit higher. Again, the same color scheme. Yellow is the 171 cool, warm coronal loops. Red is those cold plasma. Here I want to bring your attention to this region where you see some very chaotic of meandering flow versus the plasma, the flow under this region where you see well-organized flow along loops, the typical coronal ring you see. But up here in this region is very meandering. It looks like nothing like low beta plasma to me. And if you do similar thing, just take out the cold plasma, just look at the warmer plasma, you see all sorts of geometry, some cusps, Y-shaped features. So that's another indication to see there's another double Y indication, probably reconnection is happening. So again, we did extrapolation from the field line, from the magnetogram. We identify some null points in that neighborhood. And some examples of those null points. And if we look at step back further out from the potential field extrapolation of on the global scale, we found some features like a pseudo-streamer type of geometry as shown here, which was very similar to what Emily Mason did with Spiro. So we came back to the same conclusion, looks like. One more example before we get to the end. So here's the region we look at very high latitude. For most of those polar crown regions, we have those dips in 171, those large loops, like transequatorial loops. But at those lower portion of those loops, you see constant or episodic coronal ring formed, or prominence. We call those like funnel prominence is another term. But basically, at those locations, you have cold material forming and constantly flow downward and drained. And so on the right-hand side is the same feature at different time of the cycle. And if you look at closely at that region, those location, at similar location and latitudes, similar features persisted for over almost a year. But of course on and off in different cycles or different episodes, but similar features being there and with episodic coronal ring happening in those cusp locations. And we looked closely to the McLeod, and we found there are some signatures showing multipolar geometry where you have this X location, that's where presumably where we have this condensation. And then those locations where have potentially current sheets, null points or QSL, and you end up with some cold material. So the thing we learned here is they're not random. No. In active regions, you have constant coronal ring, but outside active regions, they sort of pick up some locations to occur. And those locations tend to be at somewhere in those weird geometry locations. So again, back to the physics we showed earlier, the key is the magnetic field. So magnetic field makes a big difference here by regulating how you get heat there or regulate where heat goes, right? So basically, in some locations where your heat connection, thermal connection, even though very efficient at 10 to the 6 degree, with the fifth half power of temperature, you still need the magnetic field to do the job to regulate condensation. So some random ideas, we have not done any serious modeling, but some random ideas why would those condensation happen in those locations. Some examples, current sheets. There were some ideas about current sheets could be, the field in there could be meandering, not regular field lines as you would assume in regular, like outside current sheets. So those meandering field could also suppress thermal conduction because you know thermal conduction can only go along field lines. And if you have meandering fields in such situations, like what Ben Chandra worked on in galactic or even intergalactic time space scales, they can suppress thermal conduction quite a bit. So that could provide some sort of condition in favor of condensation to happen in current sheets. And there were some other interesting things we found from flares. During flares, we have those so-called superarcade downflows in current sheets where the so-called SATs. Those are indication with some plasmoids formed in the reconnection current sheets in the flare. And those conditions can somehow, potentially, probably, in favor of condensation happen because, first of all, when you have plasmoids, they produce higher density. So the high density can serve as a seed population for condensation to happen because radiativity loss goes as density squared. So the higher density, you lose energy faster by radiation. So that could serve as an initial seed population. And some other ideas, you name it. So one example, I just want to go through this example a little bit at the bottom. This is sort of hypothetical illustration. For example, if you have this thin field lines are field lines, and well, this circle is their density contour. So if you have a dense blob forming there, and the weight can be important, and that would deform the field. So the field line would drag down, and then at some point, you would drag the field line downward, and then on the top portion of this will form a potentially like a teardrop kind of geometry, and then you could end up with reconnection. And then in this two-dimensional geometry, you end up with closed field. Then what happens when you have closed field? Thermal conduction cannot go in or out. The only thing for that part of the plasma is going to lose energy by radiation. Of course, waves is another thing here. But by radiation, it can cool the plasma to crazy low temperatures. So then the whole thing can go into in a positive feedback and produce very cold plasma. So those are ideas, and I'd like to end my talk with another thing just popped up not too long ago. That's how Titov, Slava Titov brought to my attention this interesting idea. There was an idea about those cold, dense current sheets in the 70s, and there was a paper by Spassky and Samov, and they argued there could be a condensation mode, and somewhere in this calculation, you end up with high density and low temperature current sheets, and that's what we were thinking of. And then, on another side of this coin is they could end up with the thermal trigger of the flare if the loss is not compensated by or otherwise, if the energy release is much higher than the loss, you end up with a flare. With condensation and chromospheric evaporation, all of those, again, Spiro figured out back in the 70s. So I'd like to just put this slide here for just a summary. There are so many things in our field, whether it's those null points and those weird geometry. It's so fascinating. I had nothing to do with those because for my entire career. But somehow I got sucked into this because you cannot stay away from this. And those geometries that tend to be the location where condensation happen, and we're trying to figure out why and what sort of condition there and reconnection could be facilitating condensation or some feedback, vice versa. So those are ideas we come up with, and we're on some. Have a mission to finish all of those and open for questions here. Thank you.
Derive some expressions giving the conditions for thermal non-equilibrium, and an expanding loop geometry promotes condensation formation. So when you have a null point topology, you have expanding flux tubes. So it could simply be that.
Oh, thanks, Jim. Yeah, we can talk tomorrow about that.
Spiro, did you have a comment?
I never single-handedly solved anything. So everything I did was in partnership with my colleagues. So I'm looking forward to working with you, Wei, on solving these problems.
Yep, look forward to it. Thanks, Spiro.
Thank you. Our next speaker is Roger Scott.
Yeah, got the pointer. Let's see, does it? Got it. Okay, and then can I cycle slides? I can cycle slides. Okay, I'm going to do something. I'm going to do something a little unorthodox and jump to the very end. Here we go. Okay. Before I started working on 1D simulations of the solar wind, I was doing 3D MHD modeling of global coronal fields, and this was very close to Spiro's wheelhouse. We were thinking about topology and the S-web, and I ended up having to read a lot of Spiro's papers. I was invited to Goddard to learn how to use ARMS, and shortly after I got there, we got in an argument about drawing pictures of null points in a whiteboard. I think that was within about 20 minutes. And I spent the entire rest of that trip tweaking control files in order to get an initial condition that would prove my point. And once I'd done it, I walked back down the hall to show Spiro this result. And he looked at it and he said, well, if you really think about it, it was obvious that it would have to be that way. Then I ended up moving into this 1D wind modeling, which I thought was further outside of Spiro's wheelhouse. And then I discovered that you could get TNE there. And it turned out that I was actually back in Spiro's wheelhouse. And then I had to read some more of his papers. But if you think about it, to go back to another Spiroism, if you really think about it, it's okay, because anyone who's covered as much ground in their career as Spiro has is bound to have left some stones unturned. And if you're looking for ideas, you could do worse than to read his old papers and pick up where he left off. Okay, so let's talk about what I am here to talk about, which is simulation of thermal non-equilibrium in the solar wind. In my title here, I have non-equilibrium spelled one word with a lowercase e, which is in your title from the role of asymmetry. But then the other title is the other way, so now I'm confused and I don't know how to spell it. Okay, well, so then in this paper, I'll leave it this way. Okay. So I wasted a little of your time on my anecdote, so I won't belabor the history of this, but cold condensations in the corona have been observed since the 70s. The dynamics of that and the sort of thermal runaway were observed thereafter, and we now think of this as coronal rain in cases where you have a convex loop and the condensate drains towards the foot point. And here we've got some nice figures from Mason et al. 2019 paper showing coronal rain forming near a coronal null point. And there's some indication that the rain may actually form outside of the separatrix surface, potentially adjacent to the spine line. So this could be in the open field region. And that's something that's not typically explored in the nice 1D models that we have with thermal conduction. There are some 3D models that potentially show coronal rain in field lines that are nominally open, but the domain there is so compact that you can't really say it's embedded in the wind. You know, what is an open field line if it just intersects the top of your box? So we wanted to explore, well, this came out kind of accidentally, but now I'm here to explore how this happens in a wind model. So the qualitative picture, again, is that we've got some loop, or in my case, it'll be an open field line, where you have a highly stratified heating, and you end up with a strong radiative loss function somewhere up in the region where you don't have sufficient direct heating, and you don't have enough thermal conduction to support those radiative losses, and so you can get a catastrophic cooling. Okay, so I'm going to spend a minute to describe the structure of a steady state wind solution, and then I'm going to talk a minute about how that changes when we apply strong base heating. So in this top panel, okay, so height increases on the horizontal axis. We're roughly in the range solar surface up to about 10 our sun. The solar surface is here, this vertical, and I've indicated that by these marks here. So S naught is my solar surface. SN is one density scale height, and SP is one pressure scale height. And in the ambient case, the temperature rises into the wind. The density falls off pretty monotonically. The velocity rises monotonically. Pressure falls off. You have a peak in the heating per particle at about 1 R sun, which is my global length scale for my large scale heating function. And of course, then you also have a peak in the conductive cooling at that height, which is transporting energy down to the base of the corona to supply, through conductive heating, the radiative losses. When I then add on a foot point heating mechanism that has roughly the same total energy as the global heating mechanism, then you get a secondary peak in the heating per particle. And now you don't need conductive heating to support radiative losses. Instead, you need conductive cooling to get rid of that extra heat that you're stuffing in there. And that causes the temperature profile at the top of your base heating. This decays much more fastly with height. So where that falls away, where your base heating rate gives way to the global heating rate, you start to get a flattening in the temperature profile. Okay, so if I keep turning that base heating function up, that flattening in the temperature profile eventually becomes a local concavity. Now the temperature is decreasing with height, and the heat flux is completely reversed. As a consequence of that, you are now transporting heat up from the base heating rate, and it needs to be dissipated some way. It needs to be radiated away, and so you get an increase in the density where that base heating function gives way. That large density supports a large radiative cooling, large radiative cooling there due to this bump in the density here. And in order to supply that upward heat flux, of course, your temperature has to be decreasing with height, and so the temperature within this thermal minimum starts getting lower and lower. You're pooling heat into what I call a heat sink here so that it can be radiated away in order to expel all this additional base heating that I'm just shoving into this thing. And this case here, alpha is a parameter that tells me the ratio of the total integrated foot point heating to the total integrated global heating. And when this hits about 3.5, we no longer have a steady state solution. So this is the last marginally stable steady state solution. And if I push it just a little bit more, okay, here I have alpha equals 3.45. This is marginally stable. I push on it just a little bit more, and lo and behold, you get a condensate, and then we start going into T&E cycles. So hereafter, this is a limit cycle of condensation, evaporation, settling, new condensation. And again, I'll remind you, this is in a radial solar wind, right? Okay, here I'm just plotting the density. You can see that when the temperature falls through the floor, the density rises and you get this falling condensate. And here is the mass flux so that you can see the condensate falls and then that mass is ejected back again. Then there's a settling phase and then that repeats. I won't spend too much time on this slide, but just to say, if you have an outward solar wind, there's a velocity and there's an enthalpy flux associated with that, and it's been discussed how the enthalpy flux can be a source of heat that could potentially suppress this. So I would not have expected T&E in the solar wind based on that argument. But here what I've done is looked in the Lagrangian frame of the fluid. So I'm just thinking a fluid parcel as it migrates through this local temperature minimum is losing energy at a rate, heating plus radiation plus thermal conduction. It has an internal energy that is basically the pressure. I can construct a time scale from that. I compare that time scale to the transit time across my little thermal structure. And if I lose all of my heat in less time than it takes to cross the structure, a steady state is inadmissible. It's a counterfactual to a steady state. How could there be a steady state if in that time you lost more energy than you started with? So this is a sort of a little test of how do you know when the enthalpy flux is not providing enough heat to maintain your losses. It's because in the plasma's frame, it loses its energy before it gets out of the trap, basically. And so I've plotted this, what I call the cooling factor, and you can see the cooling factor goes above 1 when we start to fall into this thermal runaway solution. Of course, there's a non-trivial interaction here with the temperature at which the radiative loss function becomes a decreasing function of temperature. I don't want to spend too much time on that. Okay, so I'm going to break down 4 subcycles within this process because each one of them can be motivated by a different physical process. So let's suppose that we've already got a condensate formed. That's this temperature depression with a local density enhancement. That propagates down towards the solar surface. The time scale for that is the ballistic freefall time. You can work it out on an envelope and you find out that you're about a factor of 4 too slow. There's a plug of plasma in front of this thing as it falls towards the solar surface that gives it a back pressure, so it doesn't quite free fall, but it's pretty close. This phase ends when the condensate has bashed into the chromosphere, and then I'm now showing the first line plot of the next time when the material is now being ablated back into the corona. Okay, so that's a preview to the ablation phase. So the condensate, when it hits the chromosphere, goes into hydrostatic equilibrium with the atmosphere that was already there. That material extends the exponentially decaying atmospheric profile, so the material at the top of the new chromosphere, if you like, is underdense. You add a lot of heat to an underdense plasma and you immediately get a huge outward enthalpy flux. So it just starts evaporating like crazy. That evaporation quickly replenishes all the material back into the corona. That's transported out by this pressure front that travels out at the acoustic speed. And then once you have all the material that was condensed onto the chromosphere ablated back into the corona, the mass flux starts to fall away as there's a signal that the chromosphere says, I don't need to ablate all this material anymore, so there's a pressure depression. That pressure wave propagates out, and at about 1 pressure scale height, it starts to turn off the outflow. So now all the material's back into the corona, but it hasn't yet reached an equilibrium state. Okay, then there's a relaxation process. Basically, this is the momentum equation seeking a force balance solution. And the time scale for this is basically just the fluid transit time from the surface up to 1 pressure scale height, because the fluid is trying to rearrange the density so that the gravitational force can be in balance with the pressure force. And then the last phase of this cycle is the interesting part. This is the momentum equation has roughly come back into force balance. You're very near to the last stable adjacent steady state solution. But recall, given the heating that we had, it wasn't actually a steady state. The energy equation was unstable to this thermal runaway. And so you get a slow increase in density and decrease in the temperature within what I call this heat sink. And then eventually you get a new condensate formation. You get a velocity reversal above the condensate. You get an upflow into the condensate from below. This is the material accumulating rapidly there. And then now this is the last time slice of the condensation phase. This cold, dense plug will now fall back to the chromosphere through the ballistic process again in the next cycle. I have spent some time trying to work out the time scale for this runaway. I use the assumption that I can treat this as a thermal instability. We can talk about whether that's a good idea or not. Okay, time scale for this. The marginal case has a very long time scale, 25 hours roughly for a cycle. This is all the long, slow condensation. This is the slow time that it takes for the thermal runaway to go. As soon as I start turning up the heating, these times get much, much shorter, and they appear to asymptote at about 3 hours. It appears that the condensation and the relaxation go to effectively 0 time, and all the time is spent on the ballistic free fall and the subsequent ablation. Here's a synthetic image to try to come up with a heliospheric signature. This is looking above the condensation from 2.5 to 15 R sun. Time on the vertical axis and space on the horizontal. This is temperature. This is density times area. So this is the linear mass density in your per length in your flux tube. And then here I've taken the spatial average of that and plotted it on a log scale against a mean value. And so you can see that these features propagate out into the heliosphere at about 350 kilometers per second. That's the acoustic speed plus the flow speed. So this was an attempt to compare to Weil et al. Periodic density enhancements. These are a different structure, but I have ideas that maybe they could be kind of the same structure. I'll skip over the ionization profiles, but just to say that different atomic species respond differently to the onset of a non-equilibrium state. It's not intuitive that they all do the same thing. So in summary, thermal non-equilibrium and condensation formation is agnostic to magnetic connectivity. It doesn't have to be a closed field line. What matters is the thermodynamics. If you can manifest those thermodynamics on a closed field versus an open field, that's what gets you there. And I think this could be important. Here I've got a fairly artificial spherically symmetric geometry and a prescribed heating function. But if you have a geometry that feeds back into the heating mechanism, if you have wave turbulent deposition and the wave energy flux depends on the expansion factor, and maybe you get a natural stratification of the heating near a null point or something, I think you could get a very similar mechanism here. And it's my hope that this could be potentially a way to explain fluctuations and sort of emergent quasi-periodic behavior in the solar wind. And there appears to be a typo on this slide. I don't know how that happened. Let's see, where is it? There it is. The strangest thing. What? You're kidding. All right, so thank you for your time.
Questions?
There's a lot of interest now on solar wind formation due to basically interchange reconnection through small bipoles. And it could very well be that a process like that does release its energy very low down. And so perhaps signatures or evidence of condensations along open fuel lines may be a way to confirm that process. So it'd be worthwhile to think about how, suppose you couple the MHD calculations with your thermal non-equilibrium calculations, see if we can distinguish between the interchange reconnection mechanism, giving you as a driver the solar wind, versus, the old ideas about just alphane waves due to the the P-mode stuff.
Yeah, I totally agree. I mean, I've tried to present this in a way that is agnostic to the details of how you get the heating there, because I don't know how to get the heating there. I prescribe the heating in my model. But, you know, null point, reconnection low in the corona could be a source of very stratified heating. Wave turbulent dissipation of non-guided waves, like compressible MHD waves banging around back down in the low corona, could be a source of highly stratified heating. I also want to build in wave turbulent dissipation into the hydrad code and see if that we could get some interesting feedback from the magnetic geometry on where the heat is deposited, just through parameterization of the flux tube profile.
Are there any hints of these condensations in EUV or white light images?
Yes and no. I mean, again, you know, looking at, like, for instance, the observations of condensations near coronal null points, I think if you allow for the extension of this model to those geometries, I think that could be a potential observation there. The more direct comparison would probably be to plumes. You know, a lot of people have modeled plumes with similarly stratified heating profiles. I don't know of a host of observations showing periodic downflows at the base of plumes, but those are hard to visualize structures anyway.
Let's think, Roger.
It looks like most of the heating at the base of plumes is intermittent. And so that may be part of the interplay, as Jim pointed out, with whether or not you can get condensations in the upflows.
Let's think, Roger. Everybody wake up. Last talk before lunch. Wake up, wake up. There's one up here. Okay, so our last talk is Alphonse Sterling.
No, but I'll try it.
Push and hold.
If you can click and hold and drag slowly to the right. To your right, yeah.
Off the screen. There, oh, there it is.
Oh, it's way over there. I see. Okay, yeah, makes perfect sense. Okay, thank you. Yes, okay, so I'm going to talk about this, and we'll about you know, Spiro business in a bit, but okay, right. Sorry about that. That was left over. Telwinder is, let's see, this should be University of Alabama. Okay, so Telwinder actually was, he was a student, a PhD student, and I was doing some lectures in a class on solar physics, and Telwinder, you know, he was, you know, usual things, you know, good student, great guy, and all that stuff. But what was really key is that he was a great science geek. And as a good science geek, he used on his computer screensaver the AIA images updated daily. So he looked at these and, you know, he just stared at this, I guess, in his spare time. And so sometime after the class, he came to me and he said, hey, by the way, you know, I've been looking at this and I've been noticing that when I look at active regions, I see these funny things around them. I see these dim areas around active regions. And I see them in, you know, some channels of AIA. So, you know, that sounds pretty nice. And so we thought about this some. And we saw that, you know, they can be seen in coronal images. They're most obvious in selected EUV wavelengths. And that's actually different from coronal holes, which are dark in all AIA wavelengths other than 304, the EUV ones. Now, a similar feature had been seen in chromospheric calcium observations going back a long time ago. And they seem to be very common. So here we're discussing actually the coronal features of it. So this just brings it out a bit more, but here you can see in various wavelengths, and you can see it, and so yeah, it's visible even in 304 actually, which is an interesting point, but it stands out really nicely in 171. You know, it's kind of gone here actually in 193 and 211. You don't really see it. And the hotter channels, you know, you kind of see it. It's kind of a mixture though, but recall when you get to those AIA channels, you're getting a lot of mixture with cool lines also. So it's a bit complicated. So to understand it, oh, and this is showing that they seem to be there almost all the time, even when there are a lot of active regions on the sun. You know, it can almost kind of overwhelm the whole sun in this case. So we call these dark moats around active regions. So of course we're interested in what causes them. And Yiming Wang and colleagues looked at them in 171, and they thought that they might be due to the presence of a low-lying magnetic canopy, they called it in their case, surrounding the AR. Maybe that's true. Recently, we just found that they've also been studied by Leslie et al. They call them dark halos, so multiple names. And Harvey and Riesli and Reardon and company also studied them in the chromosphere. So here we're going to consider a different idea, and I'm going to get to that. But first, let's look a bit more at the thermal properties of these things. So Hellwinder did this work, but anyway, so we looked at several cases. So as I showed, when you have a lot of them in the sun, yeah, they're there, but it's complicated. So you want when there's only like one nice active region on the sun. So he picks out several cases of that and ended up looking at 7 of them. What he did was he defined the regions with contours and calculated the emission measure of the moat regions, kind of marking off the bright part. And then we did some emission measure calculations. We used Mark Chung et al.'s method, and we actually cross-checked it with Marcus Ashwandan et al.'s EM code also, just to make sure we were getting consistent results. So we used all the above 304 EUV channels in AIA for this. And you can see an example here. So these were done basically by eye. You mark off the moat as the outer ring, and then you mark off well where you really just see bright stuff and you know it's just in the way, so you don't include that. So you do that and you do some emission measures, and when you do that, this is what we get. So the moat region is the blue line, and the non-moat, so again, the quiet sun, so basically outside of the moat and not going near the limbs because of limb brightening and darkening and all that stuff. But anyway, so you get all of that and you get the EM from there too, and you compare. And you do indeed see that in this cooler region, there's a depletion of emission in the moat region. Now you go to the hot side, and of course it's you're getting very hot stuff here, but remember you're looking at an active region as opposed to quiet sun, so you're going to get hotter loops there. So that seems to be kind of a consistent picture. So then we went on and looked at 6 other regions, and you can see they have a variety of different shapes, but it's basically the same story that's coming along. Emission measures, and then we do the profiles, and lo and behold, they all have this sort of thing too. You know, you get that depletion in the cooler lines. So all 7 moat regions had this depressed emission over the 5.7 to 2.6.2 range. So I've talked about why that is. So then we think about the possible resolution. And we talked about this. Ron and I talked about this some, and Ron had some ideas, of course. But these weren't really hitting it. Actually, there's this paper by Spiro that I actually knew, and for some reason, this Spiro and Nochi paper I really enjoyed at some point. I don't know why, but I really did. I think I learned a lot about coronal loops and coronal physics, I think, from this the paper, at least the simple parts of it. So anyway, go to coronal loop theory, and this is all worked out, of course, by these good folks. And then there's a relevant new point I'm going to mention from Nochi and Spiro and Nochi. So basically, it's just a balance, right? You have the heat input, the H, and the radiative losses, the R, and then that's equal to the conductive flux. So we all know and love this because that gives us the hot coronal solutions that we live with every day and every night, in our dreams at night, of course. But the chromosphere is cold, and then you have the hot solution here and a nice thin transition region. Well, I guess this is also pointed out by Hood and Priest maybe before, but it was applied to this the problem that Spiro and Nochi were looking at, the DEM of the transition region or something. Anyhow, so there's this other solution available to the same loop equations. And to see it simply, imagine this. You just have the loop, and as a boundary condition at the feet, you have the chromospheric temperature of 10 to the 4th K. And then the rest of the loop, can you get a stable solution? Well, the answer is yes. Imagine that you have, in some circumstances, imagine you have a loop that is small enough so that gravity doesn't have any effect. So then you can just fill this whole plasma with this 10 to the 4 plasma, and it'll just sit there because it's all the same temperature as its foot points. So it's just a loop there, this constant temperature, that's cooler than the corona. Now raise the loop up compared to gravity, so you start to get some gravitational stratification, and so the top of it gets more rarefied, so you're going to get it to be hotter, and so its temperature rises. And so you can get it up to like 10 to the 5 K or something, and you're just matching the heat input with the radiation. But you go too high, and then some weird things happen, because it's starting to get too hot here, and then you're on the wrong side of the radiative loss curve that Wei Liu was showing earlier, and more energy you put in, you aren't radiating it away, and so then the temperature jumps up and you get that hot solution I showed earlier. So there seems to be a limit to when you can get the cool solution. And Spiro and Nochi said that it was about, for the solar conditions, about 5,000 kilometers. Loops that are below about 5,000 kilometers in height can have this cool solution as one of their possible states. Maybe the hot solution also. If they're above 5,000 kilometers, then they only have the 5,000, the hot solution available to them. Otherwise, they would be unstable. So, and then just in the paper, they also did some preliminary studies, and it seems like the cool loops, if they're small enough, below 5,000 kilometers or so, it seems like they're always cool. They didn't really get the hot solutions. So maybe they're there sometimes, maybe not. Anyway, you can get the cool solution, so let's work with that. So this is the idea that we're putting together. Maybe it's the shorter loops and low-lying loops that are in this moat region, and maybe that's why why it's dark. So let's see how this might work out. And to do this, let's just talk about a bipole. You have the nice bipole field. And the active regions are basically this sort of a structure. They're just a bipole roughly speaking, and they have the field spilling out beyond the main part of the active region, like this. So now, and this was Ron's idea to look at it this way, and it's a great idea. Now you look along the, from the left side, and you just kind of, you get as low as you can to the surface here. You try and look along the, along the surface, and, out over in this region, and see what you see. And this is it. So here's the active region here, and here we are down near the surface looking out along where the field is splaying out just one side of it. So what are you getting? You get these large loops there, and these are nice and happy hot loops. 211, 94, they're emitting, very happily. The lowest laying ones here don't get to 5,000 kilometers, so they're actually cool. And then you have lower down, you have mixed polarity out there. So you have these short loops. Now, normally they would stand up and they'd be nice and tall, and they would be 171, about 0.8 times 10 to the 5 or whatever, about 1 million degrees. But they're pressed down now by this strong field, so they don't get that tall. So remember the scaling laws say that the shorter loops reach lower temperatures and the longer loops reach hotter temperatures. So these short loops would want to be about 1 million degree 171, but they can't do it because they're pressed down, so they're only cool. So this is what turns out to be this moat in our picture of this. So we basically think the moat properties are broadly consistent with this Noce and Spiro and Noce effect, suppressing the cooler loops and also the lower lying ones. Now we also see this moat type thing in the 304 line channel, and this bothered us a little on the paper because we thought 304 emits at 10 to the 5. Well, maybe you would get the, these 171 wannabe loops. They might be pushed down into the 304, and so you wouldn't get the moat there. So we have a couple of possible solutions. Maybe there is some sort of canopy there, but also maybe this field is really pushing them down so that they don't even emit quite in the 304 regime. We're still looking into that. But anyhow, I can summarize. These dark moats are common around ARs, and we've seen where they're depleted in that range in the emission measure, about 5.7 to 6.2. And this could be due to the Spiro and Noce effect, and we're still investigating in the 304, and you can see Singh et al. For full details. Thank you.
Emission measure is actually lower in that region, and in the log T 5.
Yeah.
So compare with this quiet zone.
Well, yeah, and active regions too. Yeah, but that's right, because that would be quiet sun out there, really, yes. So compared to the quiet sun. That's right, I compared that with the quiet sun.
So would that imply?
Yeah, yes, that's right. So this red dashed line here, this red dashed line, that comes from the quiet sun. That's all quiet sun. Remember, there's only one active region in this study that we're looking at, right? So the one active region has, that's excluded for that red dashed line. We're only looking at the quiet sun average. So compared to that, the moat region is depressed in that range.
So compare the two lines, the blue curve looks to me is hotter than the...
It's hotter. It's hotter on the hot side. If you go to like 6.5, if you go to 3 million K, it's hotter. That's true because remember, that blue line is really an active region, right? So I'm looking, that blue line is from, it's in between these two curves, all right? In between these two curves, the temperature that's hot is hotter than it is in the quiet sun because it's active region loops. It's tied into a strong field. Yes, right, it's overlying the moat. Yeah, so there, those high ones up there, that's right.
Alphonse, very nice talk. Are these active regions mature or are they emerging?
You know, we didn't look at when they start, when this starts, but these would be when it's rotated to the center. So I can't say when at the start.
Right, so actually a student of mine looked at a sample of emerging active regions into the quiet sun. And immediately as they emerge, you see a dark halo. And she did exactly the same, EM calculation. And there, I think the picture is more clear in the sense that the dark halo you see in 171 becomes brighter in 211.
Yes.
And extrapolation, you can see these loops connecting from the newly emerged field to the quiescent field. So all those loops are low-lying, so I think it's consistent with what you're showing.
Okay, okay, thank you.
Just a comment. We were there. In the beginning, we were very confused because we saw these dips only in 171 as active region was crossing the disk in sun as a star measurement, so it was so clear. And I'm glad when your paper came out.
Okay, yes, right. Were you working with Hugh Hudson on that? Yeah, right, yes, I know Hugh has a, yeah.
So I'm kind of surprised to see that the interpretation is given only along the lines of closed feed lines. And I was wondering whether at the peripheries of active closed feed lines that could give you an effect like that, because this is what you might expect in, in these regions, not necessarily as organized as coronal holes, but just a mixture of open and closed feed lines.
Well, as I said, these have a distribution that looks different from coronal holes. I mean, it's a consideration, but also remember this is just outside of an active region where normally you would expect normal quiet sun. So maybe there could be some component to that.
I mean, when you do the extrapolation, you don't see coronal open field lines there, right? If you look.
Yeah, actually, we did do an extrapolation, and we didn't see a lot of, particular amount of them. That's true too. Yeah.
I would imagine you would have. That would be obvious if there was a coronal hole coming.
Oh, yeah. There's certainly not a lot. That's positive. Yes.
Let's thank Alphonse. And we come back at 1:30, I think. Okay, back at 1:30, everybody.
Give everyone 2 minutes. Right, Sam. Everyone's been waiting for this.
Oh, great. Way to leave me guessing. I can't. You can email me. Great story, Jim.
All right, you stragglers. So 2 announcements. First of all, please don't forget to sign the picture. And secondly, there's now a sort of a sign-up sheet out there on the table with the picture for people who are needing rides to the airport or might be willing to give rides. So I think you put down your name when you plan on leaving for the airport or when you would need to leave. So we can kind of coordinate and maybe share some vehicles. All right, thank you. So.
Right, so first speaker is Sam Wallace from Embry-Riddle.
I'm going to use this mic. Yes, so today I'm going to be talking about using the ADAPT-WSA model and ultimately how we're testing the SWEB theory of how the slow FIP-enhanced solar wind is formed. So just for context, the magnetic open-closed boundary is this global dynamic boundary layer at the sun in which the closed field coronal plasma escapes out into the solar wind via interchange reconnection with these open magnetic flux tubes. So by definition, this region is intermittently open as opposed to the continuously open field that forms coronal holes. Here I'm just showing a cartoon rendition of this overlaid onto an eclipse image. So you can see the heliosphere current sheet and a well-defined pseudo-streamer. So there's this theoretical model you may have heard of, the coronal separatrix web, which describes, I took this in a recent Teams meeting with Nick and Spiro. It was just, so this describes, the background, everything was perfect. Anyways, don't take this out of my time. So, this theoretical model describes the global magnetic field topology of this open-closed boundary layer as it extends out into the heliosphere. It's also known as the S-web, and it conveniently starts with the letter S. I don't know what the point of that is, Spiro. And some fun antonyms. That's just a joke. So, all joking aside, Spiro was fundamental in describing the global coronal magnetic field topologically as it evolves due to solar activity and what that means for the solar wind. So just the details of that are like you have this global dipolar field near minimum, and when you have an active region on the sun, Spiro was fundamental in helping describe how that topologically opens up a mid-latitude coronal hole and then creates a global solar magnetic topology that now includes unipolar streamers as well as the dipolar heliosphere current sheet, and then how that all maps to a web of separatrices in the corona and heliosphere. And so the bottom right is just showing this plot of the global S-web. So you can see the heliosphere current sheet as well as these S-web arcs that extend are well separated from the current sheet that are due to the presence of pseudo-streamers. These maps are generated by plotting the squashing factor. This is calculated, you calculate the divergence of neighboring magnetic field lines in the corona through a model, and that's how we produce these maps. So what does this mean for the solar wind? This theory constrains the origin, location, and release mechanism of the slow, FIP-enhanced solar wind. The origin being the closed field corona. It's the only way you can get the FIP enhancement. The release mechanism being interchange reconnection. Emphasizing the word release here, as this is not really addressing any other mechanism that could be accelerating the solar wind once it is disconnected from the sun. And the location, this really constrained the location to these S-web arcs or the open-closed boundary, as opposed to the preceding theory, which said that interchange reconnection can happen really anywhere on the sun, even embedded under the streamer. So in doing so, this model counts for the composition, variability, and latitudinal extent of which the FIP-enhanced slow solar wind is observed. So what I do is I use the ADAPT-WSA model. I use it for scientific research. I also do some development. And typically, that involves connecting in situ observations to their source at the sun. And so as I was writing this talk, I'm like, well, by default, I'm basically constantly testing this theory of how the solar wind is formed, because I'm really studying the ambient solar wind. So I'm not going to go into too much model detail. This is a well-known model. It's potential field-based. And we use it to identify the sources of the solar wind that's observed in situ. So some recent work that I've been doing is asking this question: what are the defining in situ properties of solar wind that originates from 3 types of coronal magnetic field? So these sort of distinctions of solar wind sources were described in Val and Borowski, this review of solar wind physics in 2020, where you have these types of field. They have active region and quiet sun that are at the magnetic open-closed boundary, and you also have the solar wind source of deep inside a coronal hole. And so to really identify the sources of the solar wind to this level of distinction, you need to use a coronal model like WSA. So what I'm showing here are results from basically using WSA and a criteria that involves determining the foot point field strength at the field strength of the photosphere at the source region of the solar wind, as well as the distance that field line is from the open-closed boundary, to categorize in situ observations based on the sources of active region, quiet sun, or coronal hole. This is 4 Carrington rotations. Each point on these scatter plots is 1 hour of ACE data. And so I'm just showing charge state and FIP. The red is solar wind that comes from an active region. The yellow points are quiet sun, and the blue are coronal hole. And so some things are immediately apparent are that the charge states and FIP are strongly linked to source region. You can see that in the averages and then the median and the tables down below. And also that you have this most variability in the properties for the wind that originates from the open-closed boundary. So this, in a way, is testing the SWEB theory, because we're showing that you have the expected composition of the solar wind and the most variability coming from the open-closed boundary, which is really is equivalent to an SWEB arc, just lower down. And so, in some sense, basically this is investigating solar wind on like a mesoscale timescale, like we're talking about like hours in situ. So we do expect that doing a study like this should be able to, on average, reproduce the long-standing relationships that we already know that are derived over years or solar cycles relationships between charge state and solar wind speed, and FIP and solar wind speed, and so on. However, going to these finer timescales allows us to see the times when the solar wind doesn't behave as we expect. And that's what I'm showing in this green box here, is there's a few hours in situ where our methodology says that the solar wind emerged from quiet sun, yet it's very FIP enhanced. And so when we actually look back at this particular period, there's not an active region on the sun. It's actually in a very deep minimum period. But if you go back 1 month prior, there was a very well-defined strong active region in this location. And so sort of this methodology allows us to tease out these time periods, and we're speculating that the FIP enhancement at the sun can hang around much longer even after the active region has decayed. So that's kind of the things we're looking into with this work. Also, we know that the variability in solar wind properties at the open-closed boundary likely comes from interchange reconnection, but I would also argue that this variability in solar wind observables also can be linked to connectivity changes at the sun. This is just an example of that. So this is a period in April 2011 that we have, I'm trying to use this thing. So we have the ACE spacecraft traversing a largely unipolar region, and then the connectivity is changing from quiet sun to active region back to quiet sun. And when you plot like the hairy ball of this this time period, you see that there's a large and well-defined pseudo-streamer that you can actually see in EUV observations as well. When you plot the in situ time series, this is just hourly average ACE data, and you I'm showing here that everything in dark red is the solar wind that comes from the pseudo-streamer, and the green lines show the changes in connectivity derived by the model. And you actually see that the FIP varies directly with the changes in connectivity, and the hottest and slowest solar wind is coming from that active region. So this is just another way that we can use this methodology to understand the variability we're seeing in Situ. This is just another rendition of this where this showing the, the spacecraft connectivity to ACE, and this is just how the spacecraft is sampling the solar wind through this 3D structure. So all this work and times being on the WSA model development team and working with Nikki's ISFM, we've constantly said we got to get the SWEB and WSA. We got to be able to do this with the WSA coronal magnetic field. And so last year, I led the development to incorporate this into the model. Some of the advantages of doing this with WSA are that, one, we typically use ADAPT, so we can actually derive an SWEB for one moment in time using the 12 different realizations and estimate the uncertainty in the values of Q that form these arcs. Another motivation is that WSA already has the infrastructure in place to read older photospheric field global maps, such as from Mount Wilson or Wilcox. So now we have the ability to derive these maps for going back decades with these older data sets, as opposed to just GONG or HMI. This is just a zoom in of this plot. So what I think makes this tool most unique is that it can quantitatively relate in situ solar wind measurements to the value of Q at the source region in the corona. So this is just showing the trajectory of ACE for April, May 2011, mapped back to 5 solar radii. And you can imagine the spacecraft is sort of flying through these SWEB arcs, sampling the solar wind from these regions. And then when you plot Q as a time series related to in situ observations, what I'm showing here is the top 2 panels are polarity and solar wind speed. Everything in black is hourly average ACE data. Everything in color is a WSA model. So these top 2 panels are showing that for this entire rotation, we have really good agreement between the model and observations. This is how we can be more confident in our model results. The bottom 3 panels are the FIP and charge state measurements for this time period. And in the middle panel, I'm showing a plot of the squashing factor derived by WSA in time. And so I'm just highlighting in yellow all the locations where we have enhancements in, where we're connected to an SWEB arc essentially. And some of those are unipolar because they're from pseudo-streamers, so we can only really identify these with a model. And these highlighted regions are always associated with slow, hot solar wind with the most enhanced and variable FIP and charge states at L1. So it's another test of the SWEB theory because especially these regions where the pseudo-streamers were angularly separated from the heliospheric current sheet. So this talk would not be complete without mentioning recent work led by Nick Argy that was accepted in APJ last month, and it's a proposed resolution to the missing open flux problem. And Spiro's contributions are really vital to this work and helping it to have a lasting impact on various open-ended questions in our field. So what I'm showing here is an illustration of the problem. You have total open flux plotted for nearly 30 years on 3 Carrington rotation running averages. That derived with spacecraft measurements of BR from the Omni data set, and that derived using WSA. So how you do this with a potential field-based model is you just sum all the open flux that's derived in all the grid cells at the outer boundary of the model, because at that point everything is open and radial. So what you can see is after about 1997, there's the models consistently underpredict the total open flux as compared to spacecraft measurements, sometimes by about a factor of 2, and this issue is most prevalent at solar maximum. So in 2019, we published this paper where we derived the total open flux by manually drawing coronal holes in SDO stereo composite maps, that's shown in the cyan line, and also using Karen and Jack Harvey's hand-drawn coronal holes in helium-10-830, that's the green line. And you can tell that they agree very well with the original WSA model drive result. We are using in all 3 of these data sets, we use the same photospheric field maps to derive the total flux. So this really begs the question, could the missing flux be from the boundaries of coronal holes that are not relatively dark in EUV or bright in helium-10 830? And so our group by any means is not the first person to suggest this. John Linker and several others have been working on this problem for years, but it's just where our results pointed to at the time. So all these years later, we found a simple way to test this hypothesis by deriving the open flux through field line tracing. So imagine you have this well-defined mid-latitude coronal hole. It's easy to see with your eyes, the dark regions from the bright emission. But how that open and closed flux translates to a model like WSA is resolution dependent. And so that's what I'm trying to illustrate with this cartoon on the right that's from our paper. So this dotted line, imagine it's you drawing the coronal hole boundary in this EUV image. Now, when we calculate the regions that are open and closed on the sun with field line tracing, we do this by tracing outward from the photosphere to the outer boundary, and also inward from the outer boundary down to the photosphere. And if we do that in both ways, and the cell at the photosphere is open, we call that a bidirectional cell. And that's what I'm showing in orange here. We do this sort of bidirectional tracing just to account for the undersampling that's going to occur because we have a finite grid resolution. However, there are times where when you trace in one direction, the cell at the photosphere is only open in one direction. When you trace outward and that cell is open, this typically maps to a polar coronal hole. So in theory, not that big of a flux contribution. However, when you trace inward and that cell's only open in the inward direction, those cells typically map to the coronal hole boundary. And that's what we're showing in purple. We call them perimeter cells. So this plot on the left is just a period, one Carrington rotation and solar maximum, where we're just showing all the perimeter cells for that period. So you can see that it's not a small amount of flux, and especially near solar maximum, you can get large contributions of flux from these active regions that are at these coronal hole boundaries. The standard width that we run WSA, the standard resolution that we're running WSA is 2 degrees, and that equates to roughly the size of a supergranular at the equator. So this is like you wind up getting this sort of fuzzy boundary that's resolution dependent that represents the coronal hole boundary in the model. This is my second last slide. This is the complete version of the plot that's in the paper. Now, the blue line is all the total open flux calculated with this field line tracing method. So all the bidirectional cells, the ones that are only open when you trace inward, the ones only open when you trace outward. And you can see that that result agrees really well with the spacecraft observations. And when you break that down further, the original result from WSA is in green. And the orange line is showing the bidirectional and outward only calculated flux. And it agrees well with the original answer. But if you look at the purple line, that is the total open flux calculated from only these perimeter cells that are, they're open when you trace inward only. And you can see that, especially at solar maximum, there's a huge contribution of flux coming from these cells. And that is actually what's making up the difference to get this blue line derived from field line tracing to match observations. So it's a very, in some sense, we arrived at the right answer through this just the resolution of the model just worked really well. There's a lot of things that you can do with it, like a lot of things you can add to this study now. You can play with different resolutions and see and try to estimate the width of the open-closed boundary, try to understand the contribution of open flux that comes from the slow FIP-enhanced wind. So that's kind of where we're going next. And this is just my last slide, just that we have linked this FIP-enhanced slow solar wind with varying properties to S-Web arcs that are near to and far from the heliospheric current sheet. So we're directly able to test the unique 3 things about the S-Web model that characterize the slow solar wind. And I'm just going to stop there. Thanks.
No. You don't want it? All right. Ben.
Sam, very nice talk. I know we've discussed this before, but do you have comments on this idea of basically the parameter in WSA about being like distance from the edge of the coronal hole seems to be something also similar or could be similar to distance to an S-Web arc or, you know, the heliospheric current. You know, it's sort of like, and anyway, just on that, I mean, that somehow the reason this empirical stuff works so well, you know, is because all of that topology is folded in there somehow as well. And do you have ideas about how would you go after that in terms of saying, all right, well, like if that's true, is there a kind of statistical test that we could come up with that would be like, okay, this 400 kilometer a second wind is obviously from the middle of an open field region versus this other 400 kilometer a second wind, which is obviously, you know, maps right back to a pseudo-streamer or something like that.
Yeah, so the first half of your question, the distance from the coronal-hole boundary parameter, it does tell you basically the same information, I think, as Q, you know, because it's just telling you if you're at the boundary or not, and then you could just look at the polarity to see if you're at a pseudo-streamer or Helm streamer. I think this there's a lot we can do with this tool to where we can, you know, sort of statistically parse out solar wind that's within a 2-degree bend from the boundary, or, you know, transitioning to deep inside from like 2 to 4 degrees, and then, you know, all deep inside a coronal hole. So yeah, that's definitely possible.
Well, okay, one quick question, since it's Spiro.
I went really late.
Yes, let me make a comment on that, Ben. This distance from the coronal-hole boundary is really important because it distinguishes between interchange as being the source of the slow wind versus expansion factor, right? Because the expansion factor is actually small for pseudo-streamers, whereas it's large for Helm streamers, whereas the distance parameter seems to be the important predictor for whether the wind is going to be slow or fast. So it really is something to do with being near the boundary rather than just the expansion factor.
Yeah, I was really hoping to have time to show that and talk about my 8 times at Goddard when Spiro didn't agree with me on the work I was doing about expansion factor.
Okay, well, let's
good.
thank Sam again.
Thank you.
So, Brewer just told me that there was some confusion with time zones, and he has to go to give another lecture right now. So he won't be able to give his talk, which is not the next one. Etienne is next, and then Noor is after that. Is anyone from the session after the break willing to give their talk after Etienne? Okay, Nikki's willing to? Yeah? Okay. Sounds good. So Nikki, sorry? Well, you can chair yourself. We trust you. How's that? All right. Well, thank you. That's good then? All right. So, and then back to, just Nikki and Noor are switching. Oh, then Ron after that, yeah. Wait, is Ron here? Noor is coming back after the break, so he'll take Nikki's slot, and Nikki will take his slot. Well, sort of. You go after Nikki, so it's going to be Etienne, Nikki, then you. Yeah.
So as you heard, next up is Etienne from LPP, joining us from all the way over in France.
All right, good afternoon. I wanted to, when I saw that there was Spirofest, of course, I wanted to talk about the modeling that we've been doing, and I was putting a title on simulation of solar jets. But really, what I'm going to talk about is simulation of solar jets with arms. This is not approved by Rick, this logo. So I will not discuss about all simulation of jets. As Spiro might say, I'm not going to talk about a bunch of losers. When I was preparing as well, I was looking at Spiro's citation, and I realized that actually the work that we did together in 2009 was actually quite heavily cited. I mean, it is the third most cited article of Spiro. But that's not the reason why Spiro will think that I'm his favorite postdoc. I will explain why at the end of this talk. So I want to talk about a bit of the history and what has been done through this type of simulation. When I arrived in 2006 at NRL at that time, As Judy mentioned yesterday, Spiro was very interested in magnetic topology and understanding reconnection and null point reconnection. So these are slides that I took from a presentation that Spiro gave at the US-Japan reconnection workshops in St. Michael's in Maryland. And he was interested in this type of simulation which was already run by Rick, where you had a null point and a configuration, and he was moving it, sharing it a bit. And the goal was to obtain an impulsive compact event, an impulsive event. Because as we were discussing this morning by Alphonse, when you just do a bit of sharing, you start to have a current sheet, but it's not very impulsive. I mean, the null point is reacting immediately. And in this simulation, indeed, we did not have much conversion of energy. So Spiro suggested me to look at axisymmetric configuration. If you have a null point which is purely axisymmetric, because of the topology, with an embedded polarity, the topology inhibits magnetic reconnection. You cannot have reconnection unless you break the symmetry, for example, through a kink. So we started to look at that, and I designed a new simulation. And that was the first jet simulation. Actually, so you had a null point. Oh, maybe I should. You have a null point, you have a polarity, we were twisting it, injecting energy. The system was staying symmetric, then we break the symmetry, and then in that particular set, the system was... I mean, we were happy, we had increase of magnetic energy, we had increase of kinetic energy, but there was no jet yet. And I figured out that, as usually, we can ask my PhD student, I made a mistake in the setup. I had a very, very high beta plasma. So it was 10, so it was not very, very consistent with coronal values. So what I did was I corrected this, and this was our first jet simulation. We started to have still sharing, and then the system was releasing energy very impulsively, the way we wanted. So for example, we had, we were increasing the magnetic energy and really were able to release 72% of the free magnetic energy. So very, very strong energy release. And at the same time, we had, as can be seen here, we had upflows. So this is the velocity here. And we have a magnetic wave which was propagating. Now, at the same time, in the solar system, Stereo was just being launched. And a few seas away, we had the PI team of Seki, with Russ, Angelos, and the other Spiro Patsoukakos. And we had a very nice observation of a jet when Stereo was in his stereoscopic range. So the two spacecraft were separated by only 10-15 degrees. So this UV jet was observed in different wavelengths, and actually it's a jet where you can see it does propagate very, very far away. You can see it here in core 2. And so we had this model of jet. We had the density structure, and as Ben recommended, when you have that, you start to have a proxy for the density for the emission measure, which is a square. You integrate along the line of sight the square of the density. And we found that we had a lot of, that it was very similar. So basically we convinced ourselves that the density structure which was in the simulation could be very, very well applied to coronal jets. And so that was the model for coronal jets of the 2009 paper. There should be a movie there. I don't know. No? Well, okay. So there should be a movie for the model of a self-consistent coronal jet, where what you're having is that the key element is that you have a 3D null point topology. And this null point is going to do a lot of things for you. It's going to it's going to be able to store the energy for a long time. And then eventually there's going to be an eruption, an impulsive event, as Peter was mentioning. It's the same way as a CME. You may have a breakout or you may have torus instability. It needs to be demonstrated which one is working. And you're going to have interchange reconnection between the closed field and the open field. And this is going to be very impulsive, and you're going to launch magnetic waves. So the jet driver really is the magnetic untwisting of the closed feed lines, where the velocity of the front of the jet is alphenic, and where most of the energy is still in the Poynting flux. Now, that allows us to see jet-like event as impulsive events, reconnection enabled. in which you have an atypical post-flare loop, which is where energy is deposited at one foot point. So it's not something that we model, but we have to keep this in mind. It is very important to explain the observation. And in addition of it, we have this magnetic and twisting wave where well, you cannot see here where the field would propagate. Now, a great strength of that particular simulation of arms, which was designed by Rick, and of the model, that is highly tunable. So it's not necessarily, as Rick mentioned, all the power of ARMS in terms of adaptive mesh refinement, but we have mostly been able to do lots of numerical experiments. We've been able to test a lot of things, and that's what I want to demonstrate, all the work which has been done based on this. The first thing that we've been able to do was to change the photospheric field distribution or the coronal field. I mean, we started with an axisymmetric configuration, but we very quickly realized that as soon as even if we are beckering the symmetry, we were still able to store enough energy, have a structure which was building twist, and eventually, even if the field was inclined, even if it was not symmetric, even if we had a flux distribution which was not axisymmetric, we were still able to have impulsive events and anechoic jets. We saw as well that when we were driving, actually, we had two modes for reconnection. We could have driven reconnection, so we started to shear, and there was a bit of reconnection at the current sheet. That's what is shown here. You could have what we call straight jets that can explain some of the observation. And later, when you have an eruptive system as with CME, you will then have the more impulsive, the helical or breakout jets. Later, so there has been new tests where we changed the topology. I mean, we have a null point, but Peter Wiper did some simulation in which he had a ball patch instead of a null point. And in the same way, he was able to also produce these helical jets with a spire. There was another simulation where instead of having an open field, we start to have a closed field. And in the same way, we can still have jet and explain this time active region jet, not only coronal-hole jets. Actually, that's another work, and we are somehow back to the initial work of Spiro, which I found very interesting. I think it was the first work, one of the first work of Peter with ARMS, which was to look at the influence of the scale between the closed field here, the inner field, and the outer field. And that's an element which is very important for jets, which is this scale, this relative scale is very important. If you want to have a jet, you need to have a big difference between the inner field, the typical scale of the inner field, and the outer field. If you start to have structure which are more or less of the same scale, basically what you're getting is a compact flare. You're getting the wave which is launched, you have this bouncing back between the two foot points, and probably as in a typical coronal loop, you have energy injection at both foot points. So jets really need to have different types of magnetic scales. So that's our example where we were changing the magnetic field. But we can play also on the driving motions. For example, we realized, and again, there should be a movie, but I guess it's not working. All right, well, what we realized was the system, a null point system, basically relax once the jet has happened to its initial potential structures. In the previous simulation where we were driving and we were basically stopping the driving at the moment of the onset of the jet. Now, in this type of systems, is the system relaxed to its initial state. If you have a continuous driving, what we're able to do is that we are able to have homologous jet-like events. So that's what, you don't see the movie, but that's what shows in this plot. You keep driving and you have different sequences of jets. So the null point system really plays as a role of a capacitor. It stores energy, releases it impulsively, stores energy, releases it impulsively. And that explains the recurrence nature of these type of events which are commonly observed. Now, another big improvement which was done in this type of model was done by Peter Wiper, which is to change the way we were driving the twist in the system. In most of my simulation, I was driving basically the whole system, the whole structure around the spine. And Peter did a modification in where he was mostly driving much more close to the polarity inversion line, so having a much stronger shear there. And again, this time the movie is working. Well, that's because it's Peter. Where in that case, when you do that, what you're doing is that you're building up a flux rope. And you're forming this flux rope, and these flux ropes is actually interacting with the null point, and you're having a blowout eruptions. So that convinced many, many more of the observers. The pre-jet dynamics is really much more realistic and consistent with the observation, and the fact that in many, many of these events, at least when at a larger scale, you do see this type of mini filaments which is present. Now, in terms of driving the jets, whether you're driving with a flux rope or where you're driving modestly, it doesn't change. The driver keeps being the magnetic and twisting wave. Other things that we've been able to play with was to modify the atmosphere. So we had some runs in where, for example, we were using different plasma beta we were in the surrounding. And we were seeing, for example, that if we start to have sim jets which have a plasma beta where the surrounding has a plasma beta close to 1, we were having jets which were much more straight, much less energetic, but that mean also much more, which where you have a higher level of recurrence. So that may account for different properties of jets between the large-scale X-ray jets, large-scale coronal jets, and features which are much smaller to the photosphere. A later development is to start to have jets and see how they propagate in the solar wind. So the first work on this series has been done by Julie Karpen, where we started to have a Parker solar wind, so an isothermal solar wind, and she looked at the propagation in this type of configuration. We are now having simulations that can go up to 60 solar radius. And so the initial setup is the same, but we are now looking at how the jet is propagating in a subalvenic wind and then later in a superalvenic wind. So that's the work which I'm doing now with my PhD students, this second generations of ARM users, in which what she's doing is trying to model the propagation of jets in the context of understanding magnetic switchbacks. So one thing that we are finding is that the U-loops, which are really present at the base of the photosphere, don't propagate. They don't survive the solar corona, the low beta corona. So we are not directly creating a full reversal switchback. But if we do a cut in the system and we're looking at the in situ type magnetic measurements, we do see when the front of the jet is happening, a decrease in the magnetic field, in the radial field. We see the magnetic field is more or less constant. We see an alvenic increase of the velocity, which is very, very typical characteristics of most of the switchback which are observed. So we have magnetic deflections. We don't have full reversal switchback, but we still have magnetic deflections that can reach 70 degrees. And that's the later. So so we've been able to do a lot of things, and also we've been able to do benchmarking. I've been using this simulation to benchmark helicity conservation. We've been using this with Craig DeForest and Laurel Reichsmuller to benchmark other codes, for example, a flux code. Peter Wiper has used it with high resolution to look at the dynamic of reconnection current sheet. So all these models have been able to really bring a lot of information. And again, many of these, there's many papers. Each of them is maybe incremental. We were talking about incremental science here yesterday. But when you look at it after 20 years, there's been 20 papers, and all the amount of work which has been done has been indeed giving us a wealth of information on a particular field, which is coronal jets. And all these thanks to Rick Devore ARMS code. And just stem from Spiro's original ideas. And some ideas that Spiro has been able to nurture, that has been to push, found consistently over the last 20 years. Now, on a more personal note, I want to thank Spiro for, being a very understanding supervisor, as I said already yesterday. I mean, having a French postdoc means, you have somebody who's used to a huge amount of vacations, that needs to get some rest, needs to go back to France regularly to mingle with French politics in order to secure a position. And Spiro has been very, very understanding of this all the time. But there was a bit of a tradition, so I was regularly go back to France. And when I was coming back, I was never coming back empty-handed. I've been going back regularly with different types of goods, macarons, and mostly chocolates. Actually, I started to have, how you call it, my card at the favorite chocolate place of Spiro. And since I'm coming back from France, I have your usual box of chocolates. I would have said normally, share it with Mary. But since this time there is the comedian jury, I encourage you to, when you meet with them, to share it with your fellow colleagues and think about me.
Well, very nice development over all those years. With the early models, I'm thinking about the bright point now at the base of jets, and that's usually off asymmetric, with the spire. So I guess with your early models, you would not get that, but then with Peter wipers, you would. Is that basically right?
No, I mean, you were having them anyways, because the system is never, once you break the symmetry, reconnection is not symmetric. I mean, once you would have, for example, it's happening mostly in one direction. So there was always a bit of a level of asymmetry as soon as the jet was occurring. And in particular, as soon as you were breaking the symmetry, I mean, it was very, very similar to Peter's. There was no, it's clear that we did not have a pure flux rope, but the type of asymmetry was there. Not an arcade, no.
Yeah, right, okay. Yeah, I think they're flare arcades. Models are using, that one are using like Peter wipers.
Oh, no, we are using this one.
Okay. I think Peters gets the, that asymmetry, I think it gets it right, or better. It might, I don't know.
As soon as
it's a question, I guess.
As soon as reconnection takes place, I mean, we can ask Peter, I don't know where it is, it doesn't change. Whatever comes out of...
And the flare loops?
Whatever comes out, as soon as you're a bit further up, it doesn't change the dynamics. The twist, all the twist is transferred.
Suddenly find myself in the middle of this. So yes, I guess, to your point, Alphonse, about the low atmosphere and the bright points and so on. Yeah, Etienne's for sure will have a bit of asymmetry if it's if there's enough sort of deflection or there's sort of different patches of surface flux. So yeah, there could probably be some brighting you're thinking of under the erupting flux rope structure. Fair enough, but there could be some still asymmetry in this model for sure. But Etienne's exactly right that the wave that gets launched, the jet mechanism part, that is similar between both our kind of approaches to the energy storage. We slightly different how the energy is put in, but ultimately it's an untwisting wave.
Yeah, the key is Etienne's plot early on where you show the amount of energy released in the, let's say, solid body rotation, right? We found that over like 85%, I don't know, some huge fraction of the energy was released during that impulsive burst of reconnection, even though the energy was put in kind of volumetrically. The key difference between putting it in a filament channel is if we're in a filament channel, then you know when the filament channel takes off, you lose most of the energy. So it's kind of dead easy, brainless as to why you get a huge fraction of the energy released. But even putting it in a volumetric, somehow the null point in the reconnection was able to access enough of that volume to release a huge fraction of the energy. I mean, I remember Etienne,
the 70% was mostly the helicity. We were releasing 90% of the helicity that we put.
90% of the helicity.
The helicity was removed all of it. No, I mean that's Peter's setup. But I mean, your focus is in the pre-flare dynamics. My focus is really in the jets and the propagation. It's the physics of what you see, well, here.
Yes, it is. Nikki, thank you for being flexible. Yeah. I think they prefer to use the podium mic. Yeah. All right, so welcoming up Nikki, who's kindly slotted in here to take this spot, and she's from NASA Goddard and has some wonderful things to tell us about solar wind density structures.
Everybody. All right, let's see. So this work that I'm going to be talking about is with thanks to the ISFM team that I've been working with for the past 7 years, also Parker Solar Probe, and as Craig is going to tell you later, Punch is going to solve all of the remaining questions that I have at the end of this. Let's see, so this talk is kind of in two parts. Part one is like a crash course in science of structures in the solar wind and how we think they're related to interchange reconnection. And then the second part, I'm going to revisit a lot of that science, but in the context of some Spiro stories. And I can't believe Erica's not, I wanted Erica to be in charge of me, but I guess I'll just have to
live with Joel. All right, so how do I do this? I go like that. Okay. All right, so to begin with, periodic density structures are a type of solar wind mesoscale structure. Mesoscale as in way, way bigger than kinetic scales, but smaller than the big CMEs or big CIRs or things like that. So periodic density structures are a type of mesoscale structure in the solar wind, and we observe them throughout the inner heliosphere. We observe them in situ, and we observe them remotely. So let's see if I can do this. Ooh, there we go. All right, we observe them in white light images. These are Secchi images here, stereo Secchi high 1 images, where we're seeing a series of periodic density structures coming out from a helmet streamer. We see them in core 2 as well, so lower down close to the sun. This is high resolution deep field images of core 2 where we see them all the time. And we're seeing them, of course, in the new WSPR data too. And the way we confirm that they're periodic is with Fourier analysis. And what we do is we take slits of intensity data and we convert that into a time series and we perform Fourier analysis on it. And by the way, this code is really robust and it's open source, so if anybody wants it, please let me know because we're happy to share it. So we see them throughout the inner heliosphere as far out as our imagers can see, and this is where punch is going to play a role. Right now, we can only follow them to about 50 solar radii, and then they fall below the noise floor and the resolution limit. But we see them, and in the remote imagers, we can see them from a couple of hours to about 3 minutes, and we watch them accelerate through the acceleration region, and they sort of expand at the rate of solar wind acceleration, which is expected on average from mass conservation. And yeah, so that's what they look like when we see them in the imagers, in the white light imagers. Am I doing this wrong? No, they're, oh, wow, that was too fast. Oh no, shh. Where's Violet? Oh no. Oh, I went too fast. Okay. Ah. How does this work? Which button goes which way? The bottom one goes back. Okay. Oh, all right. I swear I'm smart. Okay, this is what they look like in situ. And again, we see them throughout the inner heliosphere. We see them in helios data, and this is what they look like in situ. So we see them in helios data very close to the sun. We see them all the time in wind data and ACE data. And what you see is it's a train of periodic enhancements in the density. Often they have B field signatures with them, discontinuities with them. Sometimes there's flux ropes with them. And we've, like I said, we've seen them throughout the heliosphere. Here, we can get all the way down to like 3 minutes because we have really high time resolution. And we see them, importantly, not just in the proton density, but we see them in alpha to proton ratio, charge states, the FIP, sulfur, and all of that confirms that it's something back at the sun. And reconnection is the most obvious way to get that high FIP-enhanced plasma out. And they survive all the way to 1 AU. And then the fact that we get the associated magnetic field variations in the form of flux ropes and things like that confirms that they're structures, and there's just no way to explain them in terms of some sort of local instability. Okay. Okay. This is a really important connection. It's not just important from the perspective of how the solar wind is formed. It is also really important for the daily driving and dynamics that occur in Earth's magnetosphere. Because they're periodic structures in density, I think there's a movie here, but maybe it's not playing. Oh, yeah. Okay, so because these are density structures, they're dynamic pressure structures from the perspective of the magnetosphere. And even though they're small in our coronagraphs, they're huge compared to Earth's magnetosphere. So it's why we have to get them right for understanding the Earth's magnetosphere. So here, this is supposed to be a cartoon. But anyway, imagine the dark purple is really dense and the white there is less dense. And as that structure advects over the magnetosphere, it literally squeezes the magnetosphere and then releases it. And imagine that you're doing that periodically now. You squeeze it and release it and squeeze it and releases. And in fact, what happens is you drive global dynamics in the magnetosphere at the exact same discrete frequencies. And that's what the plot on the right is showing here. This is showing in black, when all those dots light up, those are ground magnetometers all over the world lighting up with the same very discrete frequency. So you see it throughout the magnetosphere. And these frequencies find resonances in the radiation belt and lead to particle precipitation from the radiation belt into Earth's atmosphere. So if you want to understand the state of the magnetosphere, the state of the radiation belt, you actually have to get these things right, and they happen all the time. Okay. Okay, so we counted up all of the times that we saw these periodic density structures at wind. Wind is out at L1, and it has now 25 years of data, so 2 solar cycles. And you can really start to tease out sort of where these things might be coming from, how often they're really in the solar wind. And we looked at how often they're there, but also how often they're there and they exhibit alpha to proton ratio variations. Again, the alpha to proton ratio variations are really important because those are the ones that for sure come from the sun and cannot be explained in any way as being developed en route. And so what I'm showing here is a comparison of the occurrence distributions. And basically, what I want you to see is that the low frequencies, the ones that are sort of hour-long frequencies, have very high amounts of alpha to proton variations associated with them. They basically always have these huge alpha to proton variations within them. And there's a second population, though, that often has alpha to proton variations, but often does not. And so even though they all come from the sun, there are definitely 2 mechanisms associated with this, is what we think. Okay, and actually we already know the answer to this one. These hour-long ones, we had seen, those were the ones that we were seeing in the stereo core 2 and high 1 data. They come from helmet streamers. We saw them, this was a paper that I did with Angelos, where we counted up every single pixel. We said, yes, no, was there a frequency? And if yes, what frequency was it? And we saw that most of the time, near the streamer, we got sort of an hour to 90-minute frequency of these structures coming off. So the helmet streamer is what makes this population. And actually, in terms of the large alpha to proton variations, that makes sense because you've got the very longest loops there. This over here is another piece of evidence supporting this, where we see these long 90-minute structures at the current sheet in situ at 1 AU. And so we know it's the heliospheric current sheet because the straw, we change from one polarity to another polarity. And then we have these 90-minute trains of density structures within there. This one right here is a flux rope. It's like a little mini CME. You've got bidirectional straw, and it's like a little CME. And in fact, this is exactly what you would expect if you look at like Aleda's 3D simulations, the stuff she did with Ben. You would expect that some of them would be flux ropes, but not always, because as they come out, they have to reconnect with the surrounding field to come into balance with that. And then, of course, what's so important about this work is that we have the FIP variation and the charge state variation on the same 90-minute scales, confirming for sure these things came from the sun. All right, so what about the other population, the 1 to 4 millihertz? Well, again, we have counted up all the different times we saw this, and we get this broad distribution here in the protons. And it's broad between 1 and 4 millihertz. And in order to reproduce that, you actually have to assume a distribution of added discrete frequencies that looks like this green distribution here. And you have to add it to at least 40% of the solar wind to get our actual observed distribution. And so if you look at, well, what on the sun has a distribution like this green one? I'm already showing the answer. There's transverse fluctuations in the corona. Observed, this is a paper by Richard Morton, where he showed transverse oscillations with this exact same occurrence distribution. That's what I'm plotting over here. He observed it in AIA and also in COMP, and it matches quite closely. So we speculate that the second population are these transverse oscillations, which are also observed in the jetlets as well, and also observed in energetic particle radio bursts. Okay, so I will advance. So we think that there are these two populations here. This one population, this sort of less than 1 millihertz or sort of hour-long time frames coming from the helmet streamer. And this other population is driven by P modes that somehow mode convert into transverse alphanic fluctuations up in the corona. But I just want to point out how hard it is to connect all of this, because there's 93 million miles, 4 days, a whole lot of physical processes between all these things that are happening at the sun and the solar wind that we finally observe that drives all these dynamics in the Earth. But the time history of how the solar wind was formed is really important for the actual state of the magnetosphere. All right, so now to the Spiro. Okay, so this paper here, this was really the first time we had high enough resolution composition data to even do this analysis. So this was work that we did with Sue Lepre, because she had to reprocess, her team had to reprocess these ACE data at such high resolution so we could even do this analysis. What I'm showing here is we were trying to finish this paper up when Violet was born. And so, but she wasn't in daycare yet, so we just had to bring her into the office to finish up this paper. So there's Spiro holding Violet, so we could finish up this paper right here. She's blowing spit. I know you are. And I don't know if Sue's on right now, but I know she was on yesterday, because she and I were texting about how inspired we were by Spiro and the example he set with making sure that the centers are partnered with universities. And so Sue and I have carried on the partnership, and so Sue and I now have brought on Irina Gershkovich, who did this analysis, repeated it, but for all of the ACE data. So we have statistics for the entire ACE data set now on how often this happens, which charge states, which FIP elements, do they look different, which periodicities, all of that. Irina did all of that work, and she graduated last summer. We're bringing on a new student this summer probably. Oh, that's backwards. Okay, forwards. Okay, so then we started working with Spiro on, okay, well, what could be causing the periodicity? And TNE, as we heard about this morning, is one idea, TNE and helmet streamers. He said, well, maybe the TNE cycles get set up and then somehow that modulates the reconnection or something. And so Michael Schlenker led the paper on showing exactly this process in these helmet streamers here. And we were at a group meeting, and Emily Mason, who we also heard about earlier this morning, Emily Mason was sent off. She was a new graduate student with us, and she was sent off to go find this. Spiro said, Emily, you go find this in those AIA data. And so Emily came to the group meeting, and she showed these events. Spiro said, the observers got it wrong again. That is not a helmet streamer. I told you to find those in helmet streamers. And Spiro looked at us like, what are you guys doing? This was not what I meant. And I said, Spiro, isn't this exactly what you were thinking? It's still the last closed field lines. It's still a null point. Isn't this still really important? And finally, he agreed with us. Yes, this was still really important. And so, in fact, we had not only did Emily go off to publish the results, but we had a press release about it and about what was talked about this morning about how it's this important link, actually, between the solar wind and the coronal heating. If Larry were here, he is with, let's see, Oliver at violin lessons right now. But if Larry were here, because your cat wasn't available to babysit the kids, I don't know. So Larry's home with the kids. He would say, that a lot of you probably don't know this, but Spiro was instrumental in the creation of heliophysics. And that's only a little bit of an exaggeration. So this was Spiro and Larry at the IS2P Next workshop, inspiring the next generation. Spiro actually pulled out some words that he had written when they were imagining heliophysics in the beginning. And I really encourage you to go pull up this paper here, because they've re-put those words into this great observatory paper about the importance of heliophysics internationally. And by the way, it's working. Europe, for the first time, has a heliophysics web page. They have a heliophysics in Europe meeting that they're holding next year. This was Spiro keeping everyone inspired during COVID. It's a null point topology, if you couldn't tell. I think maybe a jet or something. This is Spiro teaching the next generation about S-web arcs. So that's Violet and Oliver and little Rika. I think she was a year, maybe? Not even, no, like 6 months. Spiro is so inspiring that the children want to dress like him. So this is Oliver stealing Spiro's hat because he wants to dress like Spiro. And Violet is very jealous that her brother got the hat and she did not. And Spiro, again, thank you for inspiring the next generation to break out. All right, that's it.
Great, Nikki. So the 1 to 3 millihertz component that you associate with the transverse oscillations in the corona, you mentioned P modes coupling into Alphane waves, but Alphane waves are incompressible. Would they produce the density fluctuations that you see?
Not alone. They are driving reconnection. There has to be something that's periodically driving reconnection.
I see, okay.
Yeah.
Thanks.
It's been suggested by several people that the P modes might drive periodic jet reconnection.
Yep.
Also, with the Alphane waves alone, in some models for like spicules, there's some coupling into higher order modes that can actually have a compressive component, when it making a slow wave. So I wonder if it could do that without the reconnection also. I don't know if it would be a big enough of a contributor, but it's something I think to think about.
Yeah, I mean, I think there's 100 steps to get the P mode energy and the coupling all the way through to the solar wind release. But we see these periodic structures in the solar wind, and they have the alpha to proton variation, so you have to somehow enhance those with the density structure that you're releasing, is why closed field release is sort of the most natural explanation for that, but you could imagine other ways potentially.
So here's a shot in the dark question. You're an expert on density in the solar wind. So Parker Solar Probe sees periods of very low density plasma coming out, and these are the so-called superalphanic regimes. And it's, some people interpreted these that we're getting inside the Alphane point, but my viewpoint is that they're seeing these very low density periods. So what could cause that?
What could cause that? Well, no, that's interesting that you point out. They see subalphanic wind at Earth. Very rarely, but it happens. And so I think the point is the solar wind is highly transient. There's no such thing as a steady solar wind flow. And I think we have to be interpreting all of these things in that context. I mean, I think the Alphane, as Craig would tell you, the Alphane surface doesn't exist. It's got to be this lumpy, bumpy thing.
Could you invert your analysis, Nikki, and look for periodic darkenings or unusual darkenings rather than the brightenings?
So in fact, well, in situ, we don't have an absolute density requirement. So in fact, it's just peak to trough variations. And so in fact, some of them are sort of, for lack of a better word, fast, smaller variations in lower density wind. Well, then you run, so how do you know if it's just no signal because you're at the noise floor? But yeah, that's the kind of thing, with punch, with the deeper sensitivity, we can start to tease out, did I see 0 because really it was 0, or did I see 0 because the instrument just wasn't good?
All right, well, let's thank Nikki again, and we can bring up Ron Moore from UAH and Marshall. I present Ron Moore.
That good, or? I don't know. Maybe I'll try this. Okay, Noor was supposed to speak before me, and he and I are singing this. We're going to be a little bit more specific about what drives the interchange reconnection that drives the solar wind. Okay, this talk is about an idea for how coronal plumes might work if it turns out that the corona and solar wind are driven by a lot of little flux rope eruptions at the edge of the magnetic network. We assume that the little flux rope eruptions work more or less like the flux rope eruption in Spiro's jet model with Peter Wiper. All right. All right, there are 4 points. First, there's evidence that switchbacks come from the magnetic network. We take that as a sign that the corona and solar wind might be powered by magnetic twist waves from the little flux rope eruptions at the edge of the network. Second, in quiet regions, it's observed that the coronal luminosity, UV luminosity, increases and decreases as the coastline length of the underlying magnetic network. Third, it's observed that EUV plumes turn on as their foot magnetic flux packs together, and turn off as their foot magnetic flux spreads apart. From these observations, we are led to think that the coronal heating in a coronal magnetic funnel may be less when it has a plume in it than when it does not have a plume in it, and that lots of the plasma in an EUV plume may come from cooling and draining of the corona higher in the funnel. So how do I go on here? Yeah, I've been pushing the middle. You have to hold it down or what?
You just click once and...
Just click? Oh, okay. I've been pushing too much. Okay, now I got to go back. Now I got to go forward. Okay. Okay, this is a... That's not too bad. Okay, this is a... to go this way. A Copland. Yeah, okay, luckily yeah, okay. This is an EUV coronal plume in a coronal hole. The EUV plume is this EUV bright plasma in this magnetic funnel, in the lower reaches of this magnetic funnel that reaches on up through the corona and out into the solar wind. These EUV images and cotemporal magnetograms step through the life of this plume, which lasts about a day. The plume turns on as the foot magnetic flux packs together, and it turns off as the foot magnetic flux spreads apart. That's what gives us our idea for how plumes might work. There's more, the foot flux has more coastline length before there's a plume than when there is a plume in it, and again, more coastline after there's not a plume in it. So if the coronal heating increases and decreases as the coastline length of the underlying magnetic network, then there should be less coronal heating in the magnetic funnel when the plume is in it than before and after the plume is in it. That's what makes us think that maybe lots of the plasma in the plume comes from cooling and draining of the corona higher in the funnel. What do I do? Just, yeah. Okay, this is quiet region corona, imaged by EIT in iron 910 emission. And this square field of view is a half a solar radius wide and centered on discentered. A little of the emission in here is actually coming from low down in the magnetic network, and it can be filtered out with this spatial filter. Then I have to point somewhere to click to make it go, or just, okay. This is what the filtering gives: the large scale corona and the network corona. The network corona traces out and outlines the magnetic network, and it has only 1/20th of the luminosity of the large scale corona. This is the large scale corona and the underlying magnetic network. The white contour here is the median brightness contour of the large scale corona. It divides the field of view into two equal area halves, the dark half and the bright half. The coastline length of the underlying magnetic network increases from the dim half to the bright half by about the same amount as the coronal luminosity increases. They both increase by they're both about 1.4 times larger in the bright half than in the dim half. That they both increase the same, we take as a good sign that the corona and solar wind might be powered by fine-scale magnetic activity at the edges of the magnetic network. This is our cartoon for generating the generation of magnetic waves by tiny flux rope eruptions at the edge of the magnetic network. Each one of these little coils is an erupting flux rope viewed end on in the edge of a magnetic funnel that's plugged into the network. And each erupting flux rope is driving interchange reconnection of itself with open magnetic field in the edge of the funnel. And the interchange reconnection generates a magnetic wave that propagates up and out along the reconnected open magnetic field. This is our cartoon for why the magnetic wave should be a twist wave. The interchange reconnection transfers the twist in the erupting flux rope to the reconnected open field line, and then the magnetic twist propagates up through the corona and out into the solar wind as a torsional alphane wave. And finally, this is our cartoon of the twist wave propagating up and out into the inner solar wind and steepening into a mild switchback. The steepening happens because the alphane speed decreases from about 1,000 kilometers a second in the corona to about 100 kilometers a second in the inner solar wind. That's enough to give you a mild switchback about this, that's steepened about this much, and then maybe shear in the solar wind could make it into a more extreme switchback. So the cartoons outline our scenario for powering the corona and solar wind by little flux rope eruptions at the edge of the network. If that scenario turns out to be true, then we will expect that UV plumes are flags of coronal magnetic funnels in which the higher corona is cooling and draining due to reduced heating. Thank you.
Very interesting. Do you expect to see any flux change in the photosphere as a result of this small-scale reconnection? Is there flux cancellation involved?
Yeah, Nora will talk a lot about that, but that in my cartoon for the generation of the waves, the flux rope that erupts is constructed, results from flux cancellation. There's an embedded island of minority polarity that erupts from.
So in essence, one can put some numbers around. I mean, based on the frequency of the small-scale reconnection or the expected frequency and some tentative values of the energy release and then try to make some energy partitioning throughout the corona toward the solar wind, conceivably.
Yeah, there's a paper that I did about 10 years ago, which did it with type 2 spicules, and I got a ballpark number that was encouraging, about right for the solar wind.
I have a suggestion and a question.
Okay.
Suggestion is that you look at papers by Kumar et al. From 2021, 2022, and 2023, where we actually show evidence for most of this picture. The other question is, how do you explain the fact that we only see outflows in these plumes?
Do we only see outflows in the plumes?
All of the work.
We see outward propagating
All
things.
the work, no, what we've done recently showed that it's actually flows.
Well, if it can be shown that there's only net outflow in the plumes, and then this is not a good idea.
Well, it's the last part. I mean, that's the only part I would disagree with, but the rest of it is very consistent with our jetlet.
Yeah, but the core idea here is there's back draining, and if you can't see the back draining, then it's not a good idea.
Byron, could you go back to that figure kind of at the beginning?
Maybe.
Oh, okay. It was, it was this one. So, so in the central panel, where you've got sort of all that, I guess, white is positive polarity concentration.
Yeah.
I mean, I guess I'm not exactly following your argument here, because I would have thought that, that plume was hotter and more energetic with more concentrated field. And when the field is more diffuse, it's cooler and there's less interaction between, say, those strong flux bundles or whatever.
So many papers have been written on jetlets at the base of plumes, and that's the prevailing idea, that the heat, the power going into the plume for heating has gone up. And this is a suggestion that the opposite is what's happening.
And then where's the flux cancellation happening?
There's no cancellation. So we're imagining that there are these sub-resolution below what Hantao can see that are embedded in there. But the jetlets are seen, and Nor will show all these little neutral lines that he imagines are canceling and making the jetlets.
So, you know, for many years now, people have hypothesized that the coronas, and you know, you've shown a similar picture. However, the observational data in the Earth space environment says that the amount of energy in the Poynting flux coming out from reconnection is an order of magnitude down from the direct heating enthalpy flux that you directly measured by the spacecraft.
But you're saying that the actual lot of energy can come out from the reconnection other than waves, right?
Right.
By particles.
Yes.
We're willing to take all the help we can get from that too.
Right. And let me further state that what we do know about reconnection, both from many simulations and also observational data, that the reconnection process is highly bursty. And that should mean what should be coming out of interchange reconnection down in lower corona is bursts, one after the other, perhaps thousands of bursts in a given current layer from the flux from the reconnection process. And it seems to me...
You mean on a much shorter time scale than a single jetlet? Is that what you mean?
Yeah, we're talking about jetlets because the Poynting, the Lundquist number for all these events in the sun is huge. And if you go back and you say, okay, how many flux ropes do you think should be produced? Thousands of flux ropes, in principle, should be produced in these reconnecting current layers. Okay, so my point is that the reconnection process is very turbulent, but it's not coming out at Poynting flux. It's mostly coming out as bursts of flows, alphanic flows coming from the reconnection process. So my point of view is we should start rethinking what's actually coming out of the reconnection process in light of what we know from direct observations in the Earth space environment, and also it's now starting to appear from the Parker Solar Probe data.
Right, you're saying that most of the energy for heating and powering the solar wind doesn't come from this twist wave that comes out, but actually comes from the energy particles that come out from the reconnection site.
Many people have done the jet simulations, and the jet simulations do show strong twist, but that twist is because of the twist of the equilibrium. It's not because of the twist that was generated in situ during the reconnection
That's
process.
right. That's what we're suggesting. It's the twist that was already in the flux rope that gets transferred and comes out, and we hope becomes a switchback, but maybe your way is what really makes the switchback.
Okay. All right. Well, Spiro.
I just want to say that if you think about the initial energy, the pre-reconnection energy, it is stored primarily in the twist, the stress of the magnetic field. Now, it may be converted to mass motions, but certainly before the eruption or before the reconnection, it's a twist that you're releasing primarily.
Yeah, and I think the prevailing view is that switchbacks are a form of Alphanic twist wave that somehow gets very nonlinear and very distorted.
All right. Well, it's now time for the coffee break, so let's thank the speakers again. Yes, we resume at 3:50. You have about an hour.
controller, middle button to advance.
Okay.
All right, everyone, take your seats, please. All right, gang, here we are, the last phase. I have an announcement. Cheryl has sent everyone an email with a link. So if you have photos that you'd like to upload to the website, put them to the folder in that link, and hopefully we'll get a nice collection of photos of the festivities. So with that, I'll pass off to Erica. Yep.
Your microphone is off. No.
Was on.
Now it is on, okay. So welcome to the last session. I hope you're caffeinated. It's gonna be exciting with 4 talks followed by the prize ceremony, so please do not leave. And we will start with Craig DeForest, who is gonna tell us about
these slides, so this shouldn't take too long. Actually, this is an afternoon talk, so I tried to make it a little lighter, and I hope it's not too far. I pushed the button, nothing happened. There it goes. All right. So this is all about coronal holes, and most of us remember this. Coronal holes rotate rigidly. This is something we should all remember. Over on the right is a figure from Zerker et al. 70, I guess just Zerker, 77. Coronal holes in high-speed wind streams. That's the Boot of Italy coronal hole. And down below, this is another one that NOAA recorded in 2015. You've probably all seen it when it was live. In the one case, you've got 7 rotations, so 7 months of persistent structure. And in the other, you've got 4. And what's remarkable is just how little these coronal holes change, despite the fact that we all know the sun rotates rigidly. So it's sort of like, what did I say? Oh, differentially, not rigidly, not rigidly. The coronal holes are rigid. So something's going on. Here's the sun rotating differentially. This is an old movie. There's lots of ways to demonstrate it. So this is a derotated MD high magnetogram sequence. And if you watch as it comes around again, you'll see, whoop, do it one more time. There you go, thank you. Yeah, hit go, there we go. You can see that the pole is rotating to the left and the equator is rotating to the right in this co-rotating frame. So the sun is actually twisting up. And over on the right, you see the results of just 1 rotation's worth of rotation, that meridians are really twisted out of shape. So the fact that the coronal holes are rigid is not just a coincidence or an accident. There is something making them stay rigid. And this is, again, old hat. We all know this, but it's worth sort of going back to the basics every once in a while. Is that working? I'm not stupid, really. All right. Okay, so here's the Boot of Italy again, just for contrast to what happened with the coordinate system with the EIT image. All right, so we all sort of know, we now call this interchange reconnection. Everyone talks about it. Over on the right-hand side, you can see a figure that I just stole from a recent paper by Fisk and Casper. But these kinds of diagrams are all over the place. You have an open magnetic field line. Let's see if I can make the other thing work. Oh, look at that. You have an open magnetic field line. You have a closed magnetic field line. They reconnect, and which one is open changes, right? And meanwhile, some perturbation goes propagating out. In this case, a switchback, because this is a recent paper. And then over on the left, there's some global effects that happen when these kinds of perturbations get out through the Alphane surface or the Alphane zone, what we used to call the Alphane point back when we all thought in 1D. So signs of interchange reconnection, there's been a whole bunch of work on demonstrating the interchange reconnection really happens, not just through these indirect measures, like the fact that coronal holes are rigid. There are universal jet events, right? We've heard about how jets work. Judy and I and Rick and many others have written papers about how ubiquitous jets are and how important they are to the dynamics of the low corona. This is a figure from a Rawafi et al. Paper on 2023, just sort of showing jets repeating. This is a time axis plot along a slit that's right here, this diagonal thing. Just sort of showing that these intermittent releases are all over the place. In fact, we just heard Nikki Weil talking about how important these are to the structure of the solar wind and the mesoscale structures that are released. Over on the right, you can see now that we can actually sample the corona in situ, we see the magnetic field reversing a lot, and that's a sign of these sort of Alphane waves going out that, well, people are still arguing about switchbacks, but one idea is that when you have a jet going off, it releases this perturbation, the perturbation grows, and then all of a sudden you get a reversal in the magnetic field. And that's actually captured over here on this diagram on the left, that you let stuff go. Here's interchange reconnection happening down in the sun, and on a global scale, you sort of get these S-shaped curves going out. All right, so far so good. What's organizing the interchange reconnection? Interchange reconnection is all well and good. That's sort of like saying your car can move, but how do you know which way to point the car, right? All the cars in traffic are going more or less the same direction. Something is organizing that flow to make sure that it's consistent. Well, we used to think it might be something to do with the magnetic carpet, that is to say the small-scale magnetic field of the sun. That doesn't work. It's pretty well known ever since sort of the late 20th century that the small-scale magnetic field, the salt and pepper field, this goes back to work, I learned about this from Alan Teitel, but there have been plenty of folks who've worked on this problem. The small-scale field doesn't seem to really be organized in any global way. Stuff emerges and moves out stochastically, and I'm now talking about things that are happening on the granular or maybe even the supergranular scale. The motions are sort of random and they move around existing flux. That's how we get the diffusion term that we use in nice things like the ADAPT model. So that's not structuring the corona. So what is? Well, we know that there's reconnection happening in the corona. On the left here this is about a 10-year-old simulation that we did of what happens in the corona if you turn off reconnection in the corona. So here we're driving this with a model of the small-scale field emerging on this granular scale and drifting around. It's about a 50 megameter piece. And the only reconnection in this simulation is happening at the bases when two flux concentrations collide and cancel. And what you find is that the corona looks nothing like the real corona. It's just tangled up and horrible. Over on the right, you have a picture, a single frame from that simulation showing there's a flux concentration. You can't really see it behind all the field lines in the middle. And the question is, how much does the flux from that flux concentration spread out? And it turns out it's a lot. So clearly there's something happening in the corona to keep the corona braided. And that sort of leads to what's going to organize the thing. You need a small perturbation. And so I like to call this the vibrating football model of the corona. The idea is, how many of you have played vibrating football? Right? All the old guys. So you have a table with a buzzer under it, and it shakes the metal of the table and just provides energy that's sort of stochastic and randomized. And all these little toy guys that you line up on the field have an asymmetry built into their feet. And as a result, when the table shakes, they sort of move around in a coherent way, and you can have endless fun. You can see the guy pounding the table, trying to get his team to do the right thing. This is a good analogy for what's happening here, right? You have all this excitation happening in a random way from the photosphere, and some organizing principle. It doesn't have to be strong. It can be a very small asymmetry, is enough to steer the overall drift of the field lines through this stochastic mess of the magnetic carpet. So we now have a name for this. It's the S-Web, right? Back in 2005, I was doing some work on what orbiter would see, and we talked about how cusps, as you integrate outward, turn into bifurcations as you integrate inward. And this means that magnetic structures on the surface of the sun are preserved in open field regions like coronal holes, but they're completely scrambled. And that's what this figure over here is supposed to be showing you, that there's these coherent structures that survive from the middle of a coronal hole. But down here in what we now call the S-Web, they're just scrambled because in order to get back to the surface, you have to integrate through a bunch of bifurcations. And so the S-Web sort of does that, right? This is a figure from a certain paper by a certain guy. And out here in the outer corona, you have all these domains that then go in and bifurcate and become different domains in the interior. This is a coronal hole over here on the left, hidden behind this wall of green. And so in this region in here, you can expect that the field approximately preserves lateral structure, whereas in here, in here it's totally scrambled. And so maybe what's going on is something in the outer corona is propagating in to steer the reconnection in the coronal hole. What could that be? Well, a while ago, I had a conversation with Spiro about a thing called helicity condensation. But I didn't know what helicity was, and I had to go off and study it. And if you are like most people, you probably either have studied it or you're kind of going, well, what is that stuff? It's linking number. So down here at the bottom, we've got a bunch of topological diagrams of discrete rings that are linked in various ways. And the linking number just tells you the number of times that the rings twist around each other. And so helicity is a generalization of that. It's linking number density in the field lines. So if you have a collection of field lines, like a horse's tail or something, it measures the density of linkages, how tangled that tail is. Well, scaled by the line. Scaled by the value of the lines. Weighted by, I should say, by this, yeah. So we don't have the complete magnetic field lines at our disposal. We have a photosphere below, and so there's some mathematical tricks that we use to avoid having to think about what's under the surface. I'm going to sweep those under the rug, but now you know what helicity is. It's really just this linking number, sort of. It's not a perfect measure of tangling in the corona. It's only good enough. And there's some weird cases that over here. The Borromean rings have no helicity or no linking number, even though they're linked to each other. And there's this thing called the unlink that sort of goes back and forth, and the linking number is 0, but you can't separate the rings. There's weird edge cases like that. So you just got to be aware. But helicity really is just linking number, sort of. So this is, again, from a certain paper from a certain guy. It's about helicity condensation. The idea is you have these large closed domains here in the corona. There's reconnection and twist going on. They're all twisted in different ways. And when they twist in opposite directions here, reconnection is less likely to happen because the field, the transverse field anyway, lines up at the place where they interact. And if they have like sign, then they're going in opposite directions where they interact, and so they're more likely to reconnect. That sounds like a subtle asymmetry to me. And so I got very excited, and we spent several days talking about this over the span of a couple of months. And so the idea then is you have, if you have a bunch of domains that are all sort of coming out and they're randomly twisted, eventually the helicity that's in here, the twist, will spread out and around to the outside. And it turns out this is a great way to concentrate helicity and to make things like filament channels happen. Really neat stuff. It works pretty well with coronal holes too, and it explains a bunch of stuff that we see around the polar coronal holes, right? So if this is a polar coronal hole, and out here is this sort of polar domain, all the helicity condenses out to the edges. In the coronal hole, it's free to leave. It's just an Alphane wave, and it goes all the way out. So you can sometimes get an opposing, and in fact here in the diagram, you've got an opposing line here. And so you get lots of shear in here, and there's lots of neat stuff you can do. We actually see this. This explains diagrams like this one, where this is from a Gibson et al. That you may be familiar with. This is from a Howard and DeForest that may be less familiar, where when you have a polar coronal hole, whoa, right there, you generally have a little gap of closed field, and there's often a polar crown filament right next to it. So this is a handy way of explaining how polar crown filaments come to be. This figure on the right is here specifically because this paper marked a high point in my career. It was at the MSU SPD, and I got in an argument with Spiro in public. Some of you were there. And I waved this paper over my head. You need to read this paper. And Spiro threw it in the trash. I'll put this where it belongs. So anyway, you should read this paper, Spiro. Now you can't claim not to have seen it. It's all about how we formed a coronal-hole based crown filament, and then it erupted later. It was exciting. All right, so condensation, I want to point out, is a symptom of inhibited reconnection in the low corona, right? If you could reconnect past the edges of that domain, then the helicity would condense farther out, right? It would continue to spread. And so the fact that you have a boundary beyond which it doesn't condense and you get these shear lines is a symptom that you're not getting a lot of reconnection across that boundary. So this is a really interesting process, but it's not actually why those extended coronal holes are rigid. It can't be, right? It may contribute to polar coronal hole structure, but it can't contribute to things like the elephant's trunk or the boot of Italy. Here we go. Also, shocker, there generally isn't a filament channel right next to these long longitudinal extensions. So we got to do something else. Some other asymmetry is propagating down and informing the surface what to do. So my idea, which we'd like to explore, is that it's the Alphane zone or the Alphane surface. The Alphane surface is, you've already seen this diagram, an imaginary surface outside most of the corona where it's the locus where the wind speed exceeds the Alphane speed. What we found with the 18 work with Core 2 is that the density variation is so great out there that you don't really have a clean locus, right? There's a zone where you're sort of above the Alphane point at some frequencies and below it at others, and it's almost fractal. So that's why we call it the zone. So down here, this figure was originally all about conservation of open magnetic flux in the heliosphere. That the only way to reduce open magnetic flux is by launching U-loops out through this surface. You can't bring anything in through the Alphane zone. And so any disturbances, including morphological disturbances, that are at the Alphane zone can't get back to the sun. What that means is from the standpoint of global dynamics, it's a rigid surface. And so this is a natural place to organize coronal holes out at the Alphane zone. This is a map of the Alphane zone that Rohit Chibber made back in 2018 using a simulation that matched some of the stereo work we've done. Right on time. So line tying at the Alphane zone kind of fits the bill to direct coronal hole evolution. It's a very subtle process. It can direct very small asymmetries in the reconnection rate back down. They can propagate down at the wave speed down into the low corona and just sort of perturb the overall distribution of directions. Unfortunately, nobody's really studied the Alphane zone in detail because up until now, it's been very hard for us to measure it. There's lots of models. They all disagree as to even how high it is. But we've only recently been able to detect it. So I tried with stereo back in 2014. We didn't find it. We just found that it was above the altitude range that we were looking at. Parker Solar Probe has recently flown through it. Most of you are familiar with this paper by Justin Casper, showing that the important plot is this one right here, the dark, which is the Alphane Mach number around the spacecraft, and it drops below Unity in a couple of places that are marked here in gray on this screen, but maybe don't come out clearly on that screen. Those are places where Parker Solar Probe actually entered the corona proper, not the solar wind. That was a big milestone for the mission, but also marks that we can actually detect this topological boundary in the heliosphere. And of course, I'm very excited for Punch. You knew I was going to talk about it. Nikki gave you a preview. Punch is here to unify the kinds of analysis we do. We're bringing imaging data out into the heliosphere, just as Parker Solar Probe is bringing in situ data into the corona. And so what one of our working groups, one Charlie and one C, is specifically devoted to analyzing the structure and dynamics of the Alphane zone. And the instruments are designed specifically to be able to measure inbound waves and other disturbances as they propagate near. So I'm hoping that we will be able to put this to rest and either determine that yes, line tying at the outer reaches of the corona is profoundly affecting the inner parts of the solar atmosphere, or it's not, and something else is doing it. So in summary, coronal holes have too much integrity, maybe like Spiro. Organized interchange reconnection has to happen at the boundaries. The most obvious things that could organize it don't, meaning small-scale emergence and so forth at the surface of the sun. Helicity condensation helps, can't account for the organization. Some other effect is propagating order into the sun itself. The tail is wagging the dog. The weird constraints imposed by the Alphane zone might do the job, and of course we'll deal with this on Punch. And this is all deeply tied to Spiro's work on topology, which sort of got me going on these topics in the first.
First, we have to ask if Spiro has a question. Do we have a question, Spiro? No. Very good. We will give it to another Greek then.
Thank you, Erica. Well, Craig, helicity is known, magnetic helicity is known to exhibit what is called an inverse cascade, contrary to the energy, namely to spread out in larger scales.
Right.
Now, my limited understanding of helicity condensation is that it's called helicity condensation because it has an effect of like condensing in small scales, pretty much like energy. It's not that.
I'm going to refer you to my friend Spiro
So
Antiojos.
what do you think happens here? Because I'm a bit confused.
So in fact, it came directly from lab plasmas, where it condenses to the largest scale, into the largest wave number. The name was actually taken straight from turbulence theory. So it goes to the largest scale. It goes to the boundary of your laboratory system. It doesn't mean it goes to the small scale. No, it goes to the opposite direction.
So it is an inverse cascade after all.
100% inverse cascade.
So what's
And
the difference then between what we know about helicity, the classical?
Like I said, it's the laboratory people some years ago said they see helicity going to the largest scale. The turbulence people have argued for years that it was an inverse cascade. And they termed that the condensation, the formation of this structure at the edge of their machines, they termed that formation process as a condensation of helicity at the largest K. So I just use the same terminology because I hate this business of people renaming a known phenomena, right? Now, I have gotten a lot of grief from that. So why'd you call it that for? Well, because I'm just using the terminology that's already there rather than, pretending that I came up with something new.
Is it a very quick question? It's not very quick, but you can try. Is it a quick question?
It could be. Okay, it's very simple, maybe stupid. If the tail is wagging the dog, line tying out at the Alphane speed, how do I understand how coronal holes change with the solar cycle, and when we have a lot of mass ejections that are interacting with the overlying field, how do you maintain these large scales?
That's a really good question. How is it that coronal holes can change if they're being line tied? And the answer is they're only tied on short time scales, right? On longer time scales, you have reconnection and U-loops emerge through the Alphane surface and change the pattern of open flux at that surface. And so you expect that the line tying pattern would evolve on the time scale of the dynamo itself. It's only on short time scales you expect it to be tied. Short meaning order of a few months.
All right, thank you, Craig.
Thanks.
We will move to Nick, who is no longer Nikki. Now Nikki is called Noor. Solar wind plasma. And you can see there is a Parker solar probe animation in the background.
Okay, thanks.
Floor is yours.
And first, I want to apologize for the disruption of the schedule, and I want to thank Nikki for filling it for me, like always. So I did not have the privilege to work directly with Spiro, but when you come in as a young student and, you get into these conferences, you start seeing these prominent folks, and there are just a handful of them that you cannot miss. And one of them is Spiro. And what you see about Spiro, I think the first impression you get about him, yeah, he's very tough in his science, he's very tough in his arguments, and sometimes he gets into these big arguments with people. But the fact of the matter, as you get to know him, you really find out that he's the embodiment of the true gentleman. And he cares, he helps, and sometimes even when you don't ask for help, he knows when to step in and help. And the nicest thing I really appreciated about him, when you go to him to ask him to do something for you, you actually don't tell him what to do for you. He will actually find it himself. You just tell him what is the situation. He tells you, you know what, this is what you need, and blah, blah, blah. And he will go and do it. And going back to these conferences, sometimes I think one of them stands out to me. It is the chromospheric and coronal magnetic fields that Sami Solanki organized in 2005 at Max Planck. And I think Spiro gave his invited talk. It was in the third session. There was something, I forgot what it is, that he didn't like about the session before. And anyway, Eric Priest made a compilation, who said what during that thing. And so this is the quotes from Spiro. And one of them that stood out to me, he said, "I'm not sure I like the kink instability." So it's something like that. And after his talk, there was a huge debate, really big debate. And I loved it. So anyway, here comes Ineke and said, and the audience was really breaking out, and it was warm. She says, "It may be a good idea for me to speak so that the audience can cool down after Spiro." And the other one that came afterwards is John, and he said, "I'm agreeing with Spiro, which is disheartening," which is really, really nice. So I had to dig out this presentation from 2005, which is, yeah, it's a nice one. Anyway, going into to the talk, this is the structure that I'm talking about, and for this audience, I don't need to explain them at all. The magnetic field network, jets, which are the impulsive feature, we see them in X-rays and EUV, and coronal plumes that are prominent at the poles, in particular during solar eclipses at the minimum. So these are the main three structures I will be talking about. And when I came in, it was the SOHO era, and Sumer and UVCS introduced the controversial topic, that is whether plumes contribute to the solar wind or not. And there was two camps. One of them, they say, yeah, they are main player in the solar wind. The other one, they said, they are not a player at all. And the heart of the controversy came from the fact that when you measure the velocities of plumes lower down, some people reported high velocities, some people reported very low velocities. So I developed a simple code, and I kind of thought, yeah, I solved the thing. I said, you know what, you can start with low velocities, and the plasma will accelerate and will catch up with the entire plume, and that will solve the whole thing. But that actually triggered something to my mind. It's, okay, what if we have really high speeds within the plumes themselves? And I start asking myself, how does a plume form? And I started looking at some data from stereo. And the first event I found is this one here. You see it there. What you get initially, you get a jet. And after a while, you see the plume haze raising about here. This is the jet is in this panel here, and after that, you get the plume. And then I collected dozens of them, and every single one of them starts with the jet first, and then you get the plume. And that was the first paper basically linking jets to plumes. And by the way, historically, when you look at jets and plumes, they look totally different. Jets are impulsive, they are sharp, they are pretty fast. Plumes are hazy, they are sluggish, they are not really that fast. So, but this one actually gave a very first hint that they are closely linked at least to a certain point. And by the way, jets also occur while the plume is ongoing. That's also another thing. So from that paper, Marshall Nigebauer used that argument to solve an old controversy as well about microstreams in the fast solar wind that is measured by Ulysses above 2 AU. Then she said, okay, if we have jetting within plumes, then we can explain all the properties of the microstreams. So that's a kind of... But then came SDO. Until SDO, we did not have high resolution and high cadence of data. And when you take the SDO data and you really filter it well, then the haziness of the plumes goes completely away, and what you discover is totally a new nature of the plumes. What you discover, you will have a myriad of a small impulsive ejection of plasma within the bottom of, at the foot points of plumes. They look like jets, but they are very small, and that's why we call them jetlets. But they are, I think we think they are just jets. And that hazy nature of the plumes, as you see it here, it becomes highly dynamic, except that you have to filter your data. Because you have to take that background away, and after that, everything is... but so far, that study in 2014, that was the first paper about these jetlets, and after that, there are a series of papers by Navdeep Panisar, Pankaj Kumar, and Vadim Yukursky. And all of them either dealt with plumes or with a limited number of jetlets. And after that, once we got the data from Parker Solar Probe, in particular about the switchbacks, and we were wondering what is going on, how the switchbacks form, and there is one hint in particular that I will come to in the next slide about it, but let me first of all say what are the problems that we want to solve about the solar wind. So basically what we want to understand about the solar wind is what are the processes that gives birth to the solar wind at the source, which is the base of the solar corona. That's one fundamental question. The other question is what is the nature of the solar wind at the source, whether it is continuous like the wind we measure around 1 AU or it is intermittent, because this is so important because the physics is totally different. And obviously the big elephant in the room is how can you get the plasma to escape the solar gravity? That's the big thing. Now, so let me list a few facts and what we can, what conclusion we can draw from them. When you look at the solar wind, and by the way, this also some of these arguments apply to the coronal heating as well. The solar wind is by nature a global phenomenon. So the source that is driving the wind has to be global as well. I think that should be evident. The other thing also, when you take solar minimum or solar maximum, the solar wind is always there. Even when the sun is completely quiet, no active regions, the wind is still there. That tells us one thing, that we can rule out that active regions are the primary source of the wind. They contribute to the wind, but they cannot be the primary source of it. And then the other thing, I think we have it from the remote sensing, but also we have it from Parker Solar Probe, is the structuring of the wind. The wind is organized in a way that it cannot be driven by a random process lower down. It has to be driven by an organized process lower down at the source as well. And the other one, okay, when we go back to the quiet period of the solar cycle, when we don't have active regions or anything, all we have is the small-scale magnetic field and the activity that is associated with them. And that could be the smoking gun that probably will lead us to what is where the wind is coming from. Anyway, this is the switchbacks from Parker Solar Probe that I think we saw them multiple times here. I will not go through this, but this is what is really important about the switchbacks. They are not random. They come organized. They come in patches, like this one here, or this one here. And the two papers by Nais Farjet and Stuart Bale in 2021, both of them, they found something that is very curious. They say, okay, the scale size of the switchback patches correlates so well with the scale size of the supergranules. And that's another hint. Probably the switchback have to do with what is going lower down at the base of the solar corona. There is another thing also, that the wind that is measured by Parker Solar Probe close to the sun is abundantly alphanic, regardless of the speed. Whether it is very slow, medium, or high, it doesn't matter, it's alphanic. And that's probably another hint also that the wind by nature is driven by the same mechanism. But the evolution later on will separate them from, some of the wind will lose its alphanicity. Now, going back to the remote sensing and trying to figure out what is going on at the base of the corona and understand if there is anything that might that might be related to the switchbacks that Parker Solar Probe are observing. And this is a movie that is playing, by the way, but this is kind of almost raw data from SDO. And when you look at the off-limb, you basically don't see much at all. It's very, very hazy. And the reason for it is there is a huge background in the data, and that's why you don't see much. Now, if you filter your data really, really well, you start seeing the stuff you want to see. And here, this is the full thing. What we were focusing on is basically the off-limb here. And you can look at any time during the solar cycle and you will see exactly the same stuff, like the solar wind. Here, what I did, I just made a zoom of the northern pole. And what we are seeing jetting all over the place. It's very clear when you see it above the poles here, but even in the quiet sun, you still see it. It's there. When you go to the streamer region, it's a little bit more difficult to see it, but if you focus enough, you can see it. So this jetting is ubiquitous. And this is, I think it was four of us when we first looked at this one. It was Guillermo Stenborg, Greg DeForest, and Dan Seaton. And when we looked at it, we said, yeah, probably this is a solar wind. We are actually seeing the solar wind rising from the base of the solar corona. And then we went on and we looked at what might be driving the whole thing. Obviously, we were thinking about reconnection. And what we got is this high-resolution magnetogram from the Goody Solar Telescope at the Big Bear. The resolution is 0.2 arcsecond, and the field of view is 70 by 70 arcsecond. And over 90 minutes, what we found is there are over 1,400 cancellation pipoles. And by the way, this region here, this one here, it's a Coronal-hole. This one is quiet sun, and they are separated by this network element here. So lower down, you see absolutely no difference between the Coronal-hole and the quiet sun. So among these 1,400 cancellation events, there are about 60 of them, they were rooted in that network element, and 7 of them, they produced EUV jetlets. And we calculated how much every jetlet will produce in terms of protons, but also the energy as well. And that based on their lifetime, their sizes, and assuming that there is, have an idea about the density there. So now the big question was, we are seeing the jetting all over the place. Whether we have enough, I'm almost there. So whether we have enough jetting to account for the whole solar wind. And that is, it's a big thing. We went through the numbers, and by the way, the team grew from 4 to about 20 people that got involved into this. And what we found, okay, if you want to drive the whole solar wind, you need about 2,000 jetlets going at any given time. And you have to also create 6 jetlets per second at all the time. So that's the rate of production of jetlets. But when we went through the statistics of our, we are getting from the data, the magnetic field, but also the EUV, instead of 2,000, we actually find 4,000 jetlets that are going all the time on the sun. That is way more than we need. But that's actually probably what we need way more, because there is a selection effect that not every jet will make it to the solar wind. Most of that material has to fall back to the sun because it cannot beat the gravity. It cannot beat the gravity. So having more jettings is way better. And by the way, even this number, we believe, if you go to higher resolution, we should even see more jetting than what we are seeing here. Here we are limited by the resolution and the cadence of SDO. So this is the conclusion. I think it's pretty much said everything about it. Let me go to the selection effect that I talked about. And this is something that Stuart Bale did, and he still have to write the paper. It's been 2 years now he's trying to write the paper. Anyway, what he did, he took the different encounters, and he drew a line tracing the minimum speed that Parker Solar Probe measured around the encounters. And after that, he organized them, put them into this plot here on the right-hand side. And what you can see that most of the wind is dominated by jetting in situ. And the funny thing is, it is on the lower part of it is limited by a Parker-like wind. But above it, it's all jetting. So, and that's why the selection effect idea came from, that you produce a gazillion of jets lower down. Some of them will make it to the solar wind. Some of them will have to fall back to the sun. I think this is all I had to say. I'm not sure if there is any. By the way, yeah, there is a lot more to say about that. So since, how many minutes do I have? So, including questions or not? Without questions, good, okay. So the nice thing about this jetting scenario, so in coming back to the switchbacks, so switchbacks, there are basically, in 1 year, I think there are 5 models of switchbacks that were published. And you can put them in 2 categories. There are models that argue for coronal origins, and most of them are based on reconnection. So yeah, if we have magnetic reconnection that drive jetting, that's obvious. So that's actually fulfill the requirement of this type of models. But also there are other models that require either steepening of alpha waves or shear or shear. And the jetting will produce all of them. Magnetic reconnection will produce alpha waves that can propagate higher up and steepen into switchbacks, but also because you have impulsive jetting, that will create shear as well. That's, in a way, the scenario of the magnetic reconnection jetting fulfill all the requirements for almost any model you want to consider for the switchbacks. Thank you very much.
Questions? Dun, 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 dun.
Thank you. Noor, the emission from active regions has 2 components, a diffuse component and a distinct loop component. And many people don't realize it, but the loops are really just very modest enhancements over the diffuse component. So there's more emission in the diffuse component than in the loop component. You pointed out that at the poles above the limb, things look very diffuse until you do filtering. Does that mean that there's more emission in a diffuse component than there is in a distinct, plume component? Or not plume, but,
Well, the diffuse component has to do with the nature of the corona itself. The corona is optically thin, and you are integrating along a huge line of sight. And the thing is, even when you take small jets or whatever, if they are on the foreground or the background of the plane of the sky, then they are way higher up from the solar surface, and they will lose a little bit of their sharpness. And that will create this diffuse background in a way. But when you remove it, at least the way I think, by removing the background, you are reducing the volume that are that creates this sharp thing to almost the vicinity of the plane of the sky. That's what we are doing by
So you believe most of the emission is really contained in distinct jetlet features and not in some diffuse component in between.
Okay, now you are touching really on something. Higher up, yes. In the solar wind, yes. I think that's whatever succeed to escape the solar gravity, I think those are individual events. And obviously, they will be homogenized by turbulence to form the continuous solar wind later on. Lower down in the solar corona, actually, most of the material is hanging in there. And that's why measuring the velocities lower down in the corona is so tricky. It's not easy at all, because it's like you have a huge fog in front of you, and within the fog you have these jetlets. So most of that material that is hanging there has to fall back to the sun, and that's probably what is happening.
That kind of gets at what my point is really, is that that fog flowing outward to be part of the solar wind?
I doubt it. I really doubt it.
Tom, do you promise you have a very quick question? Okay, go for it.
Okay. Noor, has anybody analyzed the 12-second AIA data? I noticed your movies were high cadence, but they weren't at 12 seconds.
We looked at the 12-second, and we looked at them, but we found out that even if you do 1 minute, it's still good enough. But we looked at the 12-second, and we looked at multiple wavelengths. What we have to do now is maybe to go to EOI. When we, particularly when we are very close to the sun at 0.3 AU, the resolution is much higher there. And there we will see way more stuff than what we are seeing with AIA. Yeah.
Let's thank Noor again.
Thank you.
Next, I believe, is Igor. Thankfully, I read the program before, because I don't have anything here. Without my cigarette, I'm suffering, I'm telling you.
So, Spiro.
Who is going to tell us uniquely about Spiro, and whether Spiro is also an essay in 2 parts.
So, Spiro obeys scaling law as illustrated above, so he is somewhat smaller than the sun, but definitely greater than the Earth. So this presentation is a tribute from Michigan. The title is Spiro Awesome, is trivial if you consider the literal meaning of this misspelled word. So of course he is, however, awesome can be also spelled out in 3 different ways, and this is what my talk is about. And there is a single author of this presentation. In fact, there is quite different single author for this present to delegate the sole responsibility for his inappropriate jokes. So one of the ways to spell out the word awesome is some long expanded monarch title. So he is monarch, Spiro is monarch because he has a scepter. What is scepter is explained in several words below. However, even prior to, even before scepter, so even before scepter, Spiro started the history of his devastating collaboration with the Michigan about 2 decades ago. So he started to work with Zurbuchen, of course fired from Michigan, with Len Fisk, of course retired from Michigan, and with Ben Lynch. We all know Ben Lynch, so he is now very, very far from Michigan. So, however, in a while, Spiro teamed up with Tamás Kambosi, and they won 2 consecutive NASA LWS Strategic Capability Awards. The second of them is Scepter. So you know, as the result, Tomasz is still sort of negotiating his retirement package, but this issue is almost resolved. So another way to spell out awesome, in this case, OM is a trivial suffix of Michigan. So Spiro is now a research professor at University of Michigan, started from year 2021. So the first 2 years, everything was fine. Then, thanks to him, Michigan won the national championship in football, and Spiro immediately fired Jim Harbaugh. So, however, with all these adventures, there is yet another way to spell out the word awesome. So, awesome is Alpine wave-based solar atmosphere model. It was mostly developed under these two grants. No need to say that now it is retired. And this is what I mostly will talk about. So what we will have instead, if any. So awesome model. The awesome model is mostly based on two equations for energy density for Alpine waves propagating parallel and anti-parallel to the magnetic field lines, which are quantitatively described with the function W plus and W minus. The equations for them describe the advection with plasma speed and with plus minus V Alpine speed. The equations also account for the work done by the Alpine wave pressure. The equation occurs the interaction between the modes and the dissipation. The reflection is pretty small in the coronal-hole, which explains the main feature of the model. On one hand, this model is considered to be the only source of coronal heating and solar wind acceleration, and on the other hand, it naturally describes the bimodal structure of the solar wind with this to this model, because in the closed field region, as you can see in the picture, there are two counter-propagating waves, and the interaction with dissipation and delivering the energy to plasma heating is more significant, while in the coronal holes the reflection is pretty small, and therefore the waves can propagate to a larger distance without dissipation and accelerate the fast solar wind. And this is what explains the bimodal solar wind in our models. So two words how we incorporate the features into the MHD equations. So in black, what is presented here are the usual MHD equations written in the form of conservation laws, and in red, they are features adding with awesome model. So there is an isotropic pressure due to Alpine waves in the momentum equation. There is energy dissipation in the equation for waves which hits electrons and ions, and the total of these equations with some weights gives the energy conservation law, which emphasizes the self-consistency of the model. And why do we need to go further away? This is because if we first want to generalize the model to even the nearest outer heliosphere, then we find that the models for turbulence exist for this region, but this is not quantitatively, not even qualitatively, it is ideologically different. So the turbulence is characterized in quite different ways. It is not clear how they can be, is there any correspondence between the two approaches. And usually when we are talking about the expanded model, it is usually, people usually use the Reynolds decomposition, so the field is split for regular and turbulent part, and the bilinear correlators come to the equations, to the equation of motion. If needed, it comes to the equation of induction, and it is very elegant that the pressure or the back reaction of turbulence on the plasma motion becomes anisotropic. So the turbulence along the magnetic field is due to the gradient of magnetic field correlator, while the pressure in the transverse direction is due to the extra effective gas kinetic pressure, which, so it is characterized by different components of the turbulent variables, and still this is this description is self-consistent, and with some extra work we can derive some model which has the advantage that near the sun or in the inner heliosphere it entirely comes it entirely becomes the entirely reduces to the awesome model, while at larger heliocentric distances it becomes the usual model used for outer heliosphere, and which is even more important, the estimate for the magnetic field correlator, which may be derived from this model, is what is directly applied as the characteristic for particle transport. Oh, sorry for the distraction. Where is Spiro here? So Spiro is not at that business. So this is cartoon. So this sort of demonstrates some management principles. So there are two cartoons from Sophie Masson et al. Paper at year 2013. So at the left panel, there is a demonstration that there is some flux rope, and there is some null points below this flux rope, and only when the reconnection occurs below this flux rope, it sort of disconnects from the overarching field and starts to race, and this is what is the CME eruption about. Well, so this is how we sort of following this instruction. So at the left panel, there is a picture from my paper with Tomasz at year 2023. So this is finite beta configuration, which is superposed on top of the realistic active region, and you can see that below there are some pronounced X points, exactly what are present in the cartoon above. And in order to get the first stage, which was demonstrated at the left panel in the previous slide, we need to check if our configuration, despite the presence of these X-rays, null points below, can still survive for a while in order to demonstrate some stable behavior before the reconnection starts and before the eruption occurs. So how can I? it starts. So this is the full solution of MHD equation with no magnetic friction. So it demonstrates that what we superposed is very close to model the state prior to eruption, and which is ready to cause magnetic connection somehow, and to cause eruption afterwards. So this right panel presents the movie which is done by Shanyu Liu, who is our PhD student. It was done upon request from Spiro, so Spiro loop is closed, and my presentation is over.
Yes, our monarch.
Do you want to get fired? No. So I just want to make a general comment here, Igor. This shows a stage where we are in our field. We spent the last 10 years or so developing tools, very powerful tools, for space weather because, we're paid to do that. So now is the time to use those tools back for basic science. And we have these capabilities, let's use them for basic science. That's exactly what this is all about.
Else first?
Is there someone else who is not Jim?
Everybody here is Jim.
Can you imagine the world if everyone...
Oh, what a wonderful place. Oh, my goodness. So, first of all, Harbaugh's a cheater, so good riddance to him. Who understands that? Anybody? Nobody understands that? Oh, okay. No sports fans here. He was creative, that's true. I just want to make a point that any model that tries to predict emission must include a spatially resolved transition region. Is that part of this new model or not?
It is. So this is not a picture which I prepared but we now have the pictures like full 3D image in different EUV lines, which can rotate together with the sun, and shows corresponds to different images corresponding to different time. And you are right that this is what we mostly need to do. So, for example, again, another picture which I did not demonstrate. So, with this finite beta feature, we have as a natural consequence that in the initial state we already see a shaped feature in white light.
We'll be at the iSWAT meeting.
More questions? No? Let's thank Igor again. And now to prove that Jim was lying, I'm not doing well without the cigarette because, in fact, the speaker was supposed to be Sophie, not Igor. I called the wrong speaker. So now we go back on track. Yes. The next speaker is Aleida. No.
Okay.
Will tell us about...
In my stay at Goddard, I worked with Spiro as a NPP postdoc under his supervision, and we worked on CME modeling and how we can get flare-accelerated particle escaping into space while we have CMEs. But I think we talked enough about CMEs yesterday, and so and because Jim and Judy put me in the SolarWind session, I'm going to talk about the S-Web and interchange reconnection.
Okay, so we already hear about the S-Web this afternoon. So Spiro's S-Web theory is basically that you can map in the heliosphere the open closed boundary that you have in the solar corona, and it gives you the perfect environment to get interchange reconnection, to release plasma flows in the heliosphere, to generate the slow wind sources, and it also allows you to get plasma at higher altitude in the solar wind. So if you, right, okay, so you have the heliospheric current sheet here, and you have all the separatrix arcs that you have here, and that extends basically the region where you can get the plasma flows into the heliosphere from interchange reconnection. So the idea after that brilliant idea from Spiro is to investigate the dynamic of the open-closed boundary in the S-Web model. So before I go on, I should specify that we have two ways of getting those arcs into the heliosphere. So the first one is to have a narrow corridor. This is the first picture here on your left. And those arcs can also be formed with pseudo-streamer topology. The main difference between both is that narrow corridor, there are QSLs, and pseudo-streamer topology, they have, in fact, open-closed separatrices, which is opening up into the heliosphere. If you want details on how you form the detailed web of those separatrix and quasi-separatrix, I refer you to the paper of Scott et al. 2018. Basically, they explain you how you can associate narrow corridors, pseudo-streamer, and null points to form those arcs. If we looked at observations, we have a lot of evidence that we see them at 1AU, so there is a lot of variability, and we can link what we observe in situ to what happened in the solar corona. But we also have direct evidence that we have interchange reconnection in the solar corona. So this is an example where you have EUV observation from AIA, and you basically see that the open bright loops here are reconnecting at the current sheet here, and they are opening into the open corona. We recently got a really nice paper out where we basically, Chita et al., they identify some plasma flows going out from the LMSAL topology that you have here, and also pseudo-streamer topology that we have higher up here. So we have observation that we have interchange reconnection that launches plasma flows into the heliosphere. So now that we know that, we want to know how the dynamics of interchange reconnection is developing and working in the S-Web model. So the first work that has been done are to study dynamics of interchange reconnection in narrow corridors topology. So this is a work done by Higginson et al. In 2017. And so they built narrow corridor here. So you map the narrow corridor here at the solar surface, and it created you the arc in the heliosphere here. They applied a rotational flows at the boundary here. And what happened is that the field lines, the callout field line that you have here, they were initially closed below the LMET streamer, and through interchange reconnection along the open closed boundary of the streamer, they opened into the heliosphere. They also looked at the heliospheric signature of this opening field into the heliosphere. And so what you're looking at here is that the accumulated total open flux in the heliosphere. So this is basically the heliospheric current sheet that you see down here, and you see that the field is opening actually all along the arc. The next works that have been done to understand the dynamics of the interchange reconnection in S-Webs are how we can get interchange reconnection in pseudo-streamer topology. So the first work here that I'm presenting is that you basically build up pseudo-streamer topology. So you have a disconnected equatorial coronal-hole here in blue. And in this work, they applied rotational flows at the boundary between the open-closed boundary of the pseudo-streamer. And guess what? They got interchange reconnection at this boundary, at this separatrix. And what you have here at the end is that you're mixing up open field and closed field, and you are changing the basically the separatrix mapping at the solar surface by changing the connectivity between open and closed field. Again, they looked at what happened in the heliosphere. So they find that here, if you looked at the, so that's the number of counts of time that you have a connectivity change. So there is the heliospheric current sheet again. And what they have is that they are actually extending the width of the pseudo-streamer arc that you have into the heliosphere. You can also get interchange reconnection by having another photospheric forcing. So this is what has been done here. So you build a pseudo-streamer topology here, just close to the open coronal hole here. So the one of the polar coronal hole. So this is the initial state. You have open field and closed field. And when you actually move the pseudo-streamer up, this is what happened. You form a narrow open field region here, south of the pseudo-streamer topology. And so basically now you have open field north and south of the pseudo-streamer. And here you open the field through interchange reconnection, and you form dynamically the heliospheric arc that we're seeing in the S-wave. Okay, so now we know that we have interchange reconnection at those open-close boundary. The question might be, or what we were interested in, is to understand how the dynamic of this interchange reconnection is happening in pseudo-streamer. So what we did is that we did another 3D MHD simulation. So as you guessed, we used ARMS to do that. Thanks, Rick, again. And so we basically built a pseudo-streamer topology as the previous one. And so the main point here is that you have 3 domains of connectivity as it's supposed to be. So you have the open field in blue. So here, this is the disconnected coronal hole. And higher up here, you have the polar coronal hole. Those are open field. Then you have closed field below the pseudo-streamer dome, or the small loops, so they are in green. And you also have closed field below the helmet streamer, and those are the red and the yellow field lines. In this specific topology, we have 3 null points, and the central null points give you the vertical fan separatrix, the separatrix curtain that is going to match the heliospheric arc in the heliosphere, here. Okay. And instead of applying rotational flows to the open-close boundary, since we want to understand exactly how the field and where the field is opening, we did not want to force the separatrices. So what we did instead is that we applied very gentle rotational flows all around the polarity inversion line to force the system gently. We do not want any eruptions. We don't want to have jets or filament formation or anything. We want to see how the pseudo-streamer is evolving gradually through interchange reconnection. So then we looked at, once we applied the photospheric motion, we analyzed the 3 domains of connectivity kind of independently. So we looked at, so here is a map. Yes, it's a cartoon where basically it summarizes the 3 connectivity domains. You have the closed field here in green, the closed field below the helmet streamer in red, and you have the open field. And for the analysis, we looked at each of those set of field lines here in different locations, and depending on where they are located at the open-close boundary or the closed-close boundary. Okay, already changed. So first we looked at those field lines that are actually located on each side of the open-close boundary, and it goes very, very fast. I don't know why. Okay, so basically what happens, so here we are going to see the animation where the closed field is simply reconnecting through standard interchange reconnection along the closed separator or at the null point, and the field just is opening and the open field is closing down. And so we have that, and we see successive opening and closing of the magnetic field for this specific region here. Why does it change while I don't push the button? Okay. So next, we looked at the field lines that are located between the boundary between the closed field below the pseudo-streamer dome and the closed field below the helmet streamer dome. And what we have here, we have absolutely no opening. We only have close reconnection. So this is what you you have seen on the animation before. And so now we are going to look at very special set of field lines that are actually located close to what we call the triple points. So basically, this is where you have the three connectivity domains getting together, okay? And so what we find is that for those points, in those field lines, they don't go through a standard interchange reconnection. They actually go through a two-step opening. So first, the field line close below the pseudo-streamer dome reconnect with the closed field line below the helmet streamer. And then the large closed loop below the helmet streamer, they reconnect at the open separator between the helmet streamer and the open field, and they then open into space, into the heliosphere. And what happened for those specific field lines is that, in fact, they do not stay in a single connectivity domain. They are always changing, and they are constantly reconnecting. We have several states of them. They go from closed to small closed loop to opened to large closed loop to, anyway. So that's a very, very dynamical things. I'm not touching anything. Why the slides are changing? Okay, whatever. So after that, we looked at the heliospheric signature. So here it's just 5 solar radii. So we, every dot, I don't touch that anymore. Each dot, the black dots show that field line that go through interchange reconnection. And what we have here again is that we see the heliospheric current sheet. So maybe it's gonna work. The heliospheric current sheet here. And actually you are, whatever happened to the field line, they are actually opening all over the pseudo-streamer arc here. Okay, so at the conclusion, the first thing that no matter how you force the system and whether it's a narrow corridor topology or a pseudo-streamer topology, you are opening the field over the entire heliospheric arc defined by the S1 model. Then we found, looking at the detailed dynamics of interchange reconnection in pseudo-streamer topology, we find that we can have standard interchange reconnection or a two-step opening process, including closed-closed and then interchange reconnection. And I believe it should not repeat the same type of plasma material into space because it goes through different environment before it gets open into the heliosphere. We also have successive multi-reconnection episodes between the three connectivity domain, and it might play a role in explaining the slow wind variability because it's constantly opening and closing. I think so this specific study complete all the previous study, but we need a lot of work to really characterize how all the interchange reconnection is happening in those pseudo-streamer and narrow corridor topologies. And to finish that talk, I'd like to thank you, Spiro, for this brilliant idea of the S-Web, or Spiro Web, but I think I'm not the only one of thinking about that. And it's been very challenging, at least for me, but a lot of fun to work on pseudo-streamer topology and dynamics. And I personally believe that now we have the theory and the background to understand how we connect the corona and the heliosphere and how we can get slow wind into the heliosphere. Thank you.
So, Sophie, in your calculation, you stress the system, right, and you just hold it there. So you basically add some stress to the closed field
yes.
pseudo-streamer. So, of course, the whole thing is going to blow up, and you're going to increase the amount of open flux.
So we keep it very short in time. So actually, it's not something that we do not for the system very long.
Yeah. But you maintain that stress. You don't let you let it relax, right?
I let it relax.
No, but I mean, you drive the photosphere.
Yes.
And then you just pin it there. You don't let the photosphere go back or anything like that.
No.
Okay.
No.
So you have more stress in your closed field region. So you're going to wind up with a more open field.
Yes.
Yeah, the open flux is going to increase. But this opening and closing that you now find, that the new system doesn't relax to a steady state. It seems like you're saying this opening and closing. This opening and closing that you see, is it occurring at the pseudo-streamer fan, at the S-Web arc, or is it occurring at the heliospheric current sheet?
I would argue that it's at the pseudo-streamer arc.
Okay, that's really interesting because at the heliospheric current sheet, you know, we've seen a lot of this opening and closing.
Yes.
But at the
No,
arc,
no,
we haven't
no,
seen it
this
yet,
is-
so that's really interesting.
Questions? Of course.
Slow solar wind. There are two slow solar winds. That is the plasma sheet slow solar wind that is non-alvenic from the get-go, and it is dominated by structures. And there is the background slow solar wind. Does the SWAB accounts for both or account just for one of them?
I'm not going to do it.
You have a lot of homework from my talk. I hope you're hard at work already. Okay, I think we can go to the last talk. So let's thank Sophie again. And again, my deepest apologies. And now we go to the last talk. Don't leave after the talk. Yeah, let's give it in for Aleida, who is...
Yes. So we're taking a detour and we're going to Mars. With Spiro, yes, in honor of Spiro. So this is cross-divisional work that myself and Kamal Knizhnik are doing with some colleagues in the Planetary Science Division at NASA. Roger Scott has helped us out with this. This is still very much a work in progress. Spiro is holding my baby. This is still very much a work in progress, but I wanted to talk about it because this shows just how powerful of an idea the SWAB is. It is specific. This shows just how powerful of an idea the SWAB is. It is specific enough to provide real insight into the physics, and it is general enough that you can take it from the sun and look at Mars with it as well. So I am going to go over some basics of the SWAB again. Some of this you may have heard, but it's in a very general way because it's going to be the building blocks for what we're looking at on Mars. So you've seen this picture before several times. This is a eclipse image, and you can see on here very beautifully a helmet streamer and a pseudo-streamer. So we have two types of magnetic field lines here. You guys are being very distracting. We have two kinds of magnetic field lines. We have open, we have closed. I think everybody is comfortable with that. We have two types of large-scale magnetic field topologies. We have helmet streamers and we have pseudo-streamers. So helmet streamers have the current sheet above them. In fact, it's the heliospheric current sheet. And pseudo-streamers, they are the much smaller structures, and they are, oh no, pushing the wrong button, surrounded by unipolar field. Okay, now let's try this again. All right, so we have two types of closed structures, and we have two types of reconnection that can occur. So here, these are some images from Wang 2000, and then these are images from arms runs. So Rick didn't include me on the list of talking about arms runs, but I do have pictures from arms in my talk. So the first is you can get pinch-off reconnection at helmet streamers. This is the process that happens at the base of the heliospheric current sheet, where you have this last helmet streamer field line, which reconnects with itself, and then creates this flux rope that moves out into the solar wind. And then interchange reconnection, which can occur at any boundary between the open and closed field. So this happens at the helmet streamer, at the heliospheric current sheet, and it happens at the pseudo-streamer. Okay, so what is the Spiro web? So I want you to be comfortable with looking at these types of plots, but Sam covered some of this, and Sophie covered some of this very nicely. So this is an image from Predictive Sciences, and in the top there, this is a coronal-hole map. The white is closed magnetic field, and the blue and the red are open magnetic field, colored by their BR, by their polarity. And then on the bottom is the matching Spiro web that goes along with it. So if you look at the region that I've labeled C, here, this large white open or closed region is the helmet streamer, and it maps to this contour here.
get the pointer to go. That's the boundary that you see there between blue and red. This is a continuous ring of high Q that follows along the entire helmet streamer and is in fact the heliospheric current sheet in this representation. And then I have the two cases that Sophie laid out so very nicely here with B, labeled with B here, where we have a narrow corridor and then we have a true pseudo-streamer here, and these both map to these regions of high Q arcs that move away from the heliospheric current sheet. So I have in the table down here, you see C here, you can have interchange and pinch-off reconnection at these locations, and pseudo-streamers, you can just have interchange reconnection so far as we know. And I'm not going to talk about jets because we've talked about them enough. Okay, and then I also wanted to say, if I did not explain the pseudo-streamer topology enough for you, Sophie referenced this paper as well. You can go read the OG SWeb paper, and this was published in 2011, which was the year I started working with Spiro. This is the year I started my PhD at Michigan, and you could always tell if Spiro and I had been in a conference room because this clown was drawn on the whiteboard, like over and over and over again at Goddard. Okay, so why do we really care about the SWeb and why is it useful at Mars? The reason it's such a powerful tool is that it takes this very complex, real coronal system and helps us make sense of it. So here, this is an awesome movie by Dan Seaton et al. This is SUVI data, and it's deep exposure, wide field, so that you can really capture not just the low corona, but the middle corona, which is of course where the tops of our favorite streamers are, and then the outer corona as well. And you see all kinds of complexity, you see features moving out. It would be really difficult to interpret what exactly is happening in this system if we didn't have a way to interpret it. The SWeb provides that. And so this is the paper, Sophie showed this movie as well, from Chidda et al. 2023. This is the same time period now, the same SUVI observations. And now you can look at a model run and get the SWeb. So Cooper Downs did this at Predictive Sciences. And basically, the image that you're seeing here, the data that's on the limb of the sun is the black line moving across the SWeb. So you take that plane, and you move it into the page, and that's where the black line is. And so now you can say, well, there's a lot happening here, but I know that this top structure here is the heliospheric current sheet to begin with, and there's a pseudo-streamer down here. Then I know that the heliospheric current sheet flips on edge for a few frames, and I'm getting detail that way. And then I know that the helmet streamer, the pseudo-streamer is on the top and the helmet streamer is on the bottom. So it provides a really powerful tool of interpreting what exactly you're looking at for a complex system. Okay, so Mars is a complex system, it turns out. You might not know much about Mars. I actually don't know that much about Mars. That's what my planetary colleagues are for. But it does not have an intrinsic dipole. Its magnetic field is made up entirely of these crustal magnetic fields. You can think of them as bubbles stuck onto one quadrant of the planet. So it's far from symmetric. So here, this is a nice visualization of these crustal magnetic fields and then the solar wind interacting with them. This is the way that planetary physicists often visualize the crustal magnetic fields. And you can see that they're starting to talk about, okay, we have three topologies. We have closed field, we have open field, and then we have this draped solar wind field that goes over top of the planet, and all of this is going to interact in a very complex way. So Mars is complex. It displays properties of both an intrinsic and an induced magnetosphere, and we can use the Spiro web to figure out what's going on. Okay, so just to motivate this, why do we care what's going on at Mars? There's some interesting problems here. This is some work done by Gina DiBraccio in 2018, and I'm just going to focus on the main point here, which is to say the top two panels are data, the bottom are models. If you don't include the crustal fields, then you just get this nice draping of the solar wind over the planet, and you have two symmetric lobes in the magnetotail of Mars. So that's this one here. Okay. And if you include the crustal fields and you get any kind of reconnection with them, then you get this twist in the tail of Mars, which is what they see in the data. And so what planetary physicists are really trying to do is understand how does that reconnection occur between the crustal fields and the solar wind field to create this twist in the tail. Also, they talk a lot about magnetic flux ropes. We're solar physicists. We love magnetic flux ropes. We know all kinds of different ways to get them or not get them, depending on how you think about it. And so they are wondering, okay, if we have these dipolar magnetic fields here, can we get reconnection with the solar wind to create flux ropes? Also, if anybody has looked at the helmet streamer before, you wonder, oh, can I get pinch-off reconnection at that region? Okay. And then, of course, on a very philosophical level, this is important because we want to understand how Mars has lost so much of its atmosphere and understand the life cycle of the planet because, of course, we're humans and we're trying to figure out how life works in the solar system. Okay, so the idea is, can we take the same language that we use to talk about the sun, can we make a Spiro web at Mars, and then can we use that to inform the physics that's actually happening? So to do that, you need a magnetic field data cube. We are using the Morschhauser model, which is built off of data from the Mars Global Surveyor as well as the MAVEN spacecraft. On the sun, we can use remote imaging to estimate in some way what the magnetic field is. You can't do that at Mars. And so what they've done is taken orbit after orbit after orbit of magnetic field data and then done a spherical harmonic expansion downwards towards the surface to build up this model. So there are several different ones out there. The people I'm working with, this one's their favorite, so that's why we picked it. The important assumption that goes along with this is that you're not looking at the true crustal fields, right? You're looking at an average of the state of the field that the spacecraft is measuring. So this includes seasonal variation at Mars. As the planet rotates, the crustal fields are sometimes in the tail, sometimes at the nose. And then also Mars has seasons, and so like all of that is included. So there are some important assumptions that we're making, but you gotta start somewhere. Okay, so here's the image from the paper. Planetary physicists use this horrible coordinate system, XYZ, even though they're dealing with a spherical body. But Coleman and I managed to recreate these plots here. So this is BX, BY, BZ at the surface of Mars, and it matches the paper. And then we haven't done any real modeling here. We've just traced field lines through this data cube and computed Q and asked, what kind of structures are we seeing? Okay, so ta-da! Here is the Martian Spiro web. So on the left is a Martian coronal-hole plot, if you want to think of it that way. So there are, the two top panels are at 600 kilometers, the bottom two are at 775. The bottom two are, you're really slicing through the very, very tops of those magnetic field bubbles, and then 600 is just like a little bit lower. So on the left, the black regions are closed, and then the blue and the red are open and colored by polarity. So just like the coronal-hole plots that we looked at before. And then on the right is our beautiful Martian S-web. So what can we learn from this? Well, Mars has at least 9 helmet streamers. So on the sun, we typically only talk about 1. Sometimes there's 2. I've seen it happen. But here, each of the locations where you see a high Q ring, and if you look over at the coronal-hole plot and it's spanning BR in opposite directions on either side, that's your helmet streamer. Additionally, there are an entire network of pseudo-streamers, all at various heights. So we have lots of high Q arcs. And what's cool about Mars is that because it's got so many helmet streamers, you're actually getting high Q arcs between helmet streamer regions. Thank you. Which is not something we see a lot at the sun. So what's going to happen there? I don't know. Sounds cool. And then this is just another way of looking at this. I wanted to include this because Coleman and I refer to this as the Roger plot, because the paper that Sophie told you to go read has a lot of really cool images where he's figured out a nice way to visualize, okay, this is my S-web at 600 kilometers, and then you take a slice in latitude and longitude, and then you can look at that slice with altitude as well. So if you look at this blue line here, that's cutting through the helmet streamer at several points as well as a few pseudo-streamers, and you can see the depth of these structures here. So this is very much a work in progress, but Spiro, you are enabling all kinds of work at Mars. You should be proud. The results we have so far, just from a really simple look at the B field cube, are that Mars has 9 helmet streamers at least, lots of opportunities for flux propagation. That's great news. It has a whole network of pseudo-streamers. That's lots of opportunity for atmospheric escape, super cool. Maybe that can tell us about the twist that's observed in the Martian magnetotail. And of course, we want to keep on with this work. We're working on a full analysis using field lines, and then we're also planning on comparing to some in situ data from the MAVEN spacecraft. So I think this is just super cool. This is like a first light image of the Spiro web at Mars, so it's really exciting. Now, my last slide here, I knew I was going to give the last talk at Spirofest, and so I wanted to end on some life lessons from Spiro Antiochos. This is my last slide, so Erica, I'm sorry, but I'm going to go ahead. So this is a picture from my thesis defense in 2016. I don't know what we were thinking, but we were obviously having a good time. Lesson number 1 is tell a story with your talk. To know Spiro is to hear him tell a good story, and he is always telling you to make sure that you have your audience paying attention to you, and the best way to do that is with a story. Hold a pointer steady. Don't wave it around like a lightsaber.
Clearly, none of us learned
None
this
of us.
during
He
this,
has been
during
judging
this
all
conference.
of us the last 2 days completely. The first talk that I gave as a graduate student when I got down off the podium and felt like, wow, I did a really good job. Like I actually nailed that. He said, Aleda, you did a great job, but you were like a Jedi up there. You need to get that under control. So he's definitely been judging us all week. Science is paramount. Everyone has said this. Everybody knows this about Spiro. I've included this picture again. I think Larry took it. So I just love this so much because it really just encapsulates Spiro. The world locked Spiro in his house during the pandemic, and here he is on Zoom, just like clamoring at the camera to show us the whiteboard because the science just cannot be contained. The science must go on. Ask questions. You can learn something from everyone. The students in my cohort had an observation, and we should have turned it into a drinking game, but you go to AGU or you go to Shine, and Spiro can walk into the last minute or 2 of a talk and ask the most important question out of the entire audience. He just catches the end, and he catches the essence of it. And I asked him once about it, and he said, you have to ask questions because everyone can teach you something, absolutely everyone. Mistakes are no big deal as long as you get back to the science. There were many times as a graduate student where you make a mistake in the code. Etienne, you said, oh, you ran something at the wrong beta. I had a factor of 2 off in one of my simulations in Spiro, and I spent a week trying to figure out what was going on. And I figured out over the weekend. I walked in his office 10 a.m. Monday going, oh man, like he is gonna kill me when he realizes that I just forgot a 2 in the code. And he went, oh, that's what's happening. Okay, great. So that means this, and this. Like he didn't blink. He didn't blink. And that moment really stuck with me, especially as a student. Okay, if you're skeptical, use your eyebrows. Maybe that's why you don't have any hair anymore, Spiro. You're always using your eyebrows. I always knew I was about to be challenged if I got the look. And I heard, well, wait a minute now. Professor Higginson. Know your fundamentals. Spiro once pulled out his cheat sheet when I was in grad school that maybe you made it as a postdoc or grad student, I don't know, but it was very comforting to know that even Spiro has a cheat sheet tucked away somewhere in his bookcase, and from it he can derive the entire sun and solve the entire heliosphere. So, take care of your people. Spiro absolutely understands that we are all humans, we have needs, and he always made sure to take care of the money and the paperwork so that people's needs were met so that they could do the science. And finally, enjoy your life and your family. I'm so glad, Spiro, that I have pictures of you with both of my children. I want to share a sweet anecdote, which is that when I had good news to share that I was pregnant with my first child, Spiro was very happy for me, but he's always good at reading the situation, and he could tell that, I was a little bit nervous just because it's even in 2019, it's not nothing to have a baby as a woman in science. And he said to me, Aleda, I would trade every single paper and all of the awards if it meant that I got just one extra day with my family, with my boys, with my wife. They have made me happier than anything in the world, and I am so happy for you. So thank you, Spiro, for your mentorship, for your science insight. Everyone in this room is better off because you are a heliophysicist.
Since Oliver, I think. Thank you, Aleida, for the talk, for Mars, for sending Spiro to Mars, and for the life lessons. We're not doing questions? Aleida doesn't want questions.
I'm trying to give up your award.
I haven't done, there is a committee for the awards. Ben, you have to be fast because we have awards.
I'm really intrigued by the spherical harmonic representation of Mars, and as someone who's put spherical harmonics into arms, what do you think over the next that have to get trained by Rick on how to evolve the code and putting in a boundary condition that's basically like a solar wind in the x-hat direction in our spherical coordinates, and we just pretend the sun is Mars, and let's see what happens.
We should definitely try that after Rick gets through items 1, 2, 3 on his to-do list.
Or we can just do a fourth or more.
Field fixed on Mars?
Yes.
Good, so that makes it a lot easier. That means you only have to vary the
solar wind.
The driver, solar wind, yeah.
Yep.
Okay.
Let's thank Aleida again. Let's thank all the speakers of the 2 days of conference. Spiro, I'm giving you time to go and do your committee things. Go do the back. And let's thank Jim and Judy, who were the main organizers of this beautiful event. You will have your time, Jim, don't worry. But now, no, they're going. Okay, Jim, you have some time to say things. The committee has been at hard work for 2 days, thinking about all these talks and all these prizes and things. And also, there is not only one prize now. Of course, we need to kill time because the committee is gone.
First of all, well, let me tell you. So if I gave you a badge to get in the building, please remember to get that back to me. They look, they're orange. There were only 4 of them. I have 1, 2, 3. Yeah, and Aleida has 1. And, oh, there we all have them all. Great. And thank you all for coming. I think it's been a really great success, and you brought the good weather with you, and you've been a wonderful group to have here, and you're welcome back anytime.
Thank you for having us. Thank you. But now,
Also, we have to turn in our land use, right?
I mean, you don't, those ones are the important ones.
Yeah.
Like,
Yeah.
but now, the committee has been at hard work for 2 days, and there are decisions that have been made. I want everyone to prepare phones because, wow. Yes, exactly. Prepare phones because the prizes will be delivered by Spiro inside. Let's go to the stage, Spiro. Yeah, let's come. Let's go. This is very serious prize ceremony. This has been delivered like the Oscars.
Are we going to call up people like, Brad Pitt and stuff, and Clooney to come and announce the winners?
Exactly. The announcer for this. So, I need the microphone.
Okay.
So the awardee has to come up and will be given the prize by Spiro himself, and I hope there will be pictures being taken. So the first prize awarded at the Spirofest 2024 is the Best Gym Dig Prize, awarded to Roger Scott. There is an actual diploma.
We're taking photos, right? That's right. Thank you for the hot tip.
So old is it?
Our second prize is, The second prize is the High Fashion Prize of the Spirofest 2024, awarded to Benjamin Lynch.
What happened?
The third and second to last prize is the Best Bribe Prize, awarded to Etienne, Pariat.
Next time, champagne. Oh, well, you win all prizes then. Then you get everything.
And finally, the prize that we all knew was coming. I don't know who is the winner of this one. The Best Comedian Prize of the Spirofest 2024 goes to Joel Dahlin. Oh-ho! Yes, and since this, the Oscars, yes. In public. Don't ruin the diploma.
It's invaluable.
I mean, you're like, there is Spiro's autograph on the diplomas.
Sell that for millions in a few years.
That's right, millions again.
Comedy Act cartoon
This is exactly like using the point.
I would give in the meanwhile, I would give an applause to Mary, who I'm sure was sent by Spiro to purchase the prizes. Thank you, Mary.
Many truffles, many truffles.
So did you just give back the bribe that you got from Etienne?
I'm holding it up so people can see it.
What are they? Oh, some mini truffles. Right. Some cat cards.
Cat cards.
Nice. Some space socks.
Nice.
Bravo, bravo.
The diploma.
Diploma.
Invaluable.
Thank you so much. You put a lot of work into it.
I hope you will all put these prizes on your CVs. And now I leave the microphone to Jim.
All right, thank you.
I can finally go to smoke.
Well, there's not too much left to say, except I think this has been very successful. It's because of you guys. I mean, you really came through with the talks. Great science, a lot of great humor, and praising of our hero Spiro. So thank you for making this a big success. And ultimately, of course, there would be no meeting without Spiro. So thanks for being you. So I guess we're adjourned.